plus 2. The first problem is of the form, x, 1 plus 2 equals x, whereas the second is of the form, x, y, z, 3 equals x plus y plus z. This second problem, unlike the first, consists of one equation with three unknowns. In general, when the number of unknowns is greater than the number of equations, the problem is indeterminate or mathematically ill-posed. In the preceding example, this happens because the addition function has no inverse. Hence a problem of this kind has, at best, multiple solutions. We shall next meet an insoluble problem. The capital accumulated over a given number n of years at a given rate r is given by the familiar formula, Cn equals C0, 1 plus r, n, where C0 is the principal, initial capital. To compute Cn from C0, r, and n is a direct problem that any calculator can handle. By contrast, the problem of finding out both the number of years, 152, and the rate of interest that will earn a desired sum has as many solutions as couples, that is, infinitely many. Hence, from a practical point of view this problem, so easy to state, is insoluble. No wonder that investment counseling is, black, art rather than rigorous technique. 4. Interlude, induction. To compute a value of a well-defined mathematical function is a direct problem. By contrast, figuring out a function given some of its values is an inverse problem, namely, that of curve fitting, dot joining. There are standard techniques, such as the venerable Gregory Newton formula, for performing such interpolations. However, most of these techniques yield functions of the same dull family, namely, polynomials that can be made to pass as closely as desired to the given empirical points. The existence of such algorithms falsifies Popper's opinion that induction is a myth. Induction does occur in science, both in suggesting low-level generalizations and in evaluating the empirical support of hypotheses, Bunge 1960. Moreover, induction is sometimes mechanizable, as in the case we just saw. What is true is that induction does not yield high-level and amazing, counterintuitive, results. Indeed, in general the resulting data-fitting polynomials that compress and expand data differ from the true laws, which ordinarily involve far more complicated functions. For example, the elementary law of the simple, idealized, pendulum, deduced from Newton's second law of motion, is T equals 1/2, L/g, 1/2, an approximation that can in turn be approximated by any of infinitely many polynomials in L/g. In this case, which is rather typical, the problem of induction is an inverse problem with infinitely many solutions, none of which is the correct one. The quest for high-level laws from data is hopeless unless the corresponding direct, deductive, problem has been solved in very many similar cases. More on this below. That induction is confined to low-level generalizations has been known for a long time, not so the reason for this limitation. The reason that induction cannot lead to the upper rungs of the deductive ladder is this: an inductive reasoning is semantically horizontal, in that it leaps from particular statements to a generalization containing exactly the same specific, non-logical, concepts involved in the data. For instance, n experimental dots on the xy plane can be joined by a polynomial of degree n, 1 in x, namely, y equals a 0 plus a 1x plus a 2x2 plus an xn. Thus, if y stands for a spatial coordinate, and x for time, the function may represent the motion of a point mass, such as the tip of a harmonic oscillator. Yet, no matter how large n may be, that is, regardless of the bulk of the database, the said function is bound to be a poor and clumsy. 153. Approximation to the true solution of the linear oscillator problem, namely, y equals a sin t. This solution involves the oscillation frequency, a parameter missing in the data but occurring in the equation of motion, which is one logical and semantic rung above the data. This, then, is why there can be no vertical inference from data to high-level laws, because the latter contain concepts absent from the former. Since experience cannot generate any high-level concepts or hypotheses, these must be invented. And invention is anything but a rule-directed process, one subject to algorithms that could be fed into a computer. Calling such invention abduction, following Peirce, 1934, 5.181, only suggests the illusion that it is a mode of conclusive inference. It is preferable to think of theoretical concepts as free creations of the human mind, Einstein 1950a. Such constructs are free in the sense that they are not necessitated by sense data. But, of course, contrary to the free fancies that the artist may indulge in, and that Husserl, 1931, 199 ff., commended for doing phenomenology, the scientific constructs are constrained by logic and scientific observation. 5 mathematical problems to find and problems to prove. Most mathematical problems are, in Pappus's, AD 320, terms, either problems to find or problems to prove, Thomas, ed. 1941, 567. With luck, the former are well-posed direct problems, such as drawing a polygon, solving an equation, integrating a function, expanding a function in series, or just checking a calculation. By contrast, problems to prove are generally harder and more important than problems to find. The first strategy a mathematician will try to prove a conjecture of the form if A, then B is to assert it, yet negate its consequent B, and check whether this entails some contradiction. If it does, the theorem is pronounced true; if not, it stands falsified. In either case the task will have been accomplished. Clearly, such indirect reasoning is strictly deductive. It is also clear that, in case of success, one may summarize the process with the formula conjectures and confirmations, since proving a theorem amounts to confirming the initial conjecture. Popper's, 1963, slogan Conjectures and Refutations, adopted by Lakatos, 1978, is only good for weeding out falsities through exhibiting counterexamples. Spotting mistakes does not make up for constructing guesses and corroborating them. The farmer who did nothing but weeding would have nothing to eat. If the theorem to be proved does not yield to indirect reasoning, the mathematician may have to resort to first principles. In this case, he tackles an inverse problem, that of guessing the assumptions A, axioms, other theorems, lemmas, or definitions, that jointly entail the statement T to be proved. The 154 form of such a problem is A. At. Regrettably, theorem proving is all too often presented as a direct problem like this: find the logical consequences of a given set of assumptions. This is not a realistic description of mathematics in the making, because, A. Not all the consequences of a set of assumptions are equally interesting, and, B. Some new assumptions, such as auxiliary constructions in geometry, and lemmas in analysis, may have to be introduced or revised to prove a conjecture, and it takes knowledge and imagination to hit on the pertinent constructions or lemmas. Inverse problems are also called ill-posed. Surprisingly, Jacques Hadamard, 1952, proposed the first definition of a well-posed mathematical problem as recently as in 1902. Regrettably, calling inverse problems ill-posed may have discouraged their investigation, for nobody wants to waste his time tackling wrong questions. Not surprisingly, most of the literature on inverse mathematical problems is rather recent and comparatively modest, although it has been growing exponentially in recent years. For instance, the journals Inverse Problems, Journal of Inverse and Ill-Posed Problems, and Inverse Problems in Engineering were born as recently as in 1985, 1989, and 1995 respectively. The first international conference on the subject took place in Hong Kong in 2002, and the year after the first handbooks, Ullman 2003, Woodbury 2003a, appeared. However, some ancient mathematicians did attack successfully a few tough inverse problems. The best known of them is Euclid, who among other things was the first to propose the postulate system for what has since been known as Euclidean geometry. Some historians of mathematics have claimed that Euclid did nothing but collect the geometrical knowledge that had accumulated until his time. In truth, he accomplished this, not a mean task in itself, and much more. Indeed, he organized that corpus in the most rational way, namely, axiomatically. In fact, he invented the so-called axiomatic method, which is actually a format rather than a method, since there are no rules for finding axioms. Euclid guessed a postulate system encompassing all that geometric knowledge. His was an inverse problem, because it is the dual of proving theorems from given premises with the help of given rules. Given a set of axioms and definitions, finding what they entail is a straightforward task by comparison with going upstream, from conclusions to premises, in particular from special cases to generalizations. True, Euclidean geometry is synthetic, not analytic, in the sense that it contains no algebra and therefore no algorithms, hence, the proof of nearly every theorem in it requires inventing a special construction, or importing a lemma from an adjoining field. However, given all the premises, and the rules of inference, the conclusions follow unambiguously, so much so that there are algorithms for proving. 155. Theorems in Euclidean geometry on computers. This is not the case with guessing postulates, an inverse problem with multiple solutions. In fact, there are several postulate systems for Euclidean geometry, among them those proposed by Hilbert in 1899, Huntington in 1913, and Tarski in 1959. Two of the 23 famous problems posed by Hilbert in 1901 were inverse, namely, to axiomatize the calculus of probability and the main physical theories of the time. The first task was attempted by various mathematicians, until in 1933 Kolmogorov proposed the standard solution. As for physical axiomatics, Hilbert himself gave one example, namely, the simple phenomenological, descriptive, theory of radiation. Regrettably, he did not axiomatize any of the basic physical theories of his day, although he was conversant with them. The first axiomatization of non-relativistic quantum mechanics, as well as of classical and relativistic mechanics, classical electrodynamics, special relativity, and Einstein's theory of gravitation, was performed by Bunge, 1967a. These axiomatizations included not only the mathematical formalisms, but also their realist physical interpretations via semantic postulates of the form mathematical concept M represents physical thing or property P. This work is being updated by a handful of physicists, see, example Covarrubias 1993 and Perez Bergliafa et al. 1993, 1996. 6. Astronomy and microphysics. Aristarchus may have been the first to tackle an inverse astronomical problem, namely, that of guessing the real and presumably regular planetary orbits from data about their apparent positions. This was a particularly intriguing problem at the time, given that the planetary trajectories, observed from Earth, were anomalous by comparison with those of the fixed stars. Indeed, planet means wanderer. Aristarchus hit on the right answer, he hypothesized the heliocentric system. However, he was unable to calculate any predictions, because the requisite mathematics had not yet been invented. Ptolemy mastered these formal tools, but his explicit goal was to describe appearances rather than to explain them. In fact, he may have been the first positivist, Duhem 1908. His ingenious geocentric system, involving the proverbial cycles and epicecles, succeeded in describing and predicting with remarkable accuracy the apparent motions of the then known planets. This was an astronomical feat, but at the same time a setback for physics, because the planets were attributed motions very different from those of the rest of the bodies. Besides, the planets and the Sun were considered as a motley assemblage of idiosyncratic celestial bodies rather than the system postulated by 156. Aristarchus. Ptolemy's achievement was also a setback for ontology, because it widened the theological, and Platonic, chasm between the terrestrial and the celestial. Finally, his victory was a defeat for epistemology too, since it seemed to show that science favors phenomenalism and conventionalism over realism, a mistake repeated by the Inquisition against Galileo, as well as by Hume, Kant, and the positivists and neopositivists, from Comte and Mill to Nelson Goodman and David Lewis, recall Chapter 1. The ancient Greek and Indian atomists were even more ambitious than either Aristarchus or Ptolemy. Indeed, they wished to explain everything visible in terms of invisible atoms hurtling in the void, from the drying up of sails and the manufacture of bronze to mental processes. They transformed the inverse problems effects causes and phenomena noumena into the corresponding direct problems. Ancient atomistics was, moreover, the first thoroughly naturalistic ontology. However, it was also a grand fantasy, since its upholders, who claimed to explain everything, did not account in detail for anything in particular. The transmutation of atomistics from a metaphysics into atomic physics took 2 millennia. Indeed, Daniel Bernoulli, 1738, was the first to explain a macrophysical law, Boyle's law of ideal gases, in atomic terms. And Dalton, 1803, was the first to explain, approximately, some simple chemical compounds in like manner. These and other accomplishments did not suffice to persuade the majority of 19th-century physicists, who clung to classical, phenomenological, thermodynamics up until Planck's foundational paper of 1900. As usual, philosophers upheld tradition. Thermodynamics matched the positivist philosophy popular in the philosophical community between the mid-19th century and mid-20th century. This philosophy, like that of Ptolemy, Hume, Kant, D'Alembert, Mach, Pearson, Duhem, and Ostwald, and contrary to the realism of Galileo, Huygens, Newton, Euler, Ampere, Faraday, Maxwell, and Boltzmann, enjoined scientists to stick to the phenomena, appearances. It involved a ban on the investigation of the inverse problem of going from phenomena to noumena, in particular the microphysical realities behind the former. Mach went so far as to claim that sensations, such as those of hotness and loudness, were the bricks of the world. The same phenomenalist thesis resurfaced later on in some of the works by Bertrand Russell, Rudolf Carnap, Hans Reichenbach, and Philipp Frank. Meanwhile, physicists were busy exploring such non-phenomenal entities as electrons and fields. Ironically, most of the founders of contemporary atomic theory, in particular Bohr, Born, Heisenberg, Jordan, Pauli, and Dirac, kept that obsolete empiricist philosophy. This they did while performing the Herculean, or rather Newtonian, feat of solving the inverse problem of going from macrophysical. 157. Description to microphysical explanation. For example, magnets were explained as assemblages of atoms with parallel magnetic momenta, and light rays as streams of photons. Still, positivism, in particular phenomenalism, was smuggled into textbooks and philosophical essays. For example, the basic dynamical variables, such as linear and angular momentum, spin, and energy, were dubbed observables even though they are not directly measurable. 7. Reading diffraction patterns. At about the time that atomic and nuclear physics were being built, crystallography underwent a breakthrough thanks to the use of X-rays. These were employed to discover the atomic configurations underlying the 230 pure crystal structures that had earlier been described morphologically. The method used to solve this inverse problem is as follows. A beam of X-rays, or of electrons, is made to diffract by a crystal. The diffracted waves show up on a photographic plate as spots forming an intricate geometrical pattern, such as parallel bands or concentric circles. These patterns are strikingly different from the atomic array that diffracts the rays. Hence they do not speak for themselves, they have to be interpreted. And this interpretation is actually a scientific explanation, not a hermeneutic intuition. It is carried out as follows. The crystallographer assumes a plausible crystal structure, and solves the direct theoretical problem of calculating the corresponding diffraction pattern. More precisely, he builds a theoretical model, or mini-theory, comprising hypothetical crystal structure, wave optics, and Fourier analysis. The coefficient of each term in a Fourier series for each hypothesized crystal structure is found by measuring the intensity of the corresponding X-ray beam. The theoretical pattern is then compared with the experimental one to check whether the theoretical model, or mini-theory, fits the experimental data to within the tolerable error. If it does not, the scientist keeps changing the hypothesized crystal structure until he reaches a correct result. Molecular biologists use the same method to discover the structure of proteins and nucleic acids. This is in fact how Crick and Watson unveiled the so-called genetic code in 1953, by the reciprocal adjustment of a sheaf of clever hypotheses with piles of X-ray diffraction patterns obtained by other researchers. Nowadays the crystallographer or molecular biologist need not proceed from scratch. Indeed, he can avail himself of a catalog of crystal, or molecule, structure diffraction diagram pairs. If the solution occurs in the catalog, he looks no further. Otherwise he chooses the pattern closest to his own, wiggles some of the parameters in the corresponding crystal structure, and 158. Tries again, until he solves his problem. He proceeds thus by successive approximations to the truth. See Figure 6.1. The problems in quantum physics are similar. Here, the forward problems are of this type: assuming the forces, or the potentials from which they derive, calculate the possible energy levels, transition probabilities, scattering cross-sections, and other genuine observables. The corresponding backward problem is, of course, to figure out the potential from the said measurable properties. In particular, a physicist working with particle accelerators, atom smashers, faces the following problem. He knows what goes into a box, namely, a particle beam, and what comes out of it, scattered particles or photons. He knows the former because he has made it, and he knows the latter because his measuring instruments have recorded it. The physicist's ambition is to find out what goes on inside the box. That is, he seeks to unveil the mechanism mediating the incoming to the outgoing particle beams. In short, his problem is, observed facts likely mechanisms. Until recently, next to nothing was known about nuclear forces except that they are strong, short-range, saturable, and non-classical. In the early days of theoretical nuclear physics, a rather simple-minded method was adopted to tackle problems such as that posed by the scattering of neutrons by protons. Typically, one used to posit a potential well, for the unknown attractive force, with a simple shape, such as a dromedary's humps. One then adjusted the depth, force strength, as well as the width, force range, of the well to fit the experimental values of the energy levels and the effective scattering cross-section. In recent years, some algorithms have been devised for performing this task, which may be carried out on a computer, example Zakharev and Chabanov 1997. BTD. Figure 6.1 M X-ray and particle diffraction. A beam B of waves or particles is diffracted by a target T of unknown nature, and a diffraction pattern D is photographed. The problem is to guess T from D. The way to proceed is to assume several alternative Ts, calculate the corresponding patterns using Fourier analysis, and check which of them agrees best with the observed D. The latter may be concentric rings of dots, or parallel bands, that do not resemble at all the structure of T, a neat example of the poverty of appearances. 159. Hall 1999. Moreover, by deforming the potential and noting the effects on either the energy levels or the scattering cross-section, the scientist is said to develop an intuition different from that gained in solving direct problems. Even new vistas and new problems may emerge when focusing on inverse rather than direct problems. However, some of the properties of the said potential have to be assumed, for instance, that it is piecewise continuous, bounded below, and symmetric. Besides, the algorithms in question, though numerically powerful, do not solve the essential problem, which is that of the nature of the forces at play. After all, computers are not concerned with physical interpretation. Nowadays there are refined theories of nuclear forces, so that in principle one could solve the direct problem, that is, compute the scattering they cause. However, the computational difficulties are formidable. Therefore, inverse problem solving is still prominent in the entire field. The difference with the old days lies in the fact that by now a rather extensive catalog of solutions of a state, or wave, equation for different potentials, or forces, is available. Hence, an examination of any new set of empirical data may point a trembling finger to the corresponding potential. 8. Invertibility. If the solution to a direct problem is a 1:1 map, such as the exponential function, then the solution to the corresponding inverse problem exists and is unique. For example, if it is known that a given process decays exponentially in the course of time, as in the cases of radioactivity and the destruction of a bacterial colony by an antibiotic, then the time at which the process started can be calculated from the residual intensity of the process. This is how carbon dating works. Indeed, assuming the ratio of carbon-14, radioactive, to carbon-12, stable, at the time of death of a fossilized organism, the date of that event is obtained by taking logarithms. Recall that y equals a exp, bt, is equivalent to t equals 1/b, ln, y/a, dot. Another typical case is that of economic planning on the strength of a production model, see, example Gale 1960. The gist of this model is the equation for the net production of a firm, P, I, A, equals G, where P is the production vector, A is the input-output matrix, I is the unit matrix, and G the demand or goal. The direct or forecast problem is to find G given P and A. By contrast, the inverse or planning problem is to find P, the intensity of the activity, given A and G. This problem consists in inverting the matrix I, A to obtain P equals G, I, A, 1. However, this problem need not have a solution, that is, the matrix in question may not have an inverse. In this case, then, solubility invertibility. And even if the 160 matrix does have an inverse, the solution vector P, though mathematically unique, stands for any member of a whole set of different activities, or mechanisms, with the same intensity. Such indifference to specific mechanism is of course characteristic of black box models. A black box theory models the system of interest as a black box with two terminals, the input C, circumstance, situation, stimulus, and the output R, overt response, both observable, example Bunge 1963. See figure 6.2. Typically, both input and output are indicators, that is, observable manifestations of imperceptible events in the system or its environment. The particular cases of null input, or spontaneous activity, and null output, or indifference to environmental stimuli, are supposed to be included. That is, the low-level law characterizing the system in the given environment is of the form R equals B. See the mathematical forms of C, R, and B depend on the kind of problem. For example, C and R may be functions, and B may be the operator relating them, or all three may be matrices. Problems of two kinds can be tackled with the help of a black box model like the one we have just sketched, one direct problem and two inverse problems. The direct problem is one of forecast, given B and C, compute R. The corresponding inverse problems are these: A, hindcast problem, given R and B, find out C, that is, calculate C equals B, 1. R. This problem is insoluble if B lacks an inverse, as in the case of a rectangular matrix. And when B does have an inverse, the computational task may require a high-powered computer, as the macroeconomists, who deal with huge input-output, Leontief, matrices B, know well. B, explanation, or synthesis, problem, given R and C, find out B. In other words, given the data, guess the process or mechanism responsible for their particular pairing. This is not a mere matter of computation, the task calls for potent theorizing, as made plain by crystallography, diffraction spots crystal structure, and atomic and nuclear physics, Scattering cross-sections force. The practical ideal is of course to be able to use algorithms, that is, precise and mechanical, mindless, computation rules or procedures that can be entrusted to computers. However, the vast majority of algorithms work only. CMR. Figure 6.2m. A black box, or externalist, model of a system specifies the input or circumstance C and the output or response R, but not the internal process or mechanism that transduces a C into R. 161. For well-posed, forward, problems, or for certain narrow classes of backward problems occurring in theories with powerful mathematical formalisms. For instance, as mentioned in section 4, there are now algorithms to tackle the scattering data scattering force problem in microphysics. Still, these methods fall short of the empiricist's dream, which is to leap from data to theory, since nothing can be inferred about the nature of the forces at play. Indeed, any given potential shape is consistent with forces of many different kinds. For example, although the shapes of the gravitational and the electrostatic, or Coulomb, potentials are the same, the corresponding fields, or forces, are very different, as shown by the different ways of detecting them and measuring their intensities. So, strictly speaking, the algorithms in question do not solve the given inverse problem. What they do is to supply the theorist with constraints on the possible forces. The rest, that is, guessing the forces, is up to the theorist's ingenuity. Still, in most cases even the most astute theorist will fail. For instance, the mass of a body is uniquely determined by its mass density. On the other hand, any given value of the total mass is compatible with infinitely many mass densities. Hence, the mass density problem is insoluble. The same holds for all the other densities. In particular, given a probability density, one can compute any desired statistic, such as the average and the variance. Yet the inverse problem, namely, statistics probability, is just as insoluble as the trajectory equation, S, of motion problem. Equally insoluble is the problem of recovering the initial state of a branching process of the stochastic kind. Any given final state is compatible with very many different beginnings. Think of the thermal equilibrium state attained by a system composed of two or more bodies, at different temperatures, that come into contact. Better yet, think of the Boltzmann-Planck equation S equals KLNW, which relates the macrophysical property S, thermodynamic entropy, to the number W of different microphysical configurations consistent with a given value of S. What if the inverse problem proves intractable? In this case one may try cheating a little, namely, by transforming the given ill-posed problem into a well-posed one. This somewhat irregular procedure is called regularization. The idea is to make the problem regular by changing the original problem slightly. Essentially, one exchanges the old ill-posed problem for a new regular or well-posed one whose solution, hopefully, lies near that of the original ill-posed problem. Woodbury 2003b, 57. This procedure is admissible if the solution is stable, that is, if small changes in the data map into small changes in the regularized solution. Thus, the cheating is kept under control. So much for the formal aspect of the invertibility problem. Let us now. 162. Glance at its substantive aspect. In all of the factual sciences, inverse problems are tackled in either of two ways. One is to transform the given ill-posed problem into a well-posed one, regularization. The other approach is to attempt to guess the unobservable mechanisms, processes, that mediate between the observable stimuli and responses. The first strategy is purely formal, and therefore it can be employed only when precise mathematical models are available. Otherwise one must take the bull by the horns, hoping to come up with a more or less precise model of the system or process in question that describes the essential traits of the mechanism that gives rise to the observed facts. Here is a random sample of examples of the second kind: the generation of seismic waves by the collision of tectonic plates, the cathode ray tube behind the screen in a TV set, the process whereby insulin regulates the breakdown of sugar, the action of alcohol on mood, the combination of gene changes with natural selection that drives evolution, the genome-environment combination that results in a phenotype, the combination of cooperation and competition that holds a social system together, the big business, politics connection that corrupts democracy, and such quality control mechanisms as random product sampling and peer review. More on mechanisms in Chapter 5. 9. Inverse probabilities. Let us finally make a quick remark on the old problem of inverse probabilities, which we met briefly in Chapter 4. This problem arises in applications of the Bayes theorem PR, BA, equals PR, AB. PR, B, PR, A. In this formula, the arguments of the probability function P are sets, and the conditional probabilities PR, BA, and PR, AB, are said to be mutually inverse. Actually they are mutually dual rather than inverse, because neither of them is logically prior to the other. The direct inverse distinction is epistemological and it arises in applications. Let us peek at this problem. As in any other formula in the probability calculus, the arguments A and B can be interpreted as random states or events. And yet some statisticians, epidemiologists, rational choice theorists, and philosophers have used the formula to calculate either the probability PR, CE, of the cause C given the effect E, or the probability PR, HD, of hypothesis H given data D. These popular applications are open to three fatal objections. A first objection is that such interpretations contradict the tacit assumption in science that, with reference to any real situation, the arguments of a probability function must denote random states or events rather than either causally related events or propositions. For instance, one does not compute or measure. 163. The probability that a rainfall will wet the ground or the probability that the Schrödinger equation is true. Popper claimed that law statements have zero probability, and this is why he regarded improbability as a virtue. My point is that it makes no sense to assign probabilities to propositions, recall Chapter 4. A second objection is that ordinarily the prior probabilities PR, A, and PR, B, are unknown, so they are made up, hardly a scientific procedure. Indeed, an arbitrary assignment of numbers to unknowns yields no knowledge, it only creates a false impression of rigor. It may even lead to disastrous practical consequences, as when Bayes' formula is applied to medical diagnoses or business or military decisions. More in Bunge 1985b, 1988, and 2003a. Probability applies legitimately only to random events, such as quantum tunneling, gene mutation, or random choice. My third and final objection to using Bayes' formula to infer causes from effects, or initial states from final states, is that it does not fit actual scientific practice. Thus, the quantum theory of radiation allows one to calculate the probability PR, NN, that an atom in a state N will decay to a state N and emit a photon. The same theory yields a different formula for the probability P, NN, that an atom in a state N will absorb a photon and jump to the energy level N. These two probabilities are not related by Bayes' theorem. Nor could they be, because the corresponding mechanisms are quite different. Indeed, spontaneous light emission occurs even in a closed system, and is thought to be influenced by the zero-point fluctuations of the vacuum field. By contrast, light absorption can only occur if the system is open enough to let at least one photon in. 10. Whether epistemic or practical, problems can be direct, forward, inverse, backward, or neither. The third category includes such problems as those of evaluating actions or artifacts, interpreting formalisms, teaching new subjects, and finding new problems. Research on direct problems follows either the stream of events or the logical sequence. By contrast, research on inverse problems works backward. And research on problems of the third kind proceeds typically in a zigzagging fashion. Obviously, a problem of either kind is either soluble or not. If soluble and inverse, its solution is either single, first kind, or multiple, second kind. The problems of the first kind are characterized by an invertible mapping, whose domain is a set of unobservables, and whose image is a set of data. For better or for worse, such problems are less numerous than the far more unwieldy but more interesting problems of the second kind. An inverse problem of the 164. Second kind, that is, one with multiple solutions, is equivalent to a whole family of direct problems. That is, in this case one proceeds by imagining different scenarios, or mechanisms, that might produce the same result, or different premises that might entail the same conclusions. In sum, some of the most challenging and rewarding scientific problems are of the inverse type. And the most promising strategy for handling a tough inverse problem is to try and transform it into a direct problem. This is what Newton did to account for the observed trajectories of terrestrial and celestial bodies. Indeed, despite his protestation that he did not feign hypotheses, he certainly posited some and proceeded deductively rather than inductively. In fact, Newton crafted the earliest successful theory in history in response to the most intriguing and topical inverse problem of his time. Thus, he tackled the so-called Hume's problem in technical terms long before Hume posed it in ordinary knowledge terms. Furthermore, Newton solved that problem. Why then not call it Newton's inverse problem? 165. 7. Bridging fact and theory. In this chapter we will carry on the investigation of inverse problems begun in the previous chapter. But here we will concentrate on the dual problems of how to go from facts to hypothesis or theory and how to subject the latter to reality checks. In other words, we will study the problems of how to move from the given to the far wider and deeper sought for and how to force a theory to face facts. We shall also tackle the converse problem: how does one go down from high-level theories that make no direct reference to any data to empirical evidence for or against them? In particular, what counts as an observable indicator of an unobservable fact? One induction again. Much, perhaps too much, has been written about the leap from data to hypothesis. And yet this kind of inference still puzzles philosophers and cognitive psychologists, as it should. There are two main myths about induction: that it is everything, example sometimes Bacon and Russell, Carnap and Reichenbach always, and that it is nothing or nearly so, example Leibniz, Hume, and Popper. The former myth belongs to the core of empiricism, whereas the latter is at the center of rationalism. Francis Bacon is usually regarded as the inductivist par excellence. This he certainly was in his New Atlantis, 1624, the utopia where he depicted scientists as data gatherers and packers. But Bacon was no simplistic inductivist in his Novum Organon, published 4 years earlier. Here he dismissed induction proper, or generalization from particulars, as trivial. He advocated instead framing alternative hypotheses and checking them, if possible experimentally, and he introduced the concept of a crucial experiment, by analogy with a crossroad. 166. Of the various examples Bacon gave, perhaps the clearest and most interesting concerns the nature of weight, a much discussed problem in his time. Is heaviness an intrinsic property of bodies, or is it caused by the Earth's attraction? He proposed the following ingenious experiment to settle the question, 1905, 30. Take two clocks with different mechanisms, one moved by a spring and the other by a pendulum, synchronize them, and carry them to the top of a tall steeple. If weight is an intrinsic property of bodies, the two clocks will continue to mark the same time, otherwise the pendulum clock will tick slower than the other, because the gravitational attraction must be weaker at a higher altitude. Bacon's experiment was actually not performed until a couple of centuries later, disproving conclusively the hypothesis that weight, unlike mass, is an intrinsic property of bodies. At the same time, he showed the centrality of hypothesis in science, in spite of which he is usually regarded as a radical inductivist. Many philosophers have been rightly skeptical about the power and reliability of induction proper, but different philosophers have adduced different reasons for doubting it. Hume's, 1734, is the best known. He argues that the fact that the sun has risen every day in the known past is no guarantee that it will rise again tomorrow. Hume's tacit assumption is that there are no laws of nature, that nature has only certain habits that it may quit without warning, much as an individual may suddenly quit smoking. Astronomers think differently. They predict confidently that the sun will rise every day as long as it lasts, provided our planet is not hit by a large asteroid or comet. This prediction is based on the law of conservation of spin, or intrinsic angular momentum. And this law applies to our planet because this body is similar to a frictionless spinning top. Hold a rotating spinning top in your hands, and you will find out how hard it is to alter the rotation axis. Likewise, human biologists predict confidently that human immortality is impossible, not because so far all humans have had a finite lifespan, but because the human body ages unavoidably through various mechanisms until finally all the more critical subsystems break down. Thus, we affirm the truth of all humans are mortal not just because of past experience, but because we can explain aging. In both cases, those of sunrise and mortality, scientists reason on the strength of lawful mechanisms, not mere empirical generalizations. In the case of the succession of days and nights, the mechanism is the occultation of the sun resulting from the diurnal rotation of the earth. And human mortality results from the concurrent operation of several mechanisms, wear and tear, stress, oxidation, inflammation, mutations, and the consequent inability to synthesize certain proteins, telomere shortening, and so on. 167. The limitations of induction derive from the shallowness of its products, all of which concern only observable properties, with no reference to hidden mechanisms. By contrast, direct reasoning from law statement to fact presupposes that nature is lawful rather than capricious. Hume was obviously right in holding that the leap from some to all is logically invalid. But he was wrong in denying the objectivity of connections, in particular laws, and thus in denying the existence of natural, or gnomic, necessity along with logical necessity, see Bunge 1959a. 2 centuries later Kripke, 1980, perpetrated a similar fallacy when asserting that, since the hypothesized identity mental function equals brain process is contingent rather than logically necessary, it may not hold in worlds other than our own. But of course if such worlds are accessible from ours, then they are not worlds proper but only remote regions of our universe, and if they are inaccessible, then we can only fantasize about them, a task best left to fiction writers. To conclude this section, all the deeper and therefore more interesting scientific hypotheses and theories are conjectured. And this process, from data to hypothesis or theory, is neither inductive nor deductive, it is as little rule-directed as falling in love, composing a poem, or designing an artifact. To abduction again. Many students agree that the way to account for observable facts is to frame alternative hypotheses, and then weed out the false ones, ideally by means of crucial, conclusive, experiments. This was well known to Francis Bacon, 1620, William Whewell, 1847, and John R. Platt, 1964, among many others. Regrettably all three authors, along with many others, called this procedure induction, while strictly speaking induction is the formation of a single low-level generalization from the data in hand, as when a dog learns to associate leash with walk, or a baby learns to call all men dad. Calling this procedure inductive method or strong inference suggests mistakenly that it is a safe and quick recipe for devising hypotheses from data, when in fact there is no such method, except for Pavlovian conditioning, which obviously does not help frame scientific hypotheses. The only strong inference is deduction, as it occurs in the derivation of a scientific prediction from law, and data. This is so because deduction, unlike induction, analogy, and guesswork, is the only inference subject to precise, stringent, and general logical rules. In turn, these are general because they are formal, whereas non-deductive inference depends essentially on content. For example, the analogies 1:2, 2:4 and individual is to society as atom is to molecule are both content. 168. Dependent and logically independent from one another, neither is deducible from the other. Some philosophers favor what the great Charles S. Peirce, 1934, 5.181, called abduction. He rightly regarded this as an act of fallible insight rather than a methodical procedure. Harman, 1965, termed it inference to the best explanation, a phrase that occurs frequently in the contemporary philosophical literature. However, it is still being debated whether this is either a form of induction or anything other than the choice of the hypothesis that best accounts for the data, where in turn best is equated with most accurate, explaining the most, or least ad hoc, simplest, or all three. See, example Flack and Caucas, eds 2000. However, exact empirical adequacy and conceptual simplicity are neither necessary nor sufficient in the advanced sciences. Here, a reasonably well-confirmed hypothesis that belongs to a well-corroborated theory, on top of which it coheres with the ruling worldview, ranks much higher than a stray empirical generalization, even if the latter fits somewhat better the data in hand. This condition, which I have called external consistency, Bunge 1961, 1967a, is roughly what Thagard, 1978, terms explanatory coherence. However, the word systemicity may be more suggestive than either of those names. The reason conceptual systemicity is highly desirable is this: when entrenched in a coherent, systematic, body of knowledge, a hypothesis enjoys the support of other members of that body in addition to the relevant empirical evidence. If only for this reason, the frequent resorting to crime detection in the literature on the scientific method is somewhat unfortunate. Surely good detectives make alternative conjectures and check them, but they do not construct or even use scientific theories. And in some fields, such as psychology, anthropology, medicine, and management science, theorizing is still frowned upon, so that the hypotheses are scattered and therefore they hardly enrich and control one another. To get a feel for this creative process, let us analyze some representative examples taken from the life sciences, social studies, and technology. 3. Biology, evolution. Evolutionary biology, like cosmology, geology, archaeology, and historiography, is a historical science. Hence its practitioners face a large family of inverse problems of the present past type. In particular, the reconstruction of any lineage, or phylogeny, is tentative if only because of the large gaps in the fossil record. However, qualitative novelties emerge in the course of 169. Individual development, which can be monitored and altered in the laboratory. Therefore, some of those novelties can be caused deliberately on modern organisms. This is why some inverse problems in evolutionary biology and genetics can be transformed, at least in principle, into direct problems. Actually, this is how evolutionary biology became an experimental science between the two world wars, by tampering with the genome, first with X-rays, and nowadays chemically as well. Recall from section 1 that inductive generalization from a bunch of data works only for hypotheses involving exclusively observable features, such as all mammals are hairy, but it fails miserably for high-level hypotheses, such as all mammals descend from reptiles. How does one go about framing such high-level hypotheses? The short answer is that one invents them, though not out of the blue but with the help of data, analogies, further assumptions, and above all a sensitive and experienced nose. For example, a comparison of certain well-known phylogenies with the history of the Earth suggested to Elizabeth Verba, in Gould 2002, 918 ff, her turnover pulse hypothesis. This is the conjecture that the massive speciations and extinctions that have punctuated biological evolution over 3 billion years were triggered by drastic and rather quick environmental changes, such as large variations in global temperature, meteoritic impacts, and continental drift, to which we must now add the alterations caused by pollution, logging, overcultivation, overfishing, and the like. The hypothesized mechanism is obvious: such swift and large-scale environmental disruptions destroy some habitats while opening up others. For instance, when a land mass splits into two, the area of shallow water, propitious to marine life, increases roughly by half. Certainly, evolutionary biology is not the sole abode of inverse biological problems. Every attempt to find the unknown organ that discharges a known function, or performs a certain role, requires research into an inverse problem. This holds, in particular, for the task of the cognitive neuroscientist, said to be that of mapping the mind onto the brain. However, here too many an inverse problem can be transformed into a direct one. For example, by tampering with the brain, the neuropsychologist can cause mental disorders or deficits in experimental subjects. More in the section 5. What holds for organismic and evolutionary biology holds, a fortiori, for the sciences that investigate lower levels of organization, in particular genetics. Thus, the problem of identifying the gene, S, responsible for a given phenotypic trait is of the inverse type. For example, if an adult mammal does not tolerate dairy products, it is because it cannot synthesize lactase, the enzyme involved in the digestion of milk, and in turn lactase deficiency is due to the 170 lack of the gene involved in its synthesis. The researcher is thus faced with the inverse problem: metabolic disorder, enzyme deficiency, genetic disorder. Once the suspect genes have been fingered, the problems of finding out the corresponding enzymes can be tackled. The solution to these direct problems should solve the original inverse problem. The practical payoff is obvious though still distant, namely, gene therapy. For medicine, from symptoms to diagnosis. Something similar holds, mutatis mutandis, for medicine. A few medical diagnostic problems are direct. Open bone fracture is one of them. In this case there is no need to guess invisible mechanisms to account for the cause of tissue ripping, bleeding, and pain. However, all of the diagnostic problems in internal medicine are of the inverse type. Indeed, they are of the form given such and such signs, guess the underlying causes. In the old days, such guesses were educated only by experience and post-mortem examinations. Nowadays basic anatomical and physiological knowledge, along with biological and biochemical assays, X-rays, CT scans, fMRI images, and other diagnostic tools often help spot the trouble. Using such diagnostic tools, the physician transforms the original inverse problem into one or more direct problems. For example, if the patient complains of fatigue even with adequate nourishment and rest, the physician may suspect anemia, and order a leukocyte count to check this hypothesis. But a look at the patient's family history may suggest diabetes, in which case the physician will order a sugar level measurement among others. These are direct problems because experiment has found that the said suspects, and no others, cause the symptoms in question. As with inverse problems in other fields, the most promising biomedical research strategy is to imagine and test mechanismic hypotheses. Actually, this is how contemporary biomedical research proceeds. The starting point is a conditional of the form ailment syndrome, or X, AX-SX, read for all individuals. If anyone suffers from ailment A, then she exhibits syndrome S. The direct problem of inferring S from A is trivial, but it seldom occurs in the internal medicine clinic. Here the problem is inverse, symptom ailment. And any solution to it is only tentative, unless supported by research findings concerning mechanisms. These extra hypotheses are likely to be of the forms A if and only if M, AM, and M if and only if S, MS. Here M summarizes the description of some mechanism, such as artery clogging, TB infection, or work-related stress. Now the strong inference AS can proceed confidently, more in Bunge 2003a. 171. 5. Psychology, behind behavior. In daily life we all face the problem of figuring out the beliefs and intentions that motivate other people's actions. In other words, we attempt to read other people's minds off their overt behavior. There are two ways in which humans, chimpanzees, and some pets do mind reading. One is by empathizing with others, example Preston and Duvall 2002. The other is by framing various theories of mind, that is, by attributing to others certain beliefs, preferences, or intentions, example Premack and Woodruff 1978, Whiten 1997. Clearly, consistent success in empathizing and mind reading confers an advantage. By contrast, mind reading inability, as in egotistic individuals, and autistic and Asperger patients, is a serious handicap in social intercourse. Methodologically speaking, the mind reader transforms the inverse problem behavior intention into a family of direct problems of the intention behavior kind. But of course any such theory, or rather guess, may turn out to be false. Worse yet, the observer may be unable to craft one because his medial prefrontal cortex is deficient or damaged, like that of an autistic patient. Hence, our guesses about other minds are tentative and subject to falsification. However, judging from the assurance of his pronouncements, the believer in the infallibility of introspection, mind reading, and Verstehen, hermeneutic interpretation, does not seem to realize how formidable his task is, and how dicey his conclusions, conjectures, are bound to be. This holds in particular for the psychoanalyst, the parapsychologist, the phenomenological psychologist, and the follower of the Verstehen or interpretation method. Indeed, going from behavior to intention is incomparably harder and riskier than going the other way round. In this process, misverstehen, misunderstanding, is almost as frequent as verstehen, understanding, comma. One reason for such uncertainty is that different people are likely to react differently to the same stimulus, some from self-interest, others from reason, some from habit, others under coercion, some rationally, others under the sway of passion, some out of fear, others out of greed, some for moral reasons, others from hypocrisy, some lucidly, others under self-deception, and so on and so forth. In short, the behavior-motivation relation is one-to-many. Cognitive neuroscientists have been tackling the behavior-intention problem for nearly half a century. They have been using such techniques as implanting electrodes on the prefrontal cortex to record the neuronal discharges that are part of the decision-making process. More recently they have also started to study the brain mechanisms that ensue in social behavior as well as in its inhibition, such as the role of the amygdala and other brain. 172. Centers in causing both prosocial and antisocial behavior, see, example Oxner and Lieberman 2001, Blakemore et al. 2004. To accomplish this task, the cognitive neuroscientist resorts not only to classical electrophysiological procedures, but also to such non-invasive brain imaging techniques as CT scans and fMRI. Thus, he outreaches not only the social scientist but also the pre-biological social psychologist, because he treats mental processes as brain processes. By comparison, the claims of the believer in the power of Verstehen, hermeneutic interpretation, sound like wishful thinking or even shamanism. More on this in the next section. Evolutionary psychologists face a far more daunting task, because emotions and ideas do not fossilize. They proceed in two very different ways, whereas some of them fabricate entertaining stories, others engage in evolutionary neurobiology and comparative psychology research. The former way is unconstrained by hard data, and is therefore popular. It consists in explaining every contemporary pattern of behavior, social norm, and deviance from the norm as having been designed by natural selection, see, example Barkow, COSMIDES, and Tooby, eds 1992. For instance, allegedly we find relativistic mechanics hard to understand because our mind was shaped about 100,000 years ago by the Pleistocene environment, when our ancestors had to contend only with slow-moving things such as stones and leopards. The fact that many people can learn and even invent counterintuitive ideas remains mysterious. Serious evolutionary psychology is composed of two main intertwining threads: evolutionary neurobiology, and comparative ethology and psychology. So far, the former has not found much, perhaps because it is basically limited to ascertaining changes in brain size, which is a poor indicator of mental ability. For instance, the brain must certainly grow beyond a certain threshold for certain mental processes to emerge. However, actually human brain size has decreased, not increased, over the past 35,000 years. We still don't know why. Comparative psychology has been somewhat more successful. For instance, Kabanuk, 1999, has suggested that emotion is likely to have emerged with reptiles, not before, because lizards, and of course mammals and birds, but not fish or frogs, exhibit signs of emotion when stroked. And Duvall, 1996, has conjectured that empathy emerged with the immediate ancestors of both hominids and apes, because all of them empathize, whereas monkeys hardly do so. If these conjectures were to hold up, emotion is likely to have emerged ca 400 million years ago, and empathy, and cruelty along with it, only about 8 million years ago. 173. 6. Social studies, from individual to society and back. The social sciences tackle inverse problems of two main kinds: inferring, actually guessing, individual behavior from systemic social features, such as cultivation, stratification, and dictatorship, and figuring out beliefs, preferences, and intentions from ostensible individual behavior. The two problems concatenate thus: collective features, individual behavior, belief, and intention, whereas collective features can sometimes be gathered from archaeological remains or social statistics. Individual behavior calls for either direct observation or conjecture, and in turn the attribution of intention demands a questionnaire or conjecture, as well as experiment whenever possible. Again, these are only special cases of problems of the following forms, which occur in all of the sciences and technologies: observable, unobservable, output mechanism, and effect cause. There are at least two reasons for the difficulty, ubiquity, and importance of problems of this kind. A first reason is that social scientists have a hard time producing data related to collective features, such as social strife, inflation, and the dominant morality. In particular, archaeology is the only discipline that seeks to study human behavior and thought without having any direct contact with either. Trigger 2003b, 133. A second reason for the difficulty of the problems in question is that to explain a fact, state, event, or process, is to describe how it happens, that is, to unveil its mechanism, and mechanisms are typically unobservable, recall Chapter 5. Hence, the inverse problems should not be written off in the name of the empiricist, in particular behaviorist, dogma that all that matters is observable behavior. All the same, it would be foolish to ignore that problems of this kind are hard, so much so that, in attempting to solve them, we often mistake fiction for fact, as when taking altruism for enlightened self-interest. As we saw in Chapter 5, physics contains powerful and generally accepted principles that allow one to solve many direct problems, and that can then be used as guides for solving the corresponding inverse problems. Regrettably, no such guides are available in the social sciences, which still lack theories at once general, precise, and well confirmed. The social scientist must nearly always hazard hypotheses and build theoretical models, specific theories, from scratch. To highlight the predicament of the social scientist, let us propose a few elementary examples. 174. First example: country X has very few hospital beds. This circumstance can be attributed hypothetically to, either the neglect of public health care or the good health of the population. Second example: there are no peasant revolts in country Y. This non-fact may be interpreted as the effect of either harsh repression or light taxes and corvées. Third example: only half of the electorate bothers to vote in country Z. This fact may be interpreted as either contentment or disillusion with the political system. Only further research, making use of additional indicators, could resolve the three ambiguities. A mainstream social scientist is likely to investigate either socially embedded individual actions, such as weddings and burglaries, or entire social systems, such as schools or businesses. By contrast, a doctrinaire methodological individualist is bound to focus on the subjective experiences of the actors, such as the choices and decisions of a businessman. If a hermeneuticist, he will focus on either empathy, like Dilthey, or on intention guessing, like Weber. In either case he will engage in psychological interpretation, or attribution of mental states, not in semantic interpretation, or pairing of symbols to concepts. And if a rational choice theorist, the student will center his attention on the alleged probabilities of events and their attending subjective utilities, on the assumption that all persons act so as to maximize their expected utilities. That is, in any case the individualist will psychologize. He will do it whether, like Comte, Durkheim, Weber, or Popper, he denies emphatically that psychology is relevant to social science, or whether, like Menger, Simmel, von Mises, or Budin, he invokes a psychology that, being commonsensical, abstract, or rational, a priori, rather than experimental, is anything but scientific. In either case, the methodological individualist will tend to exaggerate the importance of individual motives and decisions at the expense of natural resources, work, and social structure. See Bunge 1996, 1998, and 1999. And he cannot be taken seriously if he adopts or concocts an abstract, or folk, psychology, which is bound to be simplistic, hence unrealistic, because it is centered on cartoons, such as Homo economicus, Homo loquens, Homo aleator, or Homo ludens, or even on outrageous myths, such as that the behavior of Jews is characterized by resentment, Nietzsche and Weber. The methodological individualist claims to be able to find out what is usually supposed to be private, namely, the hopes and fears, as well as the goals and intentions, of the decision-makers. In particular, if he is a hermeneuticist, the student will claim to read such subjective features off the actor's behavior, he would thus be the privileged owner of a special faculty, Verstehen, understanding or interpretation, unknown to the natural scientist. But how does the hermeneuticist know that he has interpreted correctly the 175 data in hand, that is, that he has hit on the true hypothesis? He does not, because he lacks precise and objective standards or criteria to choose among alternative interpretations, guesses. Nor is there any chance that he will ever come up with such criteria, because the very concept of an objective and universal standard goes against the grain of any subject-centered philosophy. The hermeneuticist's choices are arbitrary, because he trusts his intuitions and consequently does not put them to the test. However, this objection won't worry the hermeneuticists, because they hold that the cultural sciences, unlike the natural ones, do not practice the scientific method, which is centered on the requirement that hypotheses pass some empirical tests before being declared true in some degree. In sum, the hermeneuticist asks us to take him at his word, which is natural enough for an intuitionist but not for a rationalist, who knows that intuition is an unreliable friend. The rational choice theorist, for his part, does not bother to guess the particular motives of his actors, he claims them to be the same for everybody under all circumstances. Indeed, he decrees that all motives are basically one, namely, to maximize expected utilities. Where the hermeneuticist cooks à la carte, the rational choice theorist offers a single tourist menu. The moral philosopher will note the parallel between act utilitarianism and rule utilitarianism. Whether rational choice theorist or hermeneuticist, the methodological individualist faces the problem of figuring out the beliefs and intentions that may motivate his character's actions. In psychological jargon, as we saw above, he attempts to read other people's minds off their behavior. In other words, he has to invent theories of mind. Methodologically speaking, he transforms the inverse problem behavior intention into a family of direct problems of the type intention behavior. But of course mind reading may and often does fail. However, judging from the assurance of his pronouncements, the believer in accurate mind reading does not seem to realize how formidable and dicey this task is. And yet married people know how many misunderstandings arise daily from the naive belief that they can read their partner's intentions off their gestures or stray words. In short, the behavior-motivation relation is one-to-many. Claiming that it is one-to-one is to defy overwhelming adverse empirical evidence, and to oversimplify a huge pile of extremely complex problems. 7. Figuring out social mechanisms. Of all the inverse problems in social studies, the toughest are those of figuring out and checking the mechanisms underlying the observed social facts. 4. 176. Example, nobody seems to have found the mechanisms of the business cycle. In particular, the neoclassical microeconomists do not have a clue about it, because they focus on free markets in equilibrium operating in a political vacuum, a triple idealization. 2 additional reasons that those theorists cannot find the mechanism in question are that their theories seldom if ever involve what physicists call the independent variable, namely time, and that they contain only observable variables. This limitation to observable variables is the reason Marx called them vulgar economists. Marx's failure to find what he called the laws of motion of the capitalist economy is beside the point. His methodological point, that such laws must exist beneath the phenomena, quantities and prices, was sound. Logic and semantics explain why there can be no straightforward leap from single observable events to general laws. The logical reason is that valid, deductive, reasoning may go from generalities to particulars, not the other way round, except in the trivial case this sum. And the semantic reason is that the high-level concepts occurring in the high-level laws, such as those of equilibrium, efficiency, knowledge, and marginal propensity to save, do not occur in the data relevant to them. Recall Chapter 5, Section 2. The hermeneuticist seems not to realize this elementary methodological point. He believes that he can leap safely from observable behavior to the wishes or intentions behind it. By contrast, the rational choice theorist seems to realize that point, since he claims to be able to deduce behavior from the alleged universal law about maximizing expected utilities. In other words, whereas the hermeneuticist claims to be able to discover causes from their effects, the rational choice theorist claims to know a priori the putative mother of all effects, namely, self-interest. One of the many problems with the rational choice theorist is that he takes that alleged law for granted. However, the law in question is not universally true, see, example Hogarth and Redder 1987. Indeed, most of us cannot afford the best. Ordinarily we must settle for a far more modest goal, for satisficing, March and Simon 1958. Moreover, most of us tend to be risk-averse, and so try to avoid losses rather than aim for great gains, Kahneman, Slovic, and Tversky 1982. Consequently, the revealed preferences seldom coincide with the secret ones. Worse, sometimes we are the victims of self-delusion, at other times we do not know what we want, and we seldom know exactly why we act as we do. Knowledge of self is so imperfect, that the ancient Greek adage, know thyself, is still topical. Thus, the claim of both the rational choice theorist and the hermeneuticist, that they can attain perfect knowledge of other people's innermost motivations without performing psychological experiments, is comparable to the psychoanalysts' conceit. 177. The alternative to both hermeneutics and rational choice theory is the scientific method. A quick study of the familiar yet poorly understood problem of the causes of delinquency should help clarify this point. It may also help design effective crime prevention policies. We need two models to account for criminal offenses, one for individual behavior and the other to account for criminality as a regular feature of a whole social group, such as the proverbial inner-city inhabitants of the industrialized world, or of the shanty town of the Third World. In other words, we need one model for the proximate causes of crime, and a different one for its distal causes, those that drive an individual to commit repeated offenses, or even to adopt crime as a career. I adopt Wickstrom's model for the former case. Figure 7.1 exhibits a simplified version of it. This model may be supplemented with one of the distal causes of crime. The basic idea is that criminal behavior is largely a result of marginality, economic, political, or cultural. Two salient features of marginality are unemployment and physical segregation. Besides, there are two microvariables that must be reckoned with: anomie, the psychological counterpart of marginality, and solidarity, which compensates to some extent for anomie. I assume that these four variables are related as shown in figure 7.2. The arrows in this diagram symbolize causation. In all cases but the last, an increase in one of the variables causes an increase in the dependent one. By contrast, stronger solidarity decreases both anomie and criminality. Both models can easily be quantitated, see Bunge 2005b. What holds for the basic social sciences also holds, with all the more reason. Figure 7.1m proximate causal factors of unlawful acts, modified from Wickstrom and Sampson 2003, 122. Offense. Dispositions and social situation. Risk of sanctions, deterrence. Options and choices. Temptations and provocations. Other. Perceived. 178. For the social technologies, from pedagogy and the law to management science and the so-called policy sciences. In fact, here one faces practical issues of this kind, given the present state of a social system, and a set of desiderata, or desirable final state, find out the best means for forcing the initial state-final state transition. However, technology deserves a separate section, not only because it is the engine of modern industry and government, but also because the philosophy of technology is even more backward than the philosophy of science. 8. Reverse engineering. The expression reverse engineering has spilled over to psychology and other fields. However, technological problems, whether direct or inverse, are very different from problems in other disciplines. They are typically design or maintenance problems, not problems to find something out there or to prove some conjecture. There are two reasons for this difference. One is that technology deals with concrete artifacts such as machines and organizations. Even software is ultimately concrete since, by contrast to pure mathematics, it guides a sequence of states of a machine. The second reason is that nowadays the typical technologist is not a self-employed inventor but an employee or a consultant. His employer or customer, far from giving him carte blanche, requests the invention or maintenance of a device performing a given task. He only specifies the desired output and the budget. Indeed, technologists are expected to invent, perfect, or maintain artifacts of some kind, whether inanimate like roads and computers, living like cultivars and cows, or social like corporations and government departments. The more creative technologists invent new artifacts to either meet needs or create wants. Think of designing a bridge capable of taking a given load and subject to given budgetary constraints, or of designing a firm capable of producing or selling a given good or service, as well as of yielding a certain return on a given capital. Both are inverse problems, and they have either many solutions. Macro-level marginality, criminality, ostensive variables. Micro-level anomie, solidarity, hypothetical variables. Figure 7.2m distal causal factors of unlawful acts, modified from Bunge 2003a, 209. 179. Or none, depending on the state of the art, the available resources, and the employer's goals. However, the inventor of cybernetics asserted that problems of invention may be direct as well as inverse, Wiener 1994, 91 ff. I submit that, whereas the former are problems of improvement on an existing artifact or process, the latter require radical innovation. An improvement problem looks like this: perfect an existing artifact with a known defect in design or operation. By contrast, a radical invention problem is of either of two types: come up with a radically new device or find a new use for a given device. Wiener's own examples were inventing the vacuum tube for radio transmission, and using it in one of the early computers. From an economic viewpoint, the difference is this: whereas improvements are often market-driven, radically new inventions may help create new markets. More precisely, a technological problem of the second type looks like this: invent a device that will meet such and such specifications. Ordinarily, a problem of this type is harder the broader the specification. A broad specification lists only the essential functions or tasks that the artifact is expected to perform. For the concepts of function occurring in technology and elsewhere, see Mario and Bunge 2001. Such specification states nothing about materials or processes. Now, in principle, any technological function can be realized by several alternative mechanisms, processes in the system concerned. Just think of the variety of timepieces, calculators, bridges, means of transportation, communications media, healthcare systems, and business firms. In other words, the function-mechanism relation is one-to-many, not one-to-one. This leeway gives the designer some freedom. By the same token, it imposes compromises and hard choices. Indeed, typically, the technologist asked to solve an inverse invention problem is presented with an input-output pair, and asked to design the box that will transduce the unknown input into the desired output. In electrical engineering, this class of problems has traditionally been known as circuit synthesis. This is the converse problem of the analysis of circuits, a comparatively straightforward direct problem that is solved using standard physics and the mathematics inherent in it. By contrast, an inverse or synthesis problem calls for more than physics. It also requires technological imagination, tinkering, and trial and error. Of course, all creative scientists are imaginative. For instance, they try to imagine the constituents of a given or assumed natural thing, and the way such constituents are held together. The engineer's daydreaming is necessarily different, because he is not given anything, except for a specification and 180. Perhaps also a box of possible constituents of a system. His task is to devise a new system with existing constituents, or even to invent new constituents, such as nanotechnological circuits and motors. Take applied chemistry for instance. The task of the analytical chemist is to find out the chemical composition of a given lump of matter. This is certainly an inverse problem, but one quite different from that of the pharmacologist intent on designing a new molecule with a given biological effect, such as lowering high blood pressure. Another clear example is this: a physicist can calculate the electromagnetic field irradiated by the electric current in an antenna of a given shape. By contrast, a radio engineer has got to devise a directional antenna, or antennas array, capable of irradiating waves of a given bandwidth to a given place on Earth or in outer space. The biomedical researcher faces a similar problem: given a diseased organism, design a therapy that will improve the patient's health. Here again, the problem is to find the most suitable means to attain a given goal. Could reverse engineering problems be entrusted to a suitably programmed computer? Hardly, because machines cannot invent new ideas. They can only combine given ideas, or rather their physical tokens, in accordance with given rules. For example, from the mid-1970s on, some computer programs have been designed, starting with Dendril, that come up with possible molecular structures when fed certain empirical data, such as chemical composition, along with certain constraints, such as valences, see Feigenbaum and Lederberg 1968. Yet Herbert Simon and other computer enthusiasts have claimed that future computers will solve problems and construct theories of all kinds, perhaps with the help of the mythical logic of discovery first announced in the 17th century. For instance, it has recently been claimed that the so-called genetic programs can come up with new electronic circuits, Koza, Keen, and Streeter 2003. However, analysis of these achievements show that they have four limitations. First, the programs in question are far less valuable to science than to industry, since they do not contribute to understanding anything. Second, they do not come up with radical, non-combinatorial, novelties. Third, they could not possibly fit such specifications as a molecule that will affect mood or a computer that will solve finite difference equations. It still is up to the pharmacologist or the engineer to conduct bench tests to find out what the functions of the novel thing in question are. The fourth fact is that all the programs in question do is to examine or to put together, either haphazardly or according to rule, a large number of given elements, such as resistors, inductors, and capacitances. They do not tell us which configurations are the most suitable for certain goals. Likewise, a calculator can tell us, say, that 10 guests, 181, can be seated at a table in more than 3 million ways, but only the experienced hostess will know how to pair off congenial people. In short, combinatorial chemistry and combinatorial electronics are useful but not enlightening. Only theory can enlighten. Let us consider now an example from social technology. In principle, any public policy goal, such as the containment of an epidemic or population control, can be achieved by different means. These go from quarantine to education to economic disincentives to forced sterilization to massacre. This is a problem of reverse social engineering, as is that of the central banker intent on using fiscal means to tame inflation, enhance consumer confidence, decrease unemployment, win an election, finance a military aggression, or what have you. The case of terrorism is tougher than the above-mentioned cases, because it is less well understood, and what is not well understood cannot be controlled effectively, let alone efficiently. One obvious reason for our deficient knowledge of terrorism is that terrorists are elusive and, when caught, are at best studied only by government psychologists. And these tend to overlook the political context, which is macro-social. Besides, usually terrorism is handled only by politicians obsessed by the next election and by the military, and the individuals of both classes only know the tit-for-tat tactics, the biblical recipe for an unending spiral of revenge. Popular platitudes, such as that the sources of terrorism are poverty and ignorance, are at variance with the evidence. Most terrorists are well-educated members of the middle class, Sageman 2004. The practical moral is that raising the standards of living and education of the population where the terrorists are recruited is not the solution. Political terrorism is not only multilevel, micro and macro-social, but also multifactorial, political, economic, and cultural. Hence its understanding calls for a systemic approach. In any case, far more serious research is needed, and only a concerted effort by social psychologists and politologists might explain suicide bombing and kamikaze-type attacks. In the meantime, I suggest a combination of two concurrent mechanisms, involving the micro, or individual, and the macro, or institutional, levels to explain that sinister combination of self-immolation and the murder of innocents in the name of a losing cause. Macro-level oppression and segregation retaliation. Micro-level anger terrorist attack. 182. 9. Bridging theory to fact. The popular account of the way scientific theories are contrasted to facts is this: deduce observable consequences, and compare these with the pertinent outcomes of observations. That is, proceed as follows: deduce observable consequences from theory. Obtain empirical data. Confront prediction, with data. Evaluate theory. This schema, called the hypothetico-deductive method, is common to both empiricists, inductivists, in particular logical positivists, and rationalists, deductivists, in particular Popper and his followers. Undoubtedly, it contains an important grain of truth. But it is also severely flawed, because theories do not imply observations without further ado, and consequently they cannot be contrasted directly with the relevant empirical data. A few examples should suffice to make this point. Celestial mechanics cannot predict eclipses by itself, quantum mechanics by itself cannot predict the wavelengths of the light emitted by atoms, psychology remains speculative without behavioral and physiological indicators, and economics can neither explain nor predict anything without a battery of indicators, such as ammonia production, an indicator of agricultural production. Much additional assumption and information are needed in all cases. For example, Newton's equations of motion do not imply any features of the simple pendulum. To describe the latter we must start by modeling it, for instance, as a point mass hanging from a rigid frame and subject to gravity. Likewise, the calculus of probability is insufficient to make probabilistic predictions, we must add to it a randomness hypothesis, such as that of random mating, recall chapter 4. In general, the actual test procedure is this: enrich the given theory with a more or less idealized model of the object under study, whether planet, molecule, cell, or social organization. This model is defined by a number of subsidiary assumptions, that is, assumptions not contained in the general theory though compatible with it, for example, that the surface of a solid is smooth, that a wave is plane, that a bacterial colony has an infinite supply of food, that a market is perfectly competitive, or that only the parties directly involved in an international conflict matter. The next step is to relate some of the concepts occurring in the model to the pertinent observable indicators of the unobservable items referred to by the theory, angle of deviation of a pointer in the case of an electric current, bones. 183. And artifacts in the case of an archaeological site, GDP in the case of a national economy, and so on. An indicator is a relation, preferably functional, between an unobservable property U and an observable one O. That is, U equals F, O. Reading O on a meter or in a statistical table we can calculate U, see Bunge 1967a and 1973. The function that bridges the observable to the unobservable is hypothetical, and it can be empirical or theoretical. If empirical, it is bound to be unreliable because isolated from the rest. If theoretical, the indicator hypothesis is part of the theory of the measuring instrument, for instance, the theory of the galvanometer. But in either case the observable indicator fact, such as the deviation of a pointer, is likely to be qualitatively different from the indicated fact, such as the electric current. See Table 7.1. The third and final step in the testing process is to set up and read the pertinent observation and measuring instrument, scale, microscope, spectroscope, chromatograph, Geiger-Müller counter, posted prices, or what have you. The typical laboratory operation involves measuring instruments with pointers and dials. Such instruments translate unobservable facts, such as electric currents, into observable dial readings. They embody indicator hypotheses. This is when the experimenter starts looking, listening, touching, and perhaps even smelling and tasting, in order to obtain authentic observational data that could not possibly be derived from theory alone. In short, the actual procedure of theory testing is the sequence. Table 7.1 Sample of indicators. Indicated indicator. Gravity pendulum period. Temperature height of thermometric column. Current intensity deviation of ammeter pointer acidity pH brain activity glucose consumption thought linguistic expression hatred pupil contraction primate social ID grooming time welfare longevity height nutrition economic activity GDP income inequality Gini index political participation voter turnout. 184. 1. General theory and subsidiary hypotheses theoretical model. 2. Theoretical model and indicator, S. Testable prediction, S. 3. New empirical data obtained by observation or experiment. 4. Confrontation of predictions with empirical findings. 5. Evaluation of theoretical model. Figure 7.3 tells all of this graphically. Figure 7.3 M2 accounts of the theory-fact confrontation. A. Naive, direct comparison, B. Realistic, comparison via subsidiary hypotheses, indicator hypotheses, etc. Note that the naive account involves neither objective facts, nor models, nor indicator hypotheses. Theory O subsidiary hypothesis. Evidence O data O theoretical model. Indicator O prediction. O observable consequence. O new data. O observation. Asterisk objective fact. Naive view realistic view. 10. What can we learn from the discussions in this and the preceding chapter? The first thing we learn is that the very existence of the sadly neglected category of inverse problems raises some interesting logical, semantic, epistemological, 185, methodological, and ontological problems. Regrettably, the logic and semantics of problems has hardly attracted the attention of philosophers. See, however, Bunge 1967a and Rescher 2000. In particular, the questions of the order and equivalence of problems should be further clarified. For instance, which comes, logically, first, an algebraic equation or its roots? In scientific practice usually the equation comes first, since one starts by assuming that a given polynomial has zeros, and proceeds to finding them out. However, the fundamental theorem of algebra allows one to go either way. Hence, in this exceptional case the inverse problem is logically equivalent to the direct one. Moreover, the concept of problem duality, or complementarity, applies here better than the direct inverse couple. Hence the general problem: what is the difference between problem duality and problem inversion? And under what conditions is one of them reducible to the other? The epistemological problem is to clarify the relation between the direct inverse and the observable-unobservable distinctions. Finding the solution to a direct scientific or technological problem boils down to constructing a map from unobservables, such as forces or intentions, to data, such as positions or pieces of human behavior, and to solve the inverse problem is to find the inverse of this map. This inverse will exist only if the map in question is Oneto 1. However, this is not enough, since the empirical data are likely to have errors that may correspond to a large difference in the domain of the map. That is, a mere empirical error in the measurement of the effect might suggest the wrong cause. To prevent such instability, the unobservables-observables map must be continuous in addition to being one-to-one, example Newton 1989. Note how closely the mathematical discussion of the invertibility conditions fits the epistemological distinction, and how the innocent-looking observable-unobservable distinction can translate into fancy mathematics. The complications in question constitute a particular case of the so-called underdetermination of the theory by the data, which has puzzled inductivists for half a century. The same complications suggest why the Automated Discovery Systems project currently underway can yield at most rediscoveries. One of these is that of the quarks, first postulated in 1964, and rediscovered in 1990 by the Gell-Mann computer program when fed a large number of theoretical models, Giza 2002. No reason to crow, once one has found out that the criminal is hiding in the house, and has procured a detailed identikit of him, one is likely to recognize, him upon searching the house. The methodological problem is this: when dealing with entities on different levels of organization, which problem-solving strategy is more convenient, top-down, analysis, or bottom-up, synthesis? The answer is that ordinarily. 186. One starts from what one knows best. In other words, the explanandum explanans relation depends on the state of knowledge. Whereas in some cases the direct problem is of the macro-micro type, in others it is of the converse kind. These dual strategies can be summarized as in Figure 7.4, Bunge 1996, 145. The top-down and bottom-up strategies should eventually be combined. For example, if we wish to explain a known macrofact, we should attempt to reduce it to microfacts, whereas if microfacts are better known, then we should attempt to aggregate them into macrofacts. Thus, at the present time neurons are far better known than neuronal systems. Hence, theoretical cognitive neuroscientists will be well advised to imagine neuronal systems, circuits, or networks capable of performing certain mental functions known from psychology. However, their experimental colleagues will continue to observe and alter multineuronal systems to find out what mental functions, processes, they instantiate, carry out. Note that the direct/inverse distinction is not a dichotomy, because many problems are neither direct nor inverse. Among these we find the following: the problems of finding a new problem, of exactifying a course or intuitive notion, of interpreting in factual terms a mathematical concept or a symbol, and of evaluating an item in the light of certain desiderata and rules. Finally, our discussion of the confrontation of a scientific theory with the relevant empirical evidence has involved a brief examination of the indicator hypotheses embodied in the very construction and reading of measuring instruments. It is a sad comment on the state of the philosophy of science that such indicators are seldom if ever mentioned, let alone analyzed, in the philosophical literature, that most philosophers still believe that scientific theories imply observational data and that these are the direct product of perception. A. Macrofact explanandum macrofact explanans. Microreduction deduction macroreduction deduction. Microfact explanans microfact explanandum. Figure 7.4 M2 mutually dual and complementary research strategies when only two levels of organization, micro and macro, are involved, A. Top-down and, B. Bottom-up. A. B. 187. Mere look at a domestic electric meter should have sufficed to explode this myth. If art critics look at artworks, why cannot science critics look at real-life scientific projects instead of relying on second-hand reports? In sum, the old problem of the theory-fact relation still needs much investigating. To be successful, this research must start by recognizing that going from facts to theories is an inverse problem, and that theories are never confronted directly with the relevant observations. 188. 8. At first sight, materialists cannot countenance abstract objects, such as theories and myths, because these are immaterial, and realists could not admit them either because they are not out there. In fact, the medieval nominalists, who were at once materialists and realists, in the modern sense of this term, admitted only one kind of entity, the concrete individual, in addition to God and the angels. In particular, Buridan conflated propositions with sentences, and identified these with single utterances or inscriptions, believing that these are just physical objects, see Scott 1966. This is why the modern nominalists use the expressions sentential calculus instead of propositional calculus, and language instead of theory. One problem with such rechristening is that linguistic expressions, unlike mere physical entities, are supposed to convey meanings, which are obviously immaterial. A second problem is that sentences are studied by linguistics, which presupposes logic, an eminently non-physical science. As for the reduction of theory to language, it is impossible because theories have non-linguistic properties, such as consistency and explanatory power, just as texts have non-logical properties, such as persuasiveness and style. Besides, we need the concept of a proposition to explicate translation as a meaning-preserving linguistic transformation. Indeed, everyone uses tacitly the convention that two signs are mutually substitutable just in case they designate constructs with the same meaning. In other words, symbols are of course physical objects, but also more than this, since they represent other objects. And a construct cannot be identified with any of its symbols because, by definition, a symbol names something other than itself. Besides, the vast majority of objects must remain nameless. Think of continuous such as the set of real numbers and the set of points in a 189 region of space-time. The naming or symbolizing function maps designata or denotata into names or symbols, which constitute a denumerable set. Besides, sentences have structures, such as the SVO word order, which are abstract, and they convey meanings, which are likewise transcendental items. Indeed, Symbols and other semiotic objects differ from physical objects in that they come together with explicit or tacit conventional codes or interpretation rules that assign them meanings. This is why we do not discover the signification of a term such as Ignis by examining any of the ways in which it can be inscribed or uttered, but by consulting a Latin lexicon. And that is also why computers, which process symbols but not their designata or denotata, cannot grasp meanings, let alone create them. See, example Searle 1980 and Bunge 2003a. So, what are materialists and realists, and a fortiori hylorealists, to do about abstract objects, in particular concepts and propositions? Some nominalists, such as Quine, have held that there are signs but not concepts, sentences but not propositions, and behavioral reactions to verbal stimuli rather than meanings. However, this doctrine fails to account for the elementary fact that the two sentences I love you and jet aim are equivalent because they designate the same proposition. In other words, a translation is faithful if and only if it preserves meaning. So, meaning is basically a property of constructs, and only derivatively a property of the signs that designate concepts or propositions, in which case it had better be called signification. Bunge 1974a, 1974b, 1975. In short, there are concepts, propositions, and systems of such, though of course as abstract objects, not physical ones. The nominalist fears that talk of concepts, propositions, and other abstract objects implies a concession to idealism. The goal of this chapter is to allay this fear, showing that there is nothing wrong with admitting abstract objects as long as they are not assigned independent existence. But before doing this, let us see why we need abstract objects. 1. The need for abstraction. In the preceding chapters we have argued for scientific realism, or the thesis that there is a real outer world, and that it can be known, particularly through scientific research. However, the scientific models of concrete things are symbolic rather than iconic, they are systems of propositions, not pictures. Besides, such models are seldom if ever completely accurate, if only because they involve more or less brutal simplifications, such as pretending that a metallic surface is smooth, a crystal has no impurities, a biopopulation has a single predator, or a market is in equilibrium. These are all fictions. However, 190. They are stylizations rather than wild fantasies. Hence, introducing and using them to account for real existence does not commit us to fictionism, just as defending the role of experience need not make us empiricists, nor is admitting the role of intuition enough to qualify as intuitionist. In other words, in science and technology we often use as ifs. That is, we feign that something has a certain property even knowing that it lacks it. When pretending something of the sort we do not lie, and we do not assume that the real nature of the item in question is unknowable. We just make a simplifying assumption, knowing full well that further research or action may disclose previously overlooked factors, and thus force us to adopt a more complicated assumption. For instance, we may conceptualize the surface of a solid body as perfectly smooth, but are ready to concede that actually it is ragged and porous. That is, we do not condone fictionism or instrumentalism, the common ground of conventionalism and pragmatism, according to which all scientific constructs are only fictions allowing us to correlate and organize experiences. The scientific realist merely admits tacitly that neither the knowledge nor the efficient management of a concrete item is likely to be instantaneous. The same holds, with all the more reason, for the worlds of mathematics, such as set theory, Boolean algebra, and the theory of differential equations. Indeed, these objects are not out there, ready to be picked up like pebbles, they are made, not found. That is, they are artificial, not natural. Moreover, the mathematical objects are imperceptible and they satisfy purely formal laws, not laws of nature or social norms. For example, it is a theorem in number theory, not a physical or an economic statement, that there is no greatest number. In other words, the statements in pure mathematics are not ontologically objective, they do not refer to the real world. But of course they are not subjective either, they do not report on the speaker's state of mind. Thus, they are neither objective nor subjective in an ontological sense, even though they are impersonal and asocial. The same holds for myths, stories, and the like. All such statements are fictions. That is, for the sake of analysis we may feign that there referents, sets, ghosts, gods, or what have you, exist independently of the subject. But no sane person will mount an expedition to search for them in the wilderness. Still, no realistic person can deny the power of some fictions, such as those of mathematics in exactifying and unifying ideas, and those of ideology in mobilizing or freezing people. Do you remember the myth of the Iraqi weapons of mass destruction made up by the Bush administration in 2001? Plato and Nietzsche might have approved of this noble lie invented to lead millions of politically naive people by the nose. At first sight, the admission of fictions constitutes a serious blow to science. 191. Scientific realism, since fictions, considered in themselves, that is, regardless of the way they are constructed and used, are neither things in the outer world nor brain processes. Is this true? Whichever the answer, we must face this practical question: which of the various philosophies of mathematics accords best with the thesis that mathematical objects are fictions, without compromising the thesis that only concrete, material, objects are real, or the freedom so dear to creative mathematicians? These questions challenge us to sketch a philosophy of mathematics to supplement our realist philosophy of science and technology. See details in Bunge 1985b. 2. Fictionism. If mathematical objects are not real in the same way as stars and birds and schools, then scientific realism does not apply to them, and therefore it cannot help us understand their nature. Could idealism help? Let us see. Platonism, the paragon of objective idealism, claims that ideas are just as real as stars and birds and schools, and actually even more real than the latter. The trouble is that there is no evidence for this conjecture. Nor can the Platonist offer any such evidence, since there are no mathematical quarries or warehouses, all of the mathematical objects are made up. This explains why mathematical discoveries are not made in the field or in the lab. It also contributes to explaining why mathematics, like literature and the law, is only a few millennia old. Still, there is no doubt that mathematical objects are ideas rather than real entities. Could they be fictions, just like Aesop's stories? Let us see. The thesis that mathematical objects, and perhaps other ideas as well, are fictions, is called fictionism. But of course fictionism, like all the other philosophical isms, comes in two main strengths, radical and moderate. Radical fictionism, or fictionalism, is the doctrine that all discourse is fictive, so that there is no truth of any kind, mathematical, factual, or other. According to it, the most we can assert is that our ideas work as if they were true. It is thus a combination of conventionalism with pragmatism. Like other epistemological doctrines, fictionism has ancient roots. One of these is ancient radical scepticism, or Pyrrhonism, nothing can be known with certainty. Another is medieval nominalism, a variety of vulgar materialism, there are no concepts, there are only things and their names. However, fictionism only flowered in Weyenger's monumental book Die Philosophie des Philosophes of 1911, which owed much to Hume, Kant, Lang, and Nietzsche. In fact, Weyenger is usually regarded as a neo-Kantian. Fictionism has had few orthodox adherents, but it has left some vestiges in the literature, though seldom under the same name. One of those vestiges is 192. Found in Milton Friedman, 1953, the famous monetarist and apologist of unregulated capitalism. He held that the assumptions of an economic theory need not be true, all that should concern us is whether their consequences match the relevant facts. But of course one may deduce true propositions from false ones, in particular contradictions. Indeed, a contradiction entails any number of propositions. Besides, the point of checking for the truth of a logical consequence is to evaluate the truth claims of its premises. Another vestige of fictionism is the view that theories and historical accounts are metaphors rather than representations of real facts, example Hesse 1966, Ricoeur 1975, Hayden White 1978, McCloskey 1985. This opinion is quite popular in the postmodern crowd. An even more popular variety of fictionism is constructivism relativism, according to which science is a form of fiction or discourse like any other, one effect of which is the truth effect, which, like all literary effects, arises from textual characteristics, Latour and Woolger 1986, 184. If truth were just a literary effect, it would hardly matter whether fictionism is true or false. But it does matter everywhere, particularly in science and technology, and this for the following reason. If fictionism were true, there would be no point in checking scientific theories and historical narratives for truth. Nor would it be possible to design empirical tests and artifacts with the help of scientific theories, unless these were at least approximately true. All laboratories, museums, archaeological sites, and the like could be closed down to the applause of all obscurantists. In sum, fictionism is false with regard to factual science. Still, I submit that fictionism, while utterly false regarding factual science, is quite true concerning pure mathematics. In other words, I submit that the mathematical objects, such as numbers, figures, sets, functions, categories, groups, lattices, Boolean algebras, topological spaces, vector spaces, differential equations, manifolds, and functional spaces, are not only encherationes, they are ficta. Consequently, the concept of existence occurring in mathematical existence theorems is radically different from that of real or material existence. We shall come back to this subject in section 4. This is why mathematical existence proofs, and all other mathematical proofs as well, are purely conceptual procedures. In short, mathematicians, like abstract painters, writers of fantastic literature, abstract, or rather uniconic, painters, and creators of animated cartoons, deal in fictions. To put it into blasphemous terms, ontologically, Donald Duck is the equal of the most sophisticated nonlinear differential equation, for both exist exclusively in some minds. This, in a nutshell, is the kind of mathematical fictionism to be sketched and argued for in the balance of this chapter. 193. As will be seen below, our fictionism, unlike Weyenger's, is of the moderate rather than the radical kind. This is so because, a. It does not embrace factual science, and, b. It regards mathematics as a science, not as a game, let alone an arbitrary fantasy. Indeed, it distinguishes between mathematical fictions on the one hand and myths, fairy tales, theological speculations, abstract paintings, parapsychological and psychoanalytic fantasies, as well as many worlds philosophical theories, on the other. 4 kinds of truth. I follow Leibniz, 1703, 394, in distinguishing propositions de raison, such as 2 + 2 = 4, from propositions de fait, such as fire burns. The former refer exclusively to encherationes, and they can be proved or falsified by purely conceptual means, namely, argument, deduction and criticism, or counter-example. By contrast, the propositions de fait refer at least partly to putatively real, concrete, entities. Consequently, if testable at all, they are checked for either truth or efficiency with the help of direct or indirect empirical operations, such as observation, counting, measurement, experiment, or mere practical trial. The formal/factual distinction calls for distinguishing formal from factual truths or falsities, Grassmann 1844, Einleitung. In particular, we distinguish mathematical theorems, on the one hand, and scientific, example biological, or technological data and hypotheses, on the other. The difference between the two kinds of truth is so pronounced that a factual theory, such as classical electrodynamics, contains some mathematically true formulas, such as those for advanced potentials, that fail to match the facts, that is, that are factually false. A simpler example is the equation PQ equals constant, which relates prices to quantities. The branch for negative values of P and Q is excluded for being economically meaningless. Besides, most mathematical theorems are yet to be employed in factual science or in technology. One have just smuggled in the distinction between formal and factual sciences. We define a formal science as an exact science that contains exclusively formal propositions, or propositions de raison. On the other hand, at least some of the propositions of a factual science must be factual. They must describe, explain, or predict things or processes belonging to the real, natural or social, world. Logic, philosophical semantics, and mathematics are formal sciences. By contrast, the natural, social, and biosocial sciences are factual. So are all the technologies, from engineering and nursing to management science and the law. The formal/factual distinction leaves out all the propositions and fields that 194 are neither formal nor factual, hence, it is not a dichotomy. Among them the artistic fictions stand out. When reading about Don Quixote's misadventures, we may feign, and may actually feel, that he exists along with the figments of his own sick imagination. And when attending a performance of Othello we may believe for a moment that in fact the Moor kills Desdemona. However, when reflecting critically upon these and other works of fiction, we do not mistake them for factual accounts, unless of course we happen to be mad. We group them together under artistic fiction. Moreover, occasionally we are justified in talking about artistic truth and falsity, as when we say that Don Quixote was generous and Othello's suspicion false. In order to establish the artistic truth or falsity of an artistic fiction we only need resort to the work of art in question. That is, artistic truth, like mathematical truth, is internal and therefore context dependent. In other words, it only holds in some context and it need bear no relation to the external world. To an atheist, the so-called religious truths are parallel, they only hold in Holy Writ. That is, they call for a deliberate attitude of assent in the absence of any clear independent evidence. Thus, the statement that Christ was human is blasphemy in some theologies and dogma in others. The only evidence accepted by the religious believers is a set of reputedly sacred texts. No data or theories coming from science or technology are regarded as pertinent to religious dogma. In other words, a religion together with its theology is a closed system, unlike a science, which overlaps partially with other sciences as well as with mathematics and philosophy. Allow me to repeat a platitude: mathematical truth is essentially relative or context dependent. For example, the Pythagorean theorem holds for plane triangles but not for spherical ones, and not all algebras are commutative or even associative. On the other hand, factual statements such as there are photons and breathing fresh air is healthy are absolute or context-free. By contrast, social norms are context-dependent because they are social constructions. Finally, let us admit that the problem of truth, though central in factual science and philosophy, is peripheral in mathematics. As MacLean, 1986, writes, it is not appropriate to ask of a piece of mathematics whether it is true. The appropriate questions are whether a piece of mathematics is correct, responsive, that is, solves a problem or carries further some line of research, illuminating, promising, or relevant, to science or to some human activities. In sum, we distinguish between formal, factual, and artistic truths and falsities. We may even add moral truths, such as racial discrimination is unfair and poverty is morally degrading, but these are irrelevant to our present subject, see Chapter 10, Sections 6 and 7. Moreover, from the above 195 discussion it is clear that, in our view, mathematics is closer to art than to science as regards its objects and its relation to the real world, as well as regards the role of truth. However, as will be argued in section 7, there are important methodological differences between mathematics and art. For mathematics is ontologically neutral. To say that logic and mathematics are formal sciences is to say, to borrow Quine's idiom, though contrary to his claim, that they have no ontological commitment, that is, that they do not assume the existence of any real entities. In other words, logic and mathematics, and a fortiori metalogic and metamathematics, are not about concrete things but about constructs, predicates, propositions, and theories. For example, predicate logic is about predicates and propositions, category theory is about abstract mathematical systems, set theory is about sets, number theory is about integers, trigonometry is about triangles, analysis is about functions, topology and geometry are about spaces, and so on. Warning: Quine and others misuse the word ontology when they equate it to the universe of discourse, or the reference class of a construct. An ontology is not a set of items but a theory about the world. The thesis that mathematics is about mathematical objects seems self-evident, yet it may not be proved in a general way. What we can do is to support it in two ways, by methodological and semantic considerations. The former is in two stages. A first step consists in recalling that all known mathematical objects are defined, explicitly or implicitly, in purely conceptual ways, without resorting to any factual or empirical means, except occasionally as heuristic devices. The second step consists in recalling that mathematical proofs, and refutations, too, are strictly conceptual processes making no reference to empirical data. In this regard, computer-assisted proofs are no different from pencil-assisted ones. As for the semantic consideration, it consists in identifying the referents of mathematical constructs, that is, in finding out what they are about. For example, set theory is about nondescript sets, whereas number theory refers to whole numbers. This task requires a theory of reference, as distinct from a theory of extensions. Unlike the latter, the former makes no use of any truth concept. For example, the predicate even and not even refers to integers while its extension is empty, for it is not true of any number. To prove the above assertions, I shall presently sketch my own axiomatic theory of reference, which is couched in elementary set theoretic terms, Bunge 1974a. Let us begin by analyzing the general concept of a predicate, such as the one occurring in the proposition America is populated, or PA for short. 196. Submit that P is to be construed as the function that pairs the individual A to the proposition PA. This construal differs from Freya's, of a predicate as a function from individuals to truth values. I find this absurd because it yields the result that predicating property P about an object A yields not the proposition PA, but its truth value. In other words, unlike Freya and his followers, I define a predicate P as a function from individuals, or n tuples of individuals, to the set S of statements containing the predicate in question. In standard symbols, an n-ary predicate P is to be analyzed as a function P, A1 times A2 times an S, with domain equal to the Cartesian product of the n sets AI of individuals concerned, such that the value of P at in that domain is the atomic statement PA1 A2, and in S. For example, the unary predicate is prime is a function from the natural numbers to the set of propositions containing is prime, that is, P, n S. And the binary predicate is greater than, when defined in the same numerical set, is analyzable as n times nt, where T is the set of propositions involving dot. I next define two reference functions, Rp and Rs, the first for predicates and the second for statements, through one postulate each. Axiom 1: the reference class of an n-ary predicate P equals the union of the sets occurring in the domain A1 times A2 times n of P, that is, Rp, P, equals AI. Axiom 2: A, the referents of an atomic proposition are the arguments of the predicate, S, occurring in the proposition. That is, for every atomic formula Pa1 A2, and in the set S of statements, Rs, Pa1 A2, and, equals A1, A2, and b. The reference class of an arbitrary propositional compound, such as a negation, a disjunction, or an implication, equals the union of the reference classes of its components. Corollary, a proposition and its negation have the same reference. By the way, the insensitivity of reference to the differences among the logical connectives is one of the differences between reference and extension, two concepts that are usually conflated in the philosophical literature. C. The reference class of a quantified formula, that is, one with the prefix some or all, equals the union of the reference classes of the predicates occurring in the formula. With the help of this theory, one can identify the reference of any construct, predicate, proposition, or theory. For example, since the logical operations, such as conjunction, and relations, such as that of entailment, relate predicates and propositions, they are about them and nothing else. The formal proof for disjunction goes like this: disjunction can be analyzed as a function from 197 pairs of propositions to propositions, that is, W, S times SS. Now, by axiom 1 above, RP, W, equals SS equals S. That is, disjunction refers to arbitrary propositions, formal, factual, moral, artistic, religious, or what have you. In general, logic refers to arbitrary predicates and their combinations, namely, propositions, classifications, and theories. Obviously, our theory of reference is about arbitrary predicates and propositions. It is then a formal theory just like logic. The same applies to our theories of sense and meaning and, indeed, to our entire philosophical semantics, Bunge 1974a. Of course, no theory of reference can prove that every single mathematical formula refers exclusively to constructs. But ours serves to test any particular claim concerning the reference class of any well-defined predicate. Such test is necessary not only to prove that mathematics is not about the world, it is also crucial in the factual sciences, when their objects or referents are the subject of spirited controversies, such as those elicited by relativistic and quantum mechanics, evolutionary biology, and microeconomics. True, Quine, 1969, claimed that reference is inscrutable. Donald Davidson, 1984, concurred, and added that no theory of reference is needed. But this only shows that their negative semantics cannot be used to find out, say, what the function in quantum mechanics refers to, or whether things, when used in cognitive psychology, refers to brains, souls, or computers. What about the well-known thesis that existence is what existential quantification expresses, Quine 1969, 97. This claim is false, as one realizes upon recalling that, unless the context is indicated, the expressions of the forms xpx and x equals a are ambiguous, since they do not tell us whether the x's in question are real or imaginary, that is, whether we are talking about real or ideal existence. Worse, as Lotson, 2001, 123, notes, Quine's view implies that abstract objects are real, which contradicts the standard conception of abstraction as irreality, and thus the opposite of concreteness. To avoid such confusions and contradictions, the ill-named existential quantifier should always be completed by indicating the set over which the bound variable in question ranges. The once standard notation x dpx, where d names the universe of discourse, will do. The bounded existential quantifier can be defined thus: x dpx equals df x xd and px, dot. A modicum of conceptual analysis, used to clarify the ambiguity of the word existence, would have spared us Quine's influential but false thesis of the ontological commitment of the existential quantifier, hence of logic and everything built upon the latter. For the same reason, Such analysis would have spared us Manin's paradox: there are objects of which it is true that there are no such objects. Manin 1960, 83. Much the same holds for the egregious claim that there are more things than actually exist. Lewis 2001. 198. 86. The same is true of the attempt to revive the nominalist thesis, that there are no mathematical entities. Field 1980. All this imprecision and extravagance would have been avoided upon distinguishing explicitly the two kinds of existence, conceptual and real. An appropriate analysis would also have shown that, outside mathematics, the proper interpretation of that quantifier is not existence but someness. More precisely, in pure mathematics, x, px can be read either as some individuals are p's or as there are ps, with the understanding that such individuals are conceptual, that is, they exist in some mathematical universe. But outside mathematics it is best to avoid the ambiguity, and read, x, px as some individuals are ps. In other words, only in mathematics there are amounts in practice to some. In alternative contexts, for instance, in physics and in ontology, when speaking of existence we may have to make two distinct statements, one of real existence, or inexistence, and the other of someness. See Bunge 1977a, 155-6 for a formalization of the existence predicate and its combination with the someness quantifier. Such combination allows one to construct well-formed sentences such as some of the particles imagined by theoretical physicists exist, really, which cannot be constructed with the sole help of in self-explanatory symbols, x, px and erx. In conclusion, pure mathematics, in particular logic, is ontologically neutral, more in Bunge 1974c. Moreover, it is a gigantic, though not arbitrary, fiction. This explains why pure mathematics, including logic, is the universal language of science, technology, and even philosophy, and why it is the most portable and serviceable of all sciences. Take note, science policy makers and bureaucrats reluctant to fund pure mathematical research. It also explains why the validity or invalidity of mathematical ideas is independent of material circumstances such as the state of the brain and the state of the nation. However, this subject deserves a new section. 5. Mathematics, brains, and society. How does mathematical fictionism differ from Platonism? The difference is that the Platonic philosophy of mathematics is part and parcel of objective idealist metaphysics, which postulates the reality of ideas in themselves, that is, the autonomous existence of ideas outside of brains, and even their ontological priority and primacy. By contrast, mathematical fictionism is not included in any ontology, because it does not regard mathematical objects as real but as fictions. 199. When introducing or developing an original mathematical idea, the mathematician creates something that did not exist before. And, as long as he keeps the idea to himself, it remains locked in his brain, for, as a cognitive neuroscientist would say, an idea is a process occurring in someone's brain. However, the mathematician does not assign his idea any neurophysiological properties. He pretends that the idea in question has only formal properties, for example, that the theorem he has just proved holds even while he is asleep and that, if made known to others, it will continue to hold long after he is gone. This is of course a fiction, since only wakeful brains can do, correct, mathematics. But it is a necessary fiction because, although proving is a neurophysiological process, a proof in itself, regarded as an abstract metamathematical object, does not contain any neurophysiological data or assumptions. In short, even though theorems are human creations, we may pretend that their form, meaning, and validity are independent of any human circumstances. We are justified in adopting this fiction because mathematical ideas are not about the real world. Every mathematical idea refers to some other mathematical idea. Mathematics, including logic, is the self-reliant science, even though some mathematicians, such as Archimedes, Newton, Euler, Fourier, von Neumann, Wiener, and Turing were occasionally motivated by problems in physics or in engineering. What holds for brains also holds, mutatis mutandis, for societies. While it is undeniable that there is no, sustained, mathematical activity in a social vacuum, but only in a community, it is equally true that pure mathematics has no social content. If it did have any, then mathematical theories would include social science predicates such as commodity, competition, social cohesiveness, crime, and political conflict. Furthermore, they would double as social science theories, perhaps to the point of rendering the latter redundant. Our thesis of the factual, in particular social, neutrality of mathematics is at odds with Quine's semantic and epistemological holism, itself an echo of Hegel's dictum das Wahr ist das Ganz, truth is in the whole. It is certainly true that mathematics permeates, at least potentially, all of human knowledge, which in turn is a system rather than a mere set. However, one can spot the formal components in every discipline, and treat them separately. This is why mathematicians without any specialized extra mathematical expertise are often consulted by workers in the most varied disciplines. The neutrality view is also at variance with the fashionable social constructivist relativist sociology of science, Bloor 1976, Restivo 1992, Collins 1998. This school contends that mathematics is through and through social. This would be so not just because all mathematical research is conducted in a 200 scholarly community, and because the mathematical formulas are communicable, but also because all of the mathematical formulas would have a social content. Needless to say, no evidence has ever been proffered for this thesis, it is just an opinion. However, we can check it in every particular case with the help of the theory of reference sketched in section 3. Take, for instance, the two formulas that define, implicitly, the factorial function, namely, 0 equals 1 and n plus 1 equals n plus 1, n. Obviously they refer to natural numbers, there is no trace in them of the social circumstances surrounding their origin. The formulas in question belong in combinatorics, the discipline that studies the permutations and combinations of objects of any kind. Likewise, Thales' theorem is about plain Euclidean triangles, not about ancient Greece. And the Taylor series concerns functions, not the events that occurred the year that Brooke Taylor published it, among them the death of Louis XIV and the expulsion of the Venetians from the Peloponnese. Because the above mathematical formulas are correct, and neither of them describes any social circumstances, they will hold for as long as there remain people interested in mathematics. For criticisms of the social constructivist relativist sociology of knowledge, see Budden and Klaeblen, eds 1994, Bunge 1999 and 2000b, and Brown 2001. 6. How to make ontological commitments. Pure mathematics, then, is not about concrete or material things such as brains or societies, although mathematical objects can only be invented by living brains under favorable social circumstances. Mathematics is exclusively about conceptual or ideal objects. One may prefer to say, as Plato first realized, that mathematics is about changeless or timeless objects, not about events or processes. The ontological neutrality of mathematics explains why this discipline is the universal language of science, technology, and even philosophy, that is, why it is portable from one intellectual field to the next. Yet when looking at any work in theoretical physics, chemistry, biology, or social science, a mathematician may be tempted to regard it as a piece of mathematics. There is a grain of truth in this belief. After all, rate equations, equations of motion, field equations, and more are mathematical formulas, and they are solved using mathematical techniques such as those of separation of variables, series expansion, and numerical integration. This is why Pierre Duhem, a conventionalist, famously claimed that classical electromagnetism is identical with Maxwell's equations. It is the same reason that many mathematicians used to hold that rational mechanics is part of mathematics, and Gerard Debreu that his theory of general equilibrium is a chapter of mathematics. 201. However, this is only a partial truth, as can be seen in the case of any formula in elementary logic. Thus, the formula for all x, if px, then, if qx, then rx, does not state anything about the real world or even about mathematical objects. It is an empty shell. In order to say something definite, true, false, or half-true, the formula must be interpreted. A possible interpretation is this: int p equals is human, int q equals thinks, int r equals is alive. These semantic assumptions turn the above formula into any human who thinks is alive, a mere generalization of Descartes' famous cogito, ergo sum. Any change in the interpretation yields a formula with a different content. Thus, we confirm a conclusion drawn in section 4, that Quine, 1953, 12, was mistaken in stating that the only way we can involve ourselves in ontological commitment is by our use of bound values, i.e., quantification. Actually, the only way to make an ontological commitment is to state a factual interpretation of the signs, words or symbols, in question. This obvious semantic thesis applies to all of mathematics. Indeed, a mathematical formula does not become part of a factual science unless enriched with a factual content. Such enrichment is achieved by pairing the formula to one or more semantic assumptions, or correspondence rules, as they used to be called. Such assumptions state that the formula refers to such and such concrete things, and that at least some of the symbols occurring in it denote certain properties of such things. For example, the equation d2x/dt2 plus x equals 0 is the equation of motion of a linear oscillator in classical mechanics, provided x is interpreted as the instantaneous value of the elongation, t as time, and as the ratio of the elastic constant to the mass of the oscillator. The concepts of linear oscillator, elongation, elastic constant, mass, and time, which confer a physical interpretation upon the mathematical symbols, are extra-mathematical. In other words, to bridge mathematics to the real world we must enrich it with semantic assumptions, or correspondence rules. Thus, the factual counterpart of a predicate is a property, that of cardinality is numerosity, that of continuity is smoothness, that of gradient is slope, and that of Laplacian is the slope of a slope. But of course there are plenty of mathematical constructs without factual counterparts. Just think of negation, contradiction, tautology, entailment, zero, and. In sum, mathematics does not suffice to describe or explain the real world. But of course it is necessary to account for it in a precise and deep manner. Indeed, mathematics supplies one of the two components of any theory in advanced theoretical factual science or technology, namely, the mathematical formalism. The other component is the set of semantic assumptions, or correspondence rules, that flesh out the mathematical skeleton. More precisely, a mathematical theory or model of a domain of factual items. 202. Is a triple domain formalism interpretation, or M equals for short. Here D denotes the factual domain or reference class, F the union of some fragments of theories in pure mathematics, and int is a partial function from the formalism F to the power set of D that assigns some of the predicates and formulas in F to sets of factual items in D. Int is a partial function because not every item in F need be interpreted in terms of facts. One and the same formalism F may be paired off to any number of different factual domains. Think, for example, of the multiple uses of linear algebra and the infinitesimal calculus. A mathematician can check the formal correctness of F, but only empirical tests can tell whether any given theoretical model M matches the domain D, that is factually true. In other words, the mathematical truth of the theorems in F does not guarantee the factual truth of M. On the other hand, any important mathematical flaw guarantees factual falsity. And yet it is easy to fall into verbal traps, taking literally such expressions as dynamic logic and dynamical systems theory, which suggest to the unwary that certain mathematical theories deal with time and change after all, whence they are worth being studied and supported by the taxpayer. In fact, those theories are just as timeless as number theory and geometry. What happens is that, when applied, some of the concepts occurring in them get interpreted in factual terms. For instance, the independent variable is routinely interpreted as time, an eminently non-mathematical concept. This is how dynamic logic is applicable to computer programs, and dynamical systems theory is applicable to the analysis or design of concrete systems of many kinds, even though it is often but an excuse for studying systems of ordinary differential equations. Likewise, elementary logic can be applied to analyzing reasoning processes such as the arguments we construct in real life, by assuming that the steps in a logical sequence match the temporal sequence of our real thoughts. In sum, mathematics supplies ready-made formal and timeless skeletons, some of which scientists and technologists see fit to flesh out, interpret, in alternative ways in order to map concrete changing things. To change the metaphor, from a purely utilitarian viewpoint, mathematics is a huge warehouse of ready-to-wear clothes that scientists, technologists, and humanists can help themselves to. When none of the existing clothes fits, the user has got to do the tailoring himself, thus becoming a mathematician for a while. Ptolemy, Newton, and Euler come to mind. So do Einstein, Heisenberg, and Dirac, though only up to a point, because Einstein reinvented Riemannian geometry, Heisenberg reinvented matrix algebra, and Dirac's famous, or infamous, delta motivated the creation of the mathematical theory of distributions. 203. 7. Responding to some objections. Let us now address some of the possible objections to mathematical fictionism. One of them is that mathematicians do not invent but discover, or at least this is what they ordinarily say. Some of them may do this out of humility, others for being either Platonists or empiricists. In any event, if that were correct, either Platonism or empiricism would be true, and hence fictionism false. I share the commonsensical view that there are mathematical inventions as well as discoveries. That is, the original mathematician sometimes posits and at other times finds. He posits definitions, assumptions, in particular axiomatic definitions, and generalizations, and he discovers logical relations between previously introduced constructs. In particular, mathematical entities, such as categories, algebras, number systems, manifolds, and functional spaces, are invented. There are no mathematical quarries where one can find them ready-made. Even theorems are ordinarily first conjectured, then proved, or disproved, sometimes much later and by other people. But the proof process consists in discovering that the new theorem follows from previously known assumptions, axioms, lemmas, or definitions. However, sometimes such discovery necessitates inventing further items, such as the auxiliary constructions of elementary geometry. For example, using a convergence test one discovers that a certain infinite series is divergent. But all convergence tests have been invented, not discovered. Likewise, by expanding a function in series, and integrating term by term, one may compute the integral of the function, provided the series converges uniformly. But the given function, the concepts of integral, and much more had to be invented before they could be handled. The general rule is, first invent, then discover. And if the discovery is negative, for instance, that a bunch of assumptions is inconsistent, that they do not entail an alleged theorem, or that a series is divergent, then alter some of the assumptions, that is, revise the invention process. Since in mathematics there is invention as well as discovery, Platonism is false. But evidence for mathematical invention is not enough to substantiate fictionism. Yet we only need to recall that we handle an infinite totality, such as a line or a hypothetico-deductive system, as if it were an individual, and as if it were there all in one piece, without of course saying where there is. Obviously, mathematicians are in space-time, but they assume that their own creations are out of space-time. A second possible objection goes as follows: if mathematics is a work of fiction, why don't librarians group mathematical works together with novels? 204. And, in particular, with fantastic literature? In other words, what if any are the differences between mathematical fictions and artistic ones? For example, how does the fundamental theorem of algebra differ from the claim that Superman can fly or Mickey Mouse can speak? Because mathematical fictions are unlike all others, they are strictly disciplined, and they can be used to think about any epistemic subject. More precisely, I submit that the crucial differences between mathematical fictions and all others are the following, adapted from Bunge 1985a, 39-40. 1. Far from being totally free inventions, mathematical objects are constrained by laws, axioms, definitions, theorems. Consequently, they cannot behave out of character. For example, there can be no such thing as a triangular circle, whereas even raving mad Don Quixote is occasionally lucid. 2. Mathematical objects exist, ideally, either by postulate or by proof, never by arbitrary fiat. 3. Mathematical objects are either theories or referents of theories, whether in the making or full-fledged, whereas myths, fables, stories, poems, sonatas, paintings, cartoons, and films are non-theoretical. 4. Mathematical objects and theories are fully rational, not intuitive, let alone irrational, even though there is such a thing as mathematical intuition. 5. All mathematical statements must be justified in a rational manner, either by their premises or by their fruits, not by intuition, revelation, or experience. 6. Far from being dogmas, mathematical theories are based on hypotheses that must be repaired or given up if shown to lead to contradiction, triviality, or redundancy. 7. There are no strays in mathematics, every formula belongs to some system, theory, and in turn theories are linked together forming supersystems, or else they are shown to be alternative models of one and the same abstract theory. Thus, logic employs algebraic methods, and number theory resorts to analysis. On the other hand, artistic or mythological fictions are self-sufficient, they need not belong to any coherent system. 8. Mathematics is neither subjective like art nor objective like factual science. It is ontologically non-committal, but the process of mathematical invention is subjective, and that of proof, or disproof, is intersubjective. What is real, concrete, about mathematics is that it is produced by living mathematicians embedded in mathematical communities. 9. Some mathematical objects and theories find application in science, technology, and the humanities. 205. 10. Mathematical objects and theories, though produced and consumed in society, are socially neutral, whereas myth and art are sometimes used either to support or to undermine the powers that be. 11. Because it deals in timeless objects, correct mathematics does not age, even though some of it may go out of fashion. 12. Mathematics is a science. That is, its practitioners employ the scientific method, background knowledge solution candidate checking re-evaluation of either problem or background knowledge. A practical upshot of the preceding is that librarians have good reasons for placing mathematical fiction and literary fiction in different sections. After all and above all, mathematics is a science, nay, the old queen of the sciences. A third possible objection to fictionism is this: if mathematics is made up exclusively of fictitious and timeless objects, how can it represent real things and processes? The answer lies of course in the concept of symbolic representation. Even ordinary language allows us to form sentences designating propositions that may represent ordinary things and processes, even though such sentences do not resemble their denotata, as in the case of books and the word books. The semantic relations involved are those of designation, d, and reference, r. The key to the reference component of meaning is of course a system of linguistic, in particular semantic, conventions, mostly tacit. In the case of scientific theories, the semantic components are not conventional and therefore irrefutable and changeable at will. Instead, they are hypothetical. This is why the name semantic assumption is more adequate than the traditional correspondence rule. Thus, the semantic assumption in Einstein's theory of gravitation, that the value of the metric tensor at a given point in spacetime represents the intensity of the gravitational field at that point, is not a convention, or even a rule. It is a hypothesis that can be put to the experimental test, and, moreover, one that makes no sense in action at a distance theories of gravitation. However, the matter of convention deserves a separate section. 8. Conventionalism and physicalism. Fully fledged fictionism is conventionalist. It holds that all assumptions are conventions, and none are true. By contrast, the moderate fictionism I am advocating is not conventionalist, because it retains the concepts of formal sentences, factual propositions, facts. Dr. 206. Truth, as well as the distinction between assumption and convention, in particular definition, which conventionalism rejects. Mathematicians use the concept of mathematical truth when claiming that a certain formula, other than an axiom, is true either because it is satisfied in some model, or example, or because it follows validly from some set of assumptions in accordance with the inference rules of the underlying logic. Likewise, we use its dual, namely, the concept of mathematical falsity, when disproving a conjecture by exhibiting a counterexample. In other words, ordinarily theoremhood equals either satisfiability or provability, neither of which is conventional. The adverb ordinarily is intended to remind ourselves of Gödel's proof that a formal axiomatic theory may contain formulas that cannot be proved with the sole resources of the theory in question. The dual of the concept of truth, namely, that of falsity, is equally important in mathematics. It occurs whenever a mathematical idea is criticized as flawed for some reason, and it is central in approximation theory and numerical analysis. Think of approximating an infinite convergent series by the sum of its first few terms. In particular, one can make true statements about quantitative errors, for instance, that they are bounded, or that they fit some distribution. Conventionalists have no more use for the concept of error than for that of truth. What about the axioms of a mathematical theory? Can one say that they are true? One might be tempted to claim that they are true by convention. But this expression strikes me as an oxymoron because conventions, such as definitions, are checked for well-formedness and convenience, not truth. In any event, there is no need to assign truth values to the axioms of a mathematical theory. By contrast, we need to know whether the axioms of a factual theory are true or false to some extent. In practice, the most important piece of knowledge about a postulate system is that it entails the standard theorems and, preferably, some new and interesting ones as well. To be sure, it would also be important to be able to prove the consistency of the system. But here again Gödel has taught us some humility. As noted above, a second difference between moderate mathematical fictionism and conventionalism is that the former keeps the difference between assumption and definition, whereas conventionalism holds, in Poincaré's famous thesis, that axioms are disguised definitions. The falsity of this view is best seen in the light of the theory of definition and, in particular, in the light of Peano's thesis that definitions are identities, which most mathematical assumptions are not. Indeed, an axiom may be an equality, such as a differential equation, but not an identity, such as 1 equals the successor of 0. Identities are symmetrical, whereas equalities are not. This difference is sometimes indi. 207. Kate by the symbols equals, identity, and colon equals, equality, respectively. Examples. For any real number x, x plus 1, x, 1, equals x2, 1, and for some complex number, s, x, x2 plus bx plus c equals 0 respectively. A particularly shallow version of mathematical conventionalism is Carnap's view that mathematical statements are empty linguistic conventions. Actually, the only conventions of this kind that occur in mathematical texts are the notational conventions, such as let n designate an arbitrary natural number. The well-formed mathematical statements are at once meaningful and testable. Indeed, they refer to definite mathematical objects, such as numbers, figures, functions, spaces, or what have you, and they have precise contents or senses even when their referents are abstract or nondescript. If the well-formed mathematical formulas were meaningless, there would be no way of checking them, and no point in doing so. But they are checked in several ways: definitions for non-circularity, axioms for fertility, conjectures for theoremhood, and so on. Further objections to Carnap's conventionalism in Quine 1949, and Gödel's in Rodriguez Consuegra 1992. In conclusion, mathematical conventionalism won't do. In any event, mathematical fictionism differs from it and has no use for it. Vulgar materialists, whether physicalists or nominalists, particularly if they are mathematically illiterate, are bound to reject mathematical fictionism for regarding it as a variety of idealism. For instance, Witz Thum, 1995, 146, who favors the 19th-century mechanistic materialism popularized by Karl Voigt, Jacob Moleschott, and Ludwig Buchner, regards fictions as constituting an anti-world. He claims that my view is a perfect vacuum, null, a mirage, and holds that I fail to see the idealist, counter-materialist quicksand into which the doctrine leads. Presumably, the nominalists would react in a similar manner, for they reject all concepts, they only admit inscriptions, which is why they prefer to speak of numerals rather than numbers, and of sentences rather than propositions. Neither physicalists nor nominalists offer a viable philosophy of mathematics, the former because they overlook the fact that mathematical objects have no physical, biological, or social features. And nominalism is false if only because there are not enough names to call even a tiny part of the world of mathematics, such as the real numbers lying between 0 and 0.001, which constitute a non-denumerable infinity. Besides, constructs, unlike their symbols, have formal structures. Actually, mathematical fictionism is neutral in the debate between materialism and idealism. In fact, mathematical fictionism is only about mathematical objects, it makes no assertions about the nature of the world. As far as mathematical fictionism is concerned, one may hold the world to be material. 208. Spiritual, or a mixture or combination of material and ideal objects. Materialists will reject fictionism out of hand only if they confuse materialism with realism. A materialist should not feel uneasy about the thesis that mathematical objects are ideal and therefore timeless, as Plato first observed, as long as he subscribes to the thesis, shared by mathematical intuitionists like Brouwer and Heyting, that mathematics is a human creation. All the reassurance the materialist needs is that mathematical ideas do not exist by themselves in some Platonic realm of ideas both immaterial and eternal. If he so wishes, he may regard any construct as an equivalence class of brain processes occurring in different brains or in the same brain at different times, see Bunge 1983. Yet it might be argued that mathematics is ultimately about the real world for, after all, arithmetic originated in counting concrete things like shells and people, and geometry originated in land surveying and, in particular, in the need to allot land lots to farmers. No doubt, such were the humble origins of the parents of mathematics. But mathematics proper is not about such empirical operations as counting and surveying. In fact, mathematics freed itself from its empirical origins about 3 millennia ago, when the Sumerians proposed the first general mathematical propositions and proofs. A cognate argument for both vulgar materialism and empiricism is that mathematicians often make use of analogy or of ordinary, incomplete, induction to find patterns, as Polya, 1954, showed persuasively. True, but the result of any such plausible reasoning is a conjecture that has got to be proved, or disproved, by purely mathematical means, for example, by reductio ad absurdum or using the principle of complete induction, neither of which is suggested by ordinary experience. In short, analogy and induction by enumeration have at most a heuristic value, they prove nothing, and proving happens to be the main job and sole privilege of the mathematician. Moreover, incomplete induction and analogy may lead us to error unless we check their outcome. Undoubtedly, factual science has sometimes stimulated mathematics by posing new problems. For example, dynamics encouraged, even required, the invention of the infinitesimal calculus and the theory of differential equations. Einstein's gravitation theory stimulated the growth of differential geometry, and quantum mechanics that of functional analysis, group theory, and the theory of distributions. But none of this proves that mathematics is about the real world, because a mathematical formula can be given alternative factual interpretations, or none. Besides, nowadays mathematics is far more useful to science and technology than the latter are to the former. In the modern intellectual production line, the main arrow goes from the abstract to the concrete. 209. Finally, another familiar objection to the autonomy of mathematics is the idea that some mathematical theories are more natural than others, for being closer to human experience. For instance, according to mathematical intuitionism in its radical version, no mathematical formula is meaningful unless it is somehow related to the natural numbers, Dummett 1977. But in fact there are plenty of non-numerical mathematical fields, such as logic, category theory, set theory, much of abstract algebra, and topology. Besides, the mathematical intuitionists have yet to produce a suitable semantic theory elucidating the notion of meaning, and thus helping us test formulas for meaningfulness, in their sense. Hence, strictly speaking, what they say about meaningfulness is meaningless. In conclusion, mathematics is semantically and methodologically self-sufficient. But at the same time it feeds all of the factual sciences and technologies, and is occasionally stimulated by them, so much so that mathematics is at the center of the system of human knowledge, which may be pictured as a rosette of partially overlapping petals. In other words, far from being independent from the rest of knowledge, mathematics is at the very center of it. But this does not entail the thesis, held consistently by Quine, and at times also by Putnam and others, that there are no important differences between mathematics and the rest, and that in principle mathematics might be refuted by experiment. Like spouses, mathematics and science are neither identical nor separate. So much for serious fictions, those that constitute knowledge and help advance knowledge. Let us now turn to a fashionable philosophical jeu d'esprit, namely, many worlds metaphysics. 9 metaphysical fictions, parallel worlds. Folklore and religion are full of impossibilia, from pathetic ghosts to awesome deities and fearsome devils. Fiction writers, painters, cartoonists, and filmmakers have imagined further impossible beings, such as Aristophanes' reasoning birds, and worlds where the laws of physics and biology do not hold. Metaphysicians too have imagined impossible entities, such as Descartes' demon and Kripke's parallel universes, though never in such minute and delightful detail as artists such as Hieronymus Bosch or Moritz Escher, Anatole France, or Italo Calvino. In particular, the contemporary philosophers who have written about possible worlds have been deliberately vague about these, perhaps because they were only interested in very general statements. However, they all agree in showing little interest in the only world that science regards as possible, that is, the one that satisfies the known laws of nature or 210. Society. Let us therefore start by distinguishing the two concepts of possibility in question, conceptual and real, see also Bunge 2003a. It is often assumed that, whereas science accounts only for the actual, artists and metaphysicians can afford to speculate about possibilities. The first part of this opinion is mistaken, because every scientific law covers not only actuals but also possibles, possible things, events, processes, and other factual items. Thus, the great physicist Ampere, 1834, 198, stated that mechanics applies not only to terrestrial bodies and machines, but also to all possible worlds. However, these are of course exclusively those that satisfy the laws of mechanics. By contrast, the possible worlds referred to by many worlds metaphysics and semantics are quite different from those of science and technology. The former need not be constrained by natural laws. Amazingly, one of the wildest fantasies about parallel worlds is the brainchild of a physicist, Hugh Everett III, 1957, and his thesis advisor, John A. Wheeler. This is the many worlds interpretation of quantum mechanics. According to it, every calculated possibility is realized in some physical world. Thus, if an electron can have three different energies, each of them with some probability, you will measure one of those energy values, a copy of you in an alternative world measures the second value, and your second copy the third value. The most obvious objections to this ingenious fantasy are that it violates all the conservation laws, and that it postulates inaccessible worlds, each of which is created by an experimenter, earthly or otherworldly. No wonder that the many worlds interpretation is generally regarded as a jeu d'esprit that does no work. Yet, at the same time it is treated as a piece of serious science, rather than pseudoscience, because it is formulated in mathematical language and it avoids certain weird features of the standard theory, such as the instantaneous collapse, or reduction, of the state function upon measurement, which is like preferring leprechauns to the ghosts said to haunt Scottish castles, because they do not drag noisy chains. Another curious development has come recently from the discovery that the universe is globally flat rather than curved. According to Einstein's theory of gravitation, this result implies that the universe is spatially infinite, see, example Tegmark 2004. Now, in an infinite universe ruled throughout by the same laws, any known material system is likely, if not bound, to occur at infinitely many places. In other words, there must be infinitely many nearly identical copies of the known part of the universe. For instance, there must be someone like you, though perhaps with a different haircut, reading a nearly identical copy of this very book. This is not the place to discuss the merits of this view. But one thing is clear, the alleged parallel universes cannot be other than very 211 distant regions of the universe, namely ours. If reality were multiple rather than one, it would be unknowable. But of course fantasy worlds are far more attractive to idealist philosophers than to scientists. Thus, the father of phenomenology, and grandfather of existentialism, held that the real world is only a special case of various possible worlds and non-worlds, all of which are in turn nothing but correlates of consciousness, Husserl 1931, 148. The plurality of worlds follows of course from the basic assumption of subjective idealism, that the world is somehow secreted by the subject. And we are supposed to know that this is so by intuition, which, according to Husserl, Ibid. 145, is infallible. However, the current vogue of possible worlds does not stem from phenomenology, so much so that David Lewis, 1986, the most famous of contemporary possible worlds metaphysicians, called himself a materialist. According to possible worlds metaphysics, example Kripke 1980, all of the conceivable universes, however weird, are equally possible, and moreover equally real, just because they are conceivable. Modal logic condones this fantasy, because it does not distinguish between logical and real possibility, and because its modal operators possible and necessary operate on propositions, not facts. By contrast, in science, technology, and everyday life possibility and necessity are predicated exclusively of factual items, as when we say that it is possible for humans to be vegetarians, but necessary for tigers to be carnivorous. Since modal logic does not distinguish between conceptual and real modalities, it is only a game with fake diamonds, logical possibilities, in paper boxes, logical necessities. Yet, as I write, modal metaphysics is mainstream metaphysics, see, example Lawrence and MacDonald, eds 1998, Lowe 2002, and Liu and Zimmerman 2003. Still, this theory is open to a number of obvious objections. One of them is that, unless we are prepared to fail utterly in real life, we must be able to distinguish between dreamed and real possibilities. If anything were really possible, then nothing would be impossible, and thus the word possible would be emptied, just like the word normal in psychoanalysis, according to which nobody is normal. A second objection is that in science really possible is coextensive with lawful, whereas in mathematics it amounts to non-contradictory, in technology to feasible, in the law to legal, and so on. Since the ontological concept of lawfulness and the praxeological concept of feasibility are alien to modal logic and to the many worlds fantasies, this theory is useless for discussing the prospects for scientific, technological, or social advancement. Besides, many worlds metaphysics is not intended as a serious ontology, for it tells us nothing, or at least nothing both interesting and correct, about being. 212. Or becoming, space or time, causation or chance, life or mind, society or history. It cannot even be used by experts in the supernatural. In fact, it has been ridiculed by some of them, because it distorts the notions of being and creation and is stuffed with infinities of abstracta that no one seriously believes to be real. Ross 1989. The theories in question are only intended as tools for semantics. Indeed, they are supposed to allow one to state, for instance, that tautologies are true in all possible worlds, that is, regardless of what happens, whereas counterfactuals hold only in some of them. Let us glimpse at the latter. A counterfactual, or contrary to fact, sentence has the form if A were the case, then B would be the case. The occurrence of the words were and would hints that neither A nor B is actually the case. Hence, the given sentence is quite unlike the conditional if A is the case, then B is the case, or AB for short. Whereas ordinarily the latter may be true or false to some degree, the corresponding subjunctive conditional can be neither. Hence, it falls beyond the reach of logic. However, the modal metaphysicians have invented a trick for transforming a counterfactual into a declarative sentence designating a proposition. The trick consists in pretending that the non-fact in question occurs in a dream world. Thus, it is posited that the sentence if A were the case, then B would be the case. 1. Is equivalent, in some unspecified sense of equivalent, to if A is the case, then B is the case in world W. 2. Of course this is not a logical equivalence, because sentence 1 does not stand for a true or even a false proposition, since it neither states nor denies anything. Moreover, whereas in affirming 1, one suggests that neither A nor B occur in the real world, when asserting 2, one may take refuge in an unreal world, much as a madman escapes the harsh facts of the real world by pretending to be God or at least Napoleon Bonaparte. In other words, if something is either impossible or false in the real world, one invents a topsy-turvy, yet otherwise nondescript, world where the impossible is possible, the false true, and evil good. Such emigration from the real world to Wonderland is the gist of an entire semantic theory, called possible world semantics, as well as of an entire metaphysics, namely, possible worlds metaphysics. These theories are said to elucidate a number of notions, such as those of disposition, lawfulness, and causation, see, example Kripke 1980, Lewis 2001 and 1986, Lowe 2002, and McCall 1994. The advantage of such elucidations is that they exempt the philosopher from learning how those important philosophical concepts are actually used in science and technology. Let us glance at some of those. 213. Brave attempts to face philosophical dragons with the handy if unreal sword, or rather scabbard, of conceptual possibility. Consider this well-worn example. This portion of cyanide has not killed anyone yet, but it would kill anyone who were to swallow it. That is, cyanide is potentially lethal, it has the dispositional property of being capable of killing, much as that heap of table salt has the disposition of dissolving in water, or that powerful government of conquering an oil-rich country. It is only natural for the ordinary language philosopher to elucidate such dispositions in two steps, This is toxic equals this would kill anyone who were to swallow it. 1. This would kill anyone who were to swallow it equals there is a world W such that in W this kills anyone who swallows it. 2. What has been gained? Nothing, since we already knew that the world W in question is the real world. We have no idea of any worlds where cyanide is not toxic, fundamentalists are tolerant, empires do not wage wars, and so on. Besides, what we really need to know is, rather, why cyanide is lethal in the only world there is. Metaphysicians cannot solve this problem, but toxicologists can. They can unveil the biochemical reactions that kill an organism poisoned with cyanide. What they do is to analyze the disposition toxicity in terms of actual properties of the organism cyanide system. They tell us that cyanide is toxic because it binds strongly with hemoglobin, thus depriving the rest of the organism of oxygen, which in turn is necessary for life. Physicists elucidate in like manner such dispositions as elasticity, potential energy, solubility, and refractivity. For instance, they do not state that the gravitational potential of a body suspended at a certain height above the surface of the Earth is the kinetic energy that it would acquire if it were released. Instead, they assert that the said gravitational potential equals the actual body weight times its height. They also tell us that, as the body falls, this potential energy is transformed into kinetic energy. Besides, they tell us precisely what the value of the latter is, they can calculate and measure it. Furthermore, physicists caution that the formulas in question only hold for small bodies, idealized as point particles, and small heights, compared with the Earth's radius. Compare the precision, richness, and testability of this bit of knowledge with the poverty of the possible worlds analysis. We shall return to this subject in Chapter 9. This is not to deny that we need fictions to do realistic science, on the contrary, we need plenty of them. Scientific fictions concern entities, properties, or experiments. For example, the atomic hypothesis was a grand fiction of the first type, about things, before any empirical evidence for it was produced more than 2 millennia after it was imagined. And the most common scientific fiction of the second type, about properties, is approximation, such as the 214 assumption that a given system is closed, that the interaction among its components is weak, or that its laws are linear. Weber called such idealizations ideal types. Their occurrence necessitates the use of the concept of partial truth. For instance, Ohm's law is only partially true at low temperatures. Literally, the truth value of this law statement decreases with temperature, a thought that is likely to induce a chill in anyone who believes that propositions are eternal objects, or at least born fully true or false. Finally, a number of imaginary, or thought, entities and experiments have been invented with several purposes: dialectical, heuristic, critical, didactic, or rhetorical. For example, Descartes imagined a malicious demon intent on deceiving him. The demon succeeded in everything except concerning Descartes' own existence. There is no doubt that I exist, if he is deceiving me. Maxwell illustrated the second law of thermodynamics imagining a being capable of directing the molecular traffic from a cold body to a warm one. This would have falsified the said law, but at the price of introducing the supernatural. Popper, 1959b, 442-52, performed a magisterial analysis of some of the most influential thought experiments in the history of physics, from Galileo's to Bohr's. He emphasized correctly that imaginary experiments prove nothing, though they may illustrate, disprove, suggest, or sell hypotheses. For example, Bohr's clock-in-a-box imaginary contraption had only what Popper called an apologetic use. In addition, it induced Bohr to postulate a false if often quoted formula, namely, the so-called fourth indeterminacy relation between energy and time. Mathematicians and philosophers too need fictions. For example, to use the truth table decision procedure, one pretends that truth values are intrinsic and eternal, while actually the truth value of any proposition about facts only emerges, or submerges, from tests, Bunge 2003a. and to introduce the general concept of a property, we may have to start off with the concept of a nondescript substantial individual or substrate, onto which we may subsequently stick such labels as massive and inhabited, Bunge 1977a. But these fictions are not idle, and they can be removed when no longer required. Which is not the case with the fictions that occur in speculative metaphysics. 10. We have outlined and defended one version of mathematical fictionism. This is our alternative to Platonism, nominalism, formalism, intuitionism, conventionalism, and empiricism. According to moderate fictionism, all mathematical objects are fictions, whence they are neither empirically compelling nor logi. 215. Cali necessary, even though they are constrained by logic. Those constructs are fictions because, although they are human creations, they are deliberately detached from physical, personal, and social circumstances. We pretend that those timeless ideal objects exist in a world, conceptual system, of their own, along with other fictions, such as myths and fables, which, however, have no ontological standing. In asserting the ideal existence of such fictions, we do not distance ourselves from reality, we just construct propositions that do not refer to the real world. Even children learn early on the difference between story and fact. Our version of fictionism is not only confined to mathematics. It is also moderate, because it is at variance with conventionalism, and it regards mathematics as a science, not as a grammar, much less as a game or pastime on a par with chess. It differs from conventionalism in assigning conventions a rather modest role in mathematics by comparison with hypotheses, proofs, and computations. And it regards mathematics as a serious activity that enriches our stock of ideas, and puts them at the disposal of factual science, technology, and even philosophy. In particular, mathematics helps us hone ideas of any kind, and discover structures and patterns, as well as pose and solve problems of all kinds in all fields of knowledge and rational action. Think of the central role that mathematics plays in modern engineering. Thus, far from being escapist, mathematical fictions are necessary to understand and control reality. If moderate mathematical fictionism is true, that is, if it fits mathematical research, then mathematical Platonism, conventionalism, formalism, nominalism, empiricism, and pragmatism are false even though they are the most popular of all the philosophies of mathematics. Platonism is false, or at least untestable, because fictions are human creations, not self-existing eternal objects. And mathematical empiricism is utterly false because most mathematical fictions go far beyond experience, and none are tested by it. The same holds, a fortiori, for mathematical pragmatism, the philosophy of mathematics tacitly espoused by those who demand that mathematics and the other basic sciences should be responsive to the market. As for mathematical intuitionism, it is inadequate because it restricts severely the invention of mathematical fictions on doubtful philosophical grounds, such as constructivism and the Pythagorean worship of natural numbers. Caution: this criticism concerns mathematical intuitionism, not intuitionist logic or mathematics, see Bunge 1962. Nominalism, or formalism, is false too if only because, as Freya pointed out, it rejects concepts and confuses signs with their designata, for instance, numerals with numbers. Not even the self-styled nominalist, or formalist, can help using notational conventions. 216. Such as let n designate the set of natural numbers, that pair concepts to symbols. Finally, conventionalism is false for a different reason, namely, because it conflates assumption with definition, and it jettisons the concept of mathematical truth. This concept is needed in at least three circumstances: when checking a calculation, proving a theorem, and showing that an abstract theory is satisfied by a concrete one, or model. Furthermore, if mathematics, including logic, is the most exact and comprehensive of fictions, then we need no special logic of fictions, such as those of Woods, 1974, and Routley, 1980. In particular, the free logics, that is, logics with empty domains, deliberately invented to handle fictions, turn out to be unnecessary. This remark may be useful to curb the inflationary growth of deviant logics, the vast majority of which are mere academic pastimes only good to get promotions, as Hilbert might have said. See Hawk 1974 for a superb survey. What about the holy trinity of foundational studies, namely, logicism, formalism, and intuitionism? It may be argued that, contrary to received wisdom, these are not philosophies of mathematics but foundational strategies, Bunge 1985a. Mathematical fictionism has little to say about any of them. Indeed, in principle one may couple mathematical fictionism to either logicism, formalism, or moderate, post-Brewerian, intuitionism. Alternatively, one may latch it onto the combination of all three strategies, which seems to be tacitly favored nowadays by most working mathematicians, Lambeck 1994. Moderate mathematical fictionism ought to exert a liberating influence on the mathematical researcher in reminding him that he is not out to discover a ready-made universe of ideas, or to explore the real world, or even to latch onto natural numbers. His tasks are to create, invent or discover, mathematical concepts, propositions, theories, or methods, and to discover their mutual relations, subject only to the conditions of consistency and conceptual fruitfulness. As Cantor said, freedom is essential to mathematics. I submit that the main duties of a philosopher of mathematics are to defend the freedom of mathematical creation from philosophical strictures, to see to it that mathematical fictions are not reified, to use some of them to elucidate, refine, or systematize key philosophical ideas, that is, to do some exact philosophy, and, above all, to build a philosophy of mathematics matching actual mathematical research as well as a science-oriented general philosophy. And as semanticists and metaphysicians, our duty is to face the fact that the conceptual and practical problems of the only world there is cannot be tackled successfully by asking for asylum in fantasy worlds. In sum, we invent fictions in all walks of life, particularly in art, mathematics, science, and technology. Whereas some fictions are disciplined, others are. 217. Wild. A disciplined fiction abides by the laws contained in an exact theory. Science, technology, and serious philosophy use only disciplined fictions, particularly mathematical ones, such as the concepts of set, equivalence relation, function, and consistency. The rightful place for wild fictions is art, or incontinent philosophy. 218. 9. Transcendentals are of this world. Anything not encountered in experience is usually called transcendental. Like all negative definitions, this one is ambiguous. Indeed, according to it, intuitions and a priori ideas, along with universals and theological items, qualify as transcendental. For example, the idealist philosophies of Plato, Leibniz, Hegel, Fichte, Bolzano, and Husserl are transcendental because they do not rely on experience. By contrast, Berkeley's, Hume's, Comte's, Mill's, and Mach's philosophies are not transcendental because of their empiricism. And Kant's philosophy is only semi-transcendental because, though a prioristic and intuitionist, it is also semi-empiricist on account of its phenomenalism. From a practical viewpoint, transcendental items, or transcendentalia, may be partitioned into two classes, useful and useless. Thus, the concept of class, kind, sort, or species is necessary in all walks of life, whereas that of parallel universe has at best a heuristic function. This chapter deals with a miscellany of transcendentals of both kinds, particularly the concepts of universal, species, possible world, disposition, spacetime, and liberty. No attempt will be made to organize this collection. The point of the present exercise is to clarify the concepts in question from the point of view of scientific hylorealism and, by the same token, to clear away a number of misconceptions about them. The net result will be that, whereas some transcendentals are indispensable to account for reality, others only block the view of it. 1. Universal. The word universal designates a general predicate, such as concept and number, as well as a frequently occurring property, such as material and live. Idealists, from Plato onwards, have ignored the predicate-property difference. They have also postulated that universals exist by themselves and 219 precede particulars, which they regard as mere instantiations, examples, of the former. This view, idealist or Platonic, realism, is still popular. For example, it is inherent in contemporary statements that brain systems instantiate, mediate, or subserve mental abilities, and that the latter have multiple realizations, in brains, computers, ghosts, and deities, as Fodor, 1981, and other philosophers of mind have claimed. According to materialism, in particular nominalism, all real existents are singular. As the putative father of nominalism put it, everything outside the soul is singular, Ackham 1957 ca 1320. This is why we can only experience particulars. In other words, the phenomenal world, just like the physical one, is composed exclusively of individuals. The nominalists, or vulgar materialists, from Ackham and Buridan to Quine and David Lewis, reject universals altogether, not only as concepts but also as features of material individuals. They postulate that the only real existents are bare individuals, that is, concrete entities devoid of properties other than the ability of joining with other individuals. Hence, they dream of a science without properties, example Woodger 1952. But that would be no science, because scientific research is essentially the search for laws, and laws happen to be invariant relations among properties, see Bunge 1967a. Furthermore, nominalists equate properties with classes of such individuals. Thus Lewis, 1983, 164 to have a property is to be a member of the class. The property of being a donkey, for example, is the class of all the donkeys. In obvious symbols, d equals x dx. But of course this definition is circular. Besides, when forming a natural class or kind, we start with the defining properties. In the example at hand, we may set, in ordinary knowledge terms, d equals equid and smaller than an Arabian horse and long-eared and stubborn. Since nominalists go from individuals to classes to properties, they are bound to form artificial classes rather than natural kinds. Hence, they are unlikely to understand such expressions as body, field, chemical species, biospecies, origin of species, or social class. And, since they countenance neither predicates nor propositions, the nominalists cannot help us analyze them either. Although we cannot sense universals, we could not possibly think or speak without them. This is why even the nominalist Ackham admitted universals by convention, that is, words that are universal because they can be predicated of several particulars. As Russell, 1912, pointed out, it is impossible to form even the simplest sentence without employing words designating universals. Thus, the trivial egocentric statement "I want it" is constituted by words designating universals. Indeed, there are as many is or selves as human beings, every one of whom wants a number of things. Likewise, it is a blank 220 or index to be filled by different items in different circumstances. Therefore, nominalism does not even hold for languages, although it attempts to replace concepts with their names. Nominalism fares even worse in mathematics and in the factual, empirical, sciences, for all of them attempt to subsume particulars under universal laws, which are the universals par excellence. These laws are either universal generalizations, or statements asserting the existence or non-existence of individuals of a given kind, such as zero, black hole, and hominid. Moreover, no physical or chemical law statement concerns observations, whereas all of these are observer-bound and couched with the help of phenomenal predicates. and the basic law statements in physics are required to be the same relative to all reference frames, hence observers in particular, of a certain kind, i.e., inertial, whereas the results of observations of certain properties, such as particular positions, frequencies, and energies, are frame-dependent. Hence, the nominalist program, of either reducing universals to particulars or dispensing with them altogether, cannot be carried out. Rather, on the contrary, many particular concepts and words can be characterized in terms of universal concepts or words. For example, my daughter describes a unique individual in terms of two universals. However, the latter are not regarded as independently existing ideas. Modern science too rejects the independent existence, anti-ram, of universals. However, scientists look for the universal and lawful in the particular and contingent. As Levins and Lewontin, 1985, 141, famously put it, things are similar, this makes science possible. Things are different, this makes science necessary. The philosophical problem is of course that of the nature of universals and their relation to particulars. Are universals self-existing ideas, Platonic realism, properties shared by many individuals, scientific realism, or just sounds or inscriptions, nominalism? In scholastic jargon, are universals anti-ram, in re, or post-ram? This problem comes from antiquity and is still with us. One of the most interesting, yet least well-known, solutions to it is that of the Jaina school, which has been in existence for 2.5 millennia. According to the Jains, everything has a general as well as a particular aspect, Haryana 1951, 65. For example, a particular cow is characterized by cowness, which it shares with all the other cows, but it also has certain properties that are special to it. In other words, the universals inhabit concrete individuals. At about the same time, Aristotle defended the view that the universals, far from being anti-ram, as his teacher had held, are in re. Nearly 1.5 millennium later, Averroes expressed essentially the same view, Quadri 1947, 209-11. In this, as in other regards, modern science has vindicated Aristotle's moderate position concerning universals. Indeed, it is a tacit postulate of 221. Modern science that all properties are properties of something or other, there are neither properties in themselves nor entities devoid of properties. The same problem resurfaced in the 19th century in relation to the social sciences: are they confined to particulars, ideographic, or do they also attempt to uncover patterns, nomothetic? Arguably, the social sciences, just like the natural ones, are nomothetic as well as ideographic, Bunge 1996. For example, the historian looks for the common features of all military aggressions, and finds them in the wish to appropriate something, such as territory, natural resource, labor force, or trade route. And criminologists look for patterns behind particular cases of law breaking, for instance, the weakening of social bonds, social control theory, anomie, social strain theory, association with delinquents, social learning theory, marginality, systemism, or what have you. According to scientific realists, the word universal denotes both a property that, like mobility, life, and being yours, is possessed by several items, and b the concept s representing that property. That is, universals are assumed to exist both through concrete individuals and as abstract ideas, in neither case in and by themselves. In Hegelian jargon, there are universals of two kinds, abstract and concrete. The former are post-rem, the latter in re. For example, logical consistency is an abstract universal because it only applies to sets of propositions, in particular theories. By contrast, income inequality is a concrete universal because it is inherent in all stratified societies. However, there are several measures of the degree of that inequality, every one of which is an abstract universal. Recall the difference between properties and the predicates representing them, Chapter 1, Section 4. This view of universals, in particular laws, is close to Aristotle's, and is part of Hylo-realism, or materialist realism. Not surprisingly, this view is unpopular among contemporary philosophers. In particular, Popper, Quine, Goodman, and Gellner called themselves nominalists just because they opposed Platonic realism, and agreed that only individuals exist, without however caring to clarify whether they meant abstract or concrete individuals. As hinted above, even particulars may be regarded as instances of universals. For instance, 7 is a number, Fido is a dog, and being 30 years old is a particular value of age. In general, functions subsume particulars under universals. More precisely, a particular property may be regarded as just a special value of a general property represented by a mathematical function. For example, energy, the most universal of all non-conceptual properties, is classically representable as a function from concrete things to numbers. Even proper names may be regarded as particular values of the naming function. This function maps people into names, that is, n, Pn, where n designates the 222 set of names, complete with surnames, patronymics, matronymics, and toponymics to make them unique. Here, the members of the set n are particulars, whereas n and p are universals. More precisely, in classical physics the energy of a concrete thing c relative to a reference frame f, at time t, and calculated or measured in the unit u, can be written E, c, f, t, u, equals E, where E is a real number. This formula makes it clear that energy is a property representable by a function, not a thing designated by a name. In the previous example, the function E maps the Cartesian product c times f times t times u into the real line. Drop c or f, the bearers of energy, and no energy remains. And dispense with energy, and no physics remains. In mathematics, both classes and their members exist, albeit only fictitiously, recall Chapter 8. By contrast, the chemical, biological, and social classes exist only as concepts, or fictions, whereas their members are material existents. However, far from being arbitrary, the classes in question are the extensions of universalia in re, such as bivalence, bipedalism, and poverty. Thus, humankind, H, is the class of all the individuals possessing the complex property H of being human, H equals XHX. How do we know that these are universalia in re rather than either ante-rem or post-rem? Because they are representable as predicates whose domains contain classes of concrete things. Equivalently, because the corresponding predicates refer to material entities. That is, the function H maps the set M of material items into statements of the form X is human. See Bunge 1974 for this non-Phrygian construal of predicates. The above functional analysis of the universal, particular relation helps analyze the thesis that there can be no historical laws because history does not repeat itself. In fact, although no two historical events are identical, any two historical events have something in common, for instance, that they are basically economic, political, cultural, or all three. For example, although the two world wars were quite different, both were military conflicts embracing nearly the entire world. In other words, although taken as a whole every historical event is unique, and thus defies classification in all respects, when analyzed it is seen to share some features with other events, it is a combination of concrete universals. The same holds, mutatis mutandis, for all facts. We may surmise that even free will is lawful, as suggested by the fact that it can be removed surgically, lobotomy. In other words, scientists assume that all facts are lawful. This explains why we find laws in all domains, provided we try hard enough. We tend to take laws for granted, both as objective patterns and as the conceptual representations of the latter. We do this to the point of adopting, at least tacitly, the lawfulness principle, according to which all facts satisfy some laws. However, the ontological status of laws is far from clear, largely because of the idealist confusion between objective patterns and the formulas whereby 223. We attempt to represent them. Take, for instance, the chemical laws, that is, the laws that govern the formation and dissociation of molecules. Did these laws exist before the first chemical compounds emerged? A Platonist, such as a medieval realist, would answer in the affirmative. The first chemical compound was just an instantiation of a chemical universal that literally governed the process in question. By contrast, a nominalist would hold that the laws in question appeared only post-rem, in the mind, by way of abstraction from phenomena. That is, he would claim that nature is contingent, and that patterns are only in the mind. Finally, a scientific realist is likely to argue that the chemical laws inhere in chemical processes, so that they first emerged along with the earliest chemical compounds, when the planets cooled sufficiently. In general, the natural laws are objective patterns of being and becoming, Bunge 1959b. To conclude this section, we cannot dispense with universals any more than we can dispense with phenomenal concepts. We need the latter to describe experience, and universals to explain it. Only a divine intellect could dispense with qualia and their corresponding concepts, and only lowly organisms make do without universals, such as reachable and edible. Presumably, a puppy forms gradually the universal meal as it finds food in its dish, and the universal people as it meets individual humans. No dog could survive on a nominalist diet, for it would be unable to, a. generalize individual experiences, b. learn rules, such as bark at strangers, compliance with which puts food in his dish, and c. distinguish the different properties of one and the same thing, such as round, soft, rollable, and bouncing applied to a ball. Besides having some universal concepts, puppies and all other things have universals in re. For example, they and all the other multicellular organisms satisfy the logistic law of body growth. In short, universals are indispensable because they are both in the world, as properties, and in theories, as predicates. The nominalist's world of bare, property-less, individuals is just as fictitious as Plato's realm of ideas. Neither helps understand, say, that buoyancy is a property of boats but not of electrons, let alone of numbers. Failing to see the universality inherent in every particular is just as mistaken as failing to identify what makes an individual unique. In other words, in trying to understand things and ideas, we cannot dispense with the concept of a kind or species. Which brings us to the next section. 2. Kind. Contrary to Plato, Aristotle held that only individuals may be real, that all classes or species are in the mind. The medieval nominalists, such as Occam 224 and Buridan, went further. They had no use at all for the concept of a species or natural kind, because they rejected universals and regarded the cosmos as a collection of mutually independent items, see, example Gilson 1947. Consequently, for a nominalist all classifications, even the periodic table, are purely conventional. The fathers of evolutionary biology, from Bonnet and Buffon to Lamarck and Darwin, concurred. To them, in nature there are only individuals, species are constructs, and classifications conventional. But Darwin contradicted himself in stating at once that species are conventional, but phylogenies, which are relations among species, are natural. Indeed, since humans and monkeys have common ancestors, all three classes in question, though not material entities, must somehow represent real evolutionary processes. Whereas some classes are artificial, others are natural, that is, they represent objective commonalities among existents. For example, there is nothing arbitrary about the periodic table of the elements. And, while both the Linnean and cladistic classifications are natural, the latter is generally deemed to be more adequate than the former. Nevertheless, whether artificial or natural, Every class is a construct. Hence, the expression origin of species must be interpreted elliptically, as short for origin of organisms belonging to new species. In other words, speciation, the emergence of new species, is a real process on the organismic level, and extinction is parallel, but in both cases what emerges or submerges are individuals. What happens before speciation and after extinction is that the corresponding species are empty collections. Scientists ignore the nominalist ban on species. Regardless of his philosophical allegiance, the very first thing a scientist does is to heed Aristotle's advice, identify the object of study in terms of species and specific differences, as in unary predicate, continuous function, higher mammal, business enterprise, and developing country. That is, scientists take it for granted that all the objects they study group into kinds or species that are natural rather than artificial or conventional. As the gruesome idiom has it, they attempt to carve the universe at its joints. Moreover, scientists formulate generalizations involving the species concept, such as birds of a feather flock together and all metals are opaque. What holds for things also holds for facts, such as states and changes of state. Every real fact is singular, but at the same time it belongs to some class or other, namely, the one covered by the law, it abides by. Shorter, facts are particular but not unique, because they all fall under some law or other. Even the origin of our solar system, though unrepeatable in details, is but an instance of the class origin of planetary systems, a class characterized by certain astrophysical laws. The main philosophical problem about species is, what is a species? That is 225. How is it defined and what kind of object is it, conceptual, factual, or, as Leibniz thought, semi-mental? To answer these questions, let us start by recalling how a species is ordinarily defined. Depending on the richness of our background knowledge, we can resort to either of two methods of definition, by property or by equivalence relation. In the first case, we pick on a salient property, such as atomic number, which we represent by a predicate p. Next we find out the extension of p, that is, the collection of all the ps, or members of the universe of objects, that possess the property represented by the predicate p, s equals e, p, equals xpx. The defining predicate p is usually the conjunction of a number of simpler predicates. When a single predicate is at stake, one gets the rather weak notion of a kind, such as age or income group. The far stronger concept of a natural kind is defined in terms of laws. It is the collection of all the things that possess properties that are lawfully related to one another. Example, electromagnetic field equals whatever satisfies Maxwell's equations or their quantum theoretical generalization. Shorter, a kind is a natural kind if all its elements meet at least one law. However, we do not always know the relevant laws, particularly at the start of a new research line. In this case we resort to mere similarities, equalities in certain respects, or equivalences, such as having the same sex, age, occupation, or income bracket. Thus, we state that, although Nelson Mandela is unique, in one respect he is in the same league as all the other freedom fighters. These individuals constitute the class F equals X. HX. FM where F designates is equivalent to with respect to F, freedom fighting, and M abbreviates Nelson Mandela. The two methods of class formation falsify, among others, the following rather popular theses. One is the opinion that it is impossible to pigeonhole complex things, such as people, mental states, and social facts. Actually, it is perfectly possible to do so in some respects, though not in all. Another related misconception, currently popular among philosophers, is that biospecies are concrete individuals on a par with their constituents, that is, individual organisms, example Gazelin 1974, Hull 1976. The reason usually given is that species are said to evolve. But of course biopsies, being sets, not aggregates, are unchanging, only their members, organisms, and aggregates of them, populations, can and do change. Still, a species may be regarded as a higher-order individual, or system, if taken together with its structure, which includes the relation of common descent. Thus, one stipulates that any 226 members A and B of S, however different in details, are equivalent in that they have a common ancestor. That is, we state that AB equals DFC, DAC and DBC. We next construct the system of akin species S equals. Thus, we have introduced two concepts, S and S. Only the members of S, and the populations of S, are concrete. The former are first-level, and the latter second-level systems. In turn, every population is a part of some community or ecosystem. See Figure 9.1. If species were concrete individuals, it would be possible to gather or hunt, cook, and eat some of them rather than some of their members. Biospecies are not individuals but collections, and, at any given instant, a collection is a set proper, see Bunge 1979a and 1981c and Monner and Bunge 1997. Proof: all biospecies are defined as sets defined by predicates. For example, the standard if flawed definition used in biology is this: biospecies are groups of potentially interbreeding organisms, which are reproductively isolated from other such groups. The same holds for chemical species, such as hydrogen and carbon, as well as for social species, such as rural and urban, or employer and employed. In all cases, the individual-species relation is the membership relation, not to be mistaken for the part-whole relation that obtains, for instance, between cell and organ, or word and text. This is why one can copyright texts but not words, nor even entire vocabularies, whereas the former have owners, the latter belong to linguistic communities. 3. Possibility. Possibility is the most slippery of ontological categories, for it lies between being and non-being, present and future, datum and conjecture. No wonder that some philosophers have denied real, or ontological, or objective, possibility. For instance, Kant restricted possibility to experience: there are only possible experiences. Moreover, this is what things would be, namely, bundles. Ecosystem OOS system of species. Things population OOS species constructs. Organism O. Figure 9.1 M concrete individuals on three different levels: organism, population, ecosystem. Abstract individuals on two levels: species, and system of species. 227. Of possible experiences. Hence, no percipients, no things. Likewise, modal logic treats possibly as an operator acting on propositions, not on facts, see, example Hughes and Cresswell 1968. And possible worlds metaphysicians analyze P is possible as there is a world at which P is true. However, they do not bother to characterize such worlds in a precise manner. Since some of the worlds in question violate the known laws of nature, the corresponding conceptual possibility may be really impossible. We looked at these unscientific fantasies in Chapter 8, Section 9, and will examine them further here in Sections 4 and 5. Let us now focus on the serious problem of the concept, or rather concepts, of real possibility. Let us start by recalling briefly how the concept of real possibility is used in the sciences and technologies. To begin with, the reality of possibility is made quite clear in the state space representation of things of any kind. Indeed, every point in such an abstract space is deemed to represent a really possible, that is, lawful, state of the thing in question, whether atom, organism, ecosystem, social system, or artifact. Recall Chapter 1, Section 1. However, even when no such representation is available, the following varieties of real possibility are generally admitted outside mainstream metaphysics, which is predominantly speculative rather than scientific. Natural possibility equals compatibility with the laws of nature. Social possibility equals compatibility with the norms prevailing in a given society. Technical possibility equals feasibility. Economic possibility equals profitability. Political possibility equals accessibility of public office. Moral possibility equals not infringing on any basic rights of anyone. Legal possibility equals compatibility with the ruling legal codes. Epistemological possibility equals knowability with the means in hand. Alethic possibility equals plausibility in the light of the background knowledge. Methodological possibility equals testability. None of these 10 concepts is elucidated by modal logic, because all of them involve non-logical concepts, hence the irrelevance of modal logic to real life, science, and technology. Worse, mixing the various concepts of possibility in the same context involves confusion, and it may lead to error or paradox. For example, you can, physically, kill me, but you may, morally, not kill me. Formalizing factual and conceptual possibility with the same possibility operator, the diamond symbol of the modal logics, leads to trouble. One solution would be to introduce 10 diamonds with the same syntax but different semantics. However, in this case one should also introduce 45 bridges between these different possibilities, such as whatever may be done can be 228 done, but not conversely. Moreover, one could then speak of 10 different worlds, and of the 45 bridges between them. But this solution would drive a cam up the wall. Why not dispense with modal logic altogether, since it can solve no philosophical problems because it is too coarse to distinguish among utterly different kinds of possibility? More in Bunge 1977a, 2003a. To sum up, since we admit the category of real possibility, we must enlarge the concept of reality, and with it our worldview, to include possible facts along with actual facts, which in turn can be either necessary or contingent. That is, we must adopt the following partition, Bunge and Monner 2004, 109. For a surfeit of worlds. Nearly everyone agrees that there are possibilities and impossibilities in addition to actualities. For example, it is possible that you will make a new friend, but impossible that your health will improve upon smoking. On a more technical level, quantum mechanics specifies that certain transitions are possible and others forbidden, and thermodynamics proves the impossibility of engines of certain kinds. In addition to asserting such real possibilities and impossibilities, physicists resort to virtual items such as imaginary points, virtual displacements, and their kin. In fact, in physics, virtual means conceptual possibility, as opposed to real, or physical, possibility. This distinction occurs in the very formulation of the highest level principles in physics, namely, the variational ones. The form of all such principles is A equals 0, where designates a conceptual variation, such as an imaginary displacement, and A names a basic physical property, such as an action, or energy times time. The formula states that A is an extremal, maximum or minimum, or, equivalently, that A is conserved under the variations in its independent variables, such as coordinates and velocities, or that the real trajectory of the thing of reference is the one, among all the conceivable trajectories, along which A is extremal, usually minimal, see, example Langchos 1949. That this is the correct interpretation is seen by contingent facts, causal, or conditional, possibility, real possibility, reality, actuality, chance, or unconditional, disposition, necessary facts. 229. Examining the way A is calculated. Indeed, this calculation obeys the laws of the calculus of variations, a branch of pure mathematics, where nothing ever happens. Interestingly, the condition A equals 0 implies the equations of motion, or the field equations, which describe the real trajectories, or the field propagations. That is, a statement of conceptual possibility, though one concerning a physical magnitude, implies a statement of actual occurrence. All that is standard if somewhat heady scientific fare. What about pigs flying, people communicating through telepathy, or government of the people, by the people, and for the people? Here is where the paths of philosophers diverge. Science-oriented thinkers regard such events as impossible, for violating certain natural or social laws. By contrast, the modal metaphysicians, such as Manin, 1960, Kripke, 1980, Routley, 1980, David Lewis, 2001, 1986, and their numerous followers regard them as possible, or even necessary, in alternative worlds, much as the theologians claim that bliss, while impossible in this world, is bound to be experienced in the next. Modal metaphysics is not just an ignorable extravagance, it has become part of mainstream philosophy. See, example Lawrence and MacDonald, eds 1998, Lowe 2002, Liu and Zimmerman, eds 2003, and Melia 2003. We glimpsed at this theory in Chapter 8, Section 9. Let us now take a closer look at it. Obviously, the choice between the two alternatives noted above depends critically upon the meanings assigned to the words world, possible, and true. On a broad construal of these terms, the above-mentioned possibilia are such in some sense, logically or physically, and in some world or other, whether real or imaginary. For example, in Kakan, the land of plenty, everyone lives in luxury without working. Obviously, this is impossible in the actual world, and in the particular sense in which the expression real possibility is used in science and technology, namely, as compatibility with the known laws of nature. But the whole point of speculative philosophy is to work with the sole restriction of logic. To mark the contrast between conceptual and real possibility, consider the ways that existence hypotheses are proved, or just confirmed, and disproved, or just undermined. In mathematics, existence proofs, if correct, are definitive. Thus, it has been proved once and for all that there is no such thing as the greatest number, and that there are infinitely many prime numbers. By contrast, real existence is ordinarily proved by exhibiting a specimen of the hypothesized entity, or at least by showing reliable indicators of it, such as brain waves in the case of neural activity and fossils in the case of extinct vertebrates. In some cases, a theory suggests the existence or non-existence of real things or events of certain kinds. Thus, classical electromagnetism suggested the existence of electromagnetic waves long before they were produced. 230. In the laboratory, and according to Einstein's theory of gravitation, there must be gravitational waves. Physical existence can be suggested by theory, but it can only be proved by experiment or field work. Characteristically, the so-called modal metaphysicians are not interested in the real world that scientists and technologists study, they enjoy imagining worlds where nearly anything is possible. Still, there are a handful of different schools of modal metaphysicians, some more tolerant of unbridled imagination than others, see Leakin 1998. The radical wing of modal metaphysics is constituted by people who assert the real existence of multiple parallel universes inaccessible from one another. Paradoxically, they call themselves modal realists. In fact, they are ontological relativists, and as such irrealists. By contrast, thinkers in the moderate wing are content with asserting that things could have been different in countless ways, and call them misleadingly possible worlds. Still other metaphysicians, notably David Lewis, waver between the two wings. Thus, he would have claimed that a world in which Hitler won the war is very different from the world we know. But he also wrote about a world at which heat is the defunct caloric rather than random molecular motion, Lewis 1983. An exact philosopher would regard the first case as an equivocation, while a scientist would dismiss the second as idle extravagance. Regardless of the wing to which they belong, all modal metaphysicians start from the semantics for modal logic proposed by Kripke 4 decades ago. The reason is that the only justification for talking of possible worlds is the need to equip modal logic with the semantics. A realist philosopher would have thought that modal logic is not worth saving at the staggering price of adding uncounted and barren dream worlds to the real world. He would have wondered why anyone would mourn the loss of a theory that had failed to deliver the goods that Clarence I. Lewis promised nearly 1 century ago, namely, the simultaneous elucidation of the notions of possibility and logical necessity, both de re and de dicto, see Bunge 1977a. At all events, modal semantics purports to explicate the modalities possible and necessary by reducing them to the concepts of world, existence at a world, and truth. Thus, it is posited that, for any proposition P, possibly P equals df, there is at least one world at which P is true, and necessarily P equals df, P is true at every world. Thus, everyone lives without working is deemed possible because somebody dreamed up Cochin. A roughly equivalent formulation of the same idea is counterpart theory, Lewis 1986. It states that individual X possibly has property P if and only if X has a counterpart in a universe spatio-temporally isolated from ours. 4. 231. Example, though unknown to you, you may be an alchemist if in an alternative universe there is an individual closely resembling you, except that he engages in alchemy. These counterparts are real according to some modal metaphysicians, notably Lewis, whereas they are abstract or semi-abstract according to others. I confess that the notion of semi-abstraction is above my head. The historical root of all these elucidations is Leibniz's 1703, important and correct distinction between vérités de raison and vérités de fait, and his assertion that the former, unlike the latter, are true in all possible worlds. This famous metaphor makes literal sense in Leibniz's Theodicee. When pondering about the kind of world he should create, God could choose whatever laws of nature he pleased, but he could not go against logic. In particular, he could not contradict himself without risking Leibniz's contempt. This metaphor is pedagogically effective. But, if taken literally, the possible world's elucidation of the modalities is open to the following technical objections. To begin with, this allegedly sophisticated explication of modality is actually coarse, because it is unrelated to the concepts of real, gnomic, possibility and necessity used in science, from physics to population genetics and the sociology of networks. In particular, the above construal makes no contact with the scientific concepts of disposition, such as solubility, and chance. Worse, none of the three definientia, the concepts of world, existence, and truth, is clearer than the corresponding definienda. It is an obscurum per obscurius explication, like defining the number 1 as 00, or as the negative of the square root of the imaginary unit. It is also objectionable to make possibility in our world dependent upon actuality in a parallel world. The reason is that, since that fantastic world is inaccessible from ours, it cannot be inspected to check whether, in fact, it contains the desired counterparts. Hence, we could never ascertain whether or not a real individual has possibly a given property. Thus, to find out whether in our world substance X is soluble in liquid Y, the counterpart theorist need not make any calculations or experiments. All he needs is to dream up a world where Y actually dissolves X. Counterpart theory evokes the doctrine of predestination. My lot in this world is already specified in the celestial record kept in the great beyond. More in Merrick's 2003. I submit that the basic philosophical concepts in question, those of world, existence, and truth, are highly problematic. Indeed, each of these words actually designates a whole bunch of concepts. In particular, there are imaginary worlds, such as Lewis Carroll's, Jorge Luis Borges's, and Isaac Asimov's, as well as those of mathematics, in addition to the real worlds of business and sports. Consequently, there are at least two very different kinds of exist. 232. Ints, namely, material and conceptual, recall Chapter 1. Accordingly, there are at least two kinds of truth, factual and formal, in addition to artistic and moral. Modal metaphysicians overlook or deny all these huge differences. Moreover, In nearly all fields of knowledge and action, truth comes in degrees. In fact, in all walks of life we find and use many more near truths and near falsities than full truths and full falsities respectively. For example, even the most precise measurements are affected by errors or discrepancies from truth, and even the best theories are only approximately true. What do we get when substituting approximately true or half true for true in the above definitions of the modalities, half possibility and half necessity, or else half worlds? The modal metaphysician does not raise these questions, he is content with coarse notions of truth, world, and existence. I submit that this imprecision, inherent in ordinary knowledge and everyday language, is a root of the various systems of modal metaphysics. More on this anon. 5. Many worlds metaphysics is inexact. The best way to find out the presuppositions and basic assumptions of any theory is to organize it axiomatically, that is, to force it into the axiom definition theorem format. Since modal metaphysics is inexact, its axiomatization should help pinpoint the roots of its troubles. I will therefore axiomatize a fragment of David Lewis's theory, which is currently the most widely discussed of all modal metaphysics. To begin with, the primitive, undefined, notions of this theory are those of world and truth, both of which are actually problematic. The underlying logic is modal logic. But we are not told which one of the 256 possible systems of modal logic. The first specific assumption is this: axiom 9.1 to be is to be a value of a bound variable. Equivalently, existence equals. Remark 1. This is of course Quine's famous formula, a typical piece of panlogism, although Quine thought of himself as a physicalist, or nominalist, or vulgar materialist. Remark 2. Although at first sight the above is a convention, actually it is an assumption, for it equates two radically different modes of existence, namely, logical and physical, or conceptual and material, or abstract and concrete respectively. Indeed, axiom 9.1 entails informally corollary 9.1 there is no difference between real, or material, and logical, or imaginary, existence. Equivalently, whatever is conceivable exists simpliciter, and conversely. Corollary 9.2 there is no difference between facts and propositions. 233. This identity is of course suggested by ordinary language, from Sanskrit to English, where one seldom distinguishes between this happened, or this is a fact, and the proposition that this happened is true. But of course the difference between facts and propositions is basic in any self-respecting ontology and epistemology. Refined nominalists, like Occam, admitted the difference, since they located all fictions in the mind. Axiom 9.2 there is only one concept of possibility, and it is exhaustively elucidated by any of the systems of modal logic. Corollary 9.3 there is no difference between real and logical possibility. Equivalently, whatever is really possible is logically possible, and conversely. Corollary 9.4 whatever could, conceivably, happen does happen in at least one of the possible worlds. Definition 9.1 a possible world is similar in kind to ours. Remark, Lewis, 1973, 85, asks us to admit that we know what sort of thing our actual world is, and goes on to explain that other worlds are more things of that sort, differing not in kind but only in what goes on at them. This is a paragon of inexact philosophy, and as such it invites multiple arbitrary interpretations. Definition 9.2 Object X is real equals there is at least one world that contains X. Definition 9.32 Individuals are world mates if and only if they are related spatio-temporally. Definition 9.4 The actual world is the one of my world mates. Theorem 9.1 There are infinitely many possible worlds. Theorem 9.2 Our actual world is only one world among others, Lewis, Ibid. Proof, by axiom 9.1 and definition 9.2, neither the possible worlds nor their constituents are subject to any constraints, in particular laws. This completes my construction of the axiomatic mini-system that encapsulates Lewis's metaphysics. There are two ways of judging this theory: or any other for that matter. One of them is to examine the axioms and definitions themselves, the other is to assess their logical consequences. If the former or the latter are found to be either untestable or false, then the system as a whole will be inadmissible in a science-oriented ontology. It would seem that the least damning judgment on Lewis's metaphysics is that it does not help explore the actual world, because it does not even state any interesting falsities about it. The next negative evaluation is that, because the system says nothing specific about the actual world, no empirical evidence can be adduced either in its favor or against it. In fact, Lewis's system is worse than either trivially true or obviously false, it is utterly irrelevant because it is 234. Essentially fuzzy. To substantiate this charge, let us examine the above axiomatic reconstruction. To begin with, axiom 9.1 is inadmissible in any domain, because it conflates two radically different modes of being, logical, or conceptual, and real, or material. More precisely, it asserts that material, or real, existence is reducible to conceptual existence, which in turn equals someness. Such conflation is justifiable only in a system of objective idealism, such as Plato's, Hegel's, or Freya's. But it is untenable elsewhere. In logic and mathematics, something exists if it is well defined, whether explicitly or tacitly. For instance, an equation defines implicitly the numbers or functions that satisfy it, and a consistent system of postulates defines tacitly the object, S, it describes. By contrast, to prove the real existence of a hypothetical particle or field, we must have it interact with some observation or measuring instrument, we must show that it possesses energy of some kind. Recall Chapter 1, Section 7. For these reasons, the existential quantifier should be read for some rather than there exists. Recall Chapter 8, Section 4. Existence proper, the most important of all properties, is not to be formalized as a quantifier but as a predicate. There is good reason for this, namely, that existence is the most important property that anything can have. If in doubt, ask Hamlet. Consider Mening's puzzling albeit famous statement, "There are objects of which it is true that there are no such objects," Mening 1960. According to Van Inwagen, 2003, 141, what Mening seems to have had in mind is elucidating the second "there are" as an existential quantifier like this: exfx equals dfx, x has being and fx. Regrettably, Mening left has being undefined, and Van Inwagen did not fill this hole. I submit that the concept we need to dissolve Mening's paradox is that of existential predicate, Bunge 1977a, 155-6, explained in Chapter 1. That is, the problem is solved upon replacing the first occurrence of "there are" with "some," and the second with "exists in the world," or its equivalence is material, is changeable, or has energy. The result is some individuals do not exist really, or X, ERX, where ER is read exists in R, R being the name of a collection, world, of objectively real, material, objects. Axiom 9.2, on possibility, is likewise untenable. First, strictly speaking, it is false, because modal logic does not involve a unique concept of possibility, since there are 256 possible systems of modal logic. It would be a long, boring, and unrewarding task to find the sense or content common to all those different notions of possibility. Second, as everyone knows, not everything thinkable is really possible, and, as historians of science and technology know, we now admit many entities and events that were earlier regarded as impossible, or were not even thought about. Third, and most importantly, modal. 235. Logic cannot handle the concept of real, or physical, possibility, which scientists characterize as compatibility with the natural laws or social norms, because that theory does not contain that notion of an objective law or pattern. If only for this reason, the modal logics are utterly irrelevant to science. This is why they are never used in science, whereas the exact concept of probability is ubiquitous. Corollary 9.4 says that the difference between possibility and actuality is world relative. This result is more than puzzling, it is self-defeating, for it shows that the possible in possible worlds metaphysics is basically indistinguishable from actual. As for the definition 9.1 of a possible world, it is pathetically imprecise, because it specifies neither the nature nor the interrelations of the entities that may inhabit it. In particular, neither the Lewisian worlds nor their inmates are constrained by any laws. For example, they might contain perpetual motion machines of the first and the second kinds, in violation of the first two laws of thermodynamics respectively. This places modal metaphysics on the same bookshelf with fantastic literature, New Age thinking, and theology. According to definition 9.2, reality would be world relative. This is not so in science, where only concrete objects can be said to be real, and reality is absolute even though some properties and changes thereof are frame-dependent. For instance, a light wave emitted by an atom is absolutely real, although the value of its wavelength is relative to the frame of reference, it is velocity-dependent, Doppler effect. Besides, sometimes there are mismatches between reality and its perceptions. For example, when a fingertip is stimulated at two adjacent points, it is felt as a single stimulus in the middle. And one and the same political event, such as the passing of a bill or a government change, is likely to be perceived, evaluated, differently by members of different parties, but the event itself is single. In both cases, although the world is one, it is likely to be perceived somewhat differently by different subjects. Definition 9.3 is reasonable but, by the same token, it performs no work in a system designed to allow for any old world. It is like decreeing that dragons won't be taxed. The definition 9.4 of actual world suggests that the existence of the latter depends on that of myself. It is not clear whether this is a case of subjective idealism à la Fichte or Husserl, or at least of operationism. At all events, it is useless in science and technology. Finally, Theorem 9.1 prompts two remarks. First, it is not clear whether the infinity in question is actual or potential, that is, whether the infinitely many worlds are already there, where, or are in the making, by what mechanism, or else are just conceivable, by whom. Second, the theorem is trivial. 236. Since, where anything goes, there is no limit to the type or number of worlds. In fact, the theorem is so trivial that it is possible to program a computer that will design a potential infinity of worlds consisting of only two material points moving inside a box starting with different positions and velocities. Admittedly, the proposed rational reconstruction of a fragment of David Lewis's modal metaphysics is unlikely to satisfy any of Lewis's admirers, because my prose is far less elegant if more precise than Lewis's. But I hope it does what I wanted, which is to exhibit the roots, and the rot in them, of the metaphysical nightmare dreamed up by Lewis. Table 9.1 summarizes the main differences between Lewis's metaphysics and my own, Bunge 1977a, 1979a, 1981a. This table suggests that modal metaphysics is mired in confusion as well as being utterly at variance with science. In fact, it amounts to folk ontology plus modal logic. Lewis, 1973, 88, himself stipulated that the philosopher's task is to systematize his pre-philosophical, that is, uncritical, non-scientific, opinions. Still, the modal metaphysician will claim that his theory has a practical application, it allows one to make sense of counterfactuals, which in turn can be used to elucidate the key notions of causation and law. Let us examine these claims. 6 counterfactuals. A counterfactual is a sentence of the form if A were the case, then B would occur. Recall Chapter 8, Section 9. Example, if pigs could fly, we could eat leaner ham. It is tacitly understood that the antecedent of this subjunctive conditional is false. Everyone makes counterfactual statements, for instance, when drawing plans, expressing regrets, or assigning blames, as in if you had arrived in time, the accident would not have happened. But only some philosophers believe that counterfactuals can be true. And a few of them, starting with Chisholm and Goodman, have looked for truth conditions for. Table 9.1 Contrast between Lewis's fantastic metaphysics and scientific metaphysics. Key concept: modal metaphysics, scientific ontology. World: any old collection system of either things or constructs. Possibility: single concept, logical. Two concepts, conceptual and real. Real: thinkable. Material equals changeable existence. Single concept, two concepts, material and conceptual. Truth: single concept, vulgar. At least two concepts, factual and formal. Truth: values 0 and 1, all the values in the 0, 1 real interval. 237. Counterfactuals. Still, the various attempts to solve this problem met insurmountable difficulties, until it was announced that the solution was found. As McCall, 1994, 170, wrote, For many years those who studied counterfactuals wandered in the wilderness, until at last Stalnaker and Lewis showed us the promised land. This was the land of possible world semantics. The alleged solution boils down to this: in the case of flying pigs, if you want leaner ham, travel to the land of flying pigs. There, at that imaginary land or world, the indicative conditional "if pigs fly then their hams are lean" is true because, by stipulation, there is where pigs fly. I submit that the possible world solution to the problem of the truth value of counterfactuals is not only cost inefficient, but also rests on the presupposition that such sentences can have a truth value. This assumption is dubious for several reasons. The first is that counterfactuals are sentences that do not designate propositions without further ado. In this regard, counterfactuals are in the same league as wishes, interrogatives, and imperatives. A second reason that counterfactuals are neither true nor false is that no datum could serve to either confirm or undermine a counterfactual, since it fails to refer to real facts. A third reason is that counterfactuals, unlike ordinary conditionals, entail nothing. For example, if pigs flew they would be slender can be analyzed as the conjunction of the following two indicative sentences: if pigs fly then they are lean and pigs do not fly. But valid reasoning stops right here, for nothing follows from these premises. Still, one may learn something from analyzing counterfactuals in the way just indicated, which I proceed to render more explicit. Bunge 1968c. We are given the rhetorical expression "if A were the case, then B would be the case." 1. And translate it into the proposition "if A, then B." And not A. 2. Next, we check whether the conditional in 2 is plausible or not. If the conditional is a law, a norm, a robust trend, or is compatible with either, it can be said to be nomic, otherwise anomic. A nomic counterfactual only suggests a non-fact, whereas an anomic one suggests the violation of a law, norm, or trend, that is, either a miracle or the non-occurrence of a necessary condition for the law to hold. For this reason the nomic counterfactuals may be said to be reasonable, though not true, and the anomic ones unreasonable, though not false. A nomic counterfactual can be meek to the point of ridicule, or it may have some heuristic power, as when the assumption that an event did not really happen shows how important, or else unimportant, it was. An early example of the latter is Herodotus's evaluation of the Athenian. 238. Contribution to repelling the Persian invasion: what if the Athenian fleet had not been ready? Weber, 1906, 2 used counterfactuals to gauge the importance of certain events. A more recent example is Robert Fogel's research on the role of railways in the American economy at the time of the Gilded Age: what would have happened without them? His interesting conclusion is that the American economy would have attained roughly the same present level through the exclusive use of canals and highways, Fogel 1994. But of course there is no way of knowing for sure. Though unreasonable, some anomic counterfactuals can lead to discoveries. For example, if the second law of thermodynamics did not hold, life might have emerged spontaneously suggests removing the condition of system closure. Indeed, the said law does not hold for open systems, which of course are far more permissive than closed systems, and thus more propitious to qualitative novelty. Something similar holds for social norms, such as legal restrictions. For instance, were it not for this norm, we could lay our hands on that piece of property suggests either changing the law or breaking it. In short, whereas some counterfactuals are meek, others are subversive. Yet, ironically, the many worlds metaphysicians are hardly interested in alternative social worlds, they are politically aseptic. And still others, those that involve impossible worlds, are idle parlor games. Regrettably, the above distinction is lost on the many worlds philosophers who have attempted to analyze causation in counterfactual terms, see, example Collins, Hall, and Paul 2004. This strategy is understandable in a subjectivist perspective, but wrong in a realist one, where a causal link is an objective energy transfer, recall Chapter 4, Section 1. This is why scientists and technologists use counterfactuals only as heuristic, critical, or rhetorical devices, as when a politician states that everyone would be better off if the income tax were either cut or increased. In these cases one assumes a causal, in general, non-logical, analysis of counterfactuals rather than a counterfactual analysis of causal, in general, non-logical, relations. Proceeding in the reverse manner is like putting the cart before the horse. We shall return to this subject in section 7. In sum, counterfactuals are neither true nor false, since they cannot be put to the test. However, some counterfactual questions, such as those involved in thought experiments, do have a heuristic power. But, since this power depends on the truth of the pertinent law statements, norms, or trends, counterfactuals cannot elucidate, let alone validate, scientific hypotheses. This is why no scientific theory contains counterfactuals. These belong either in the heuristic scaffolding or in the rhetorical packaging, which is why their place, albeit a modest one, is in epistemology, not ontology. Serious ontology deals only with the real world, and it does so in the light of the sciences of this world. In other 239 words, serious metaphysics, by contrast to its speculative counterpart, is scientific, the way Peirce, 1935, had envisaged. 7. Disposition. Whereas fragility is a dispositional property, being broken is a manifest one. Crystal shops would not exist if there were no difference between dispositional and non-dispositional properties. In general, the features of concrete things, and their corresponding predicates, have traditionally been split into manifest, such as mass, age, and population, and dispositional, such as solubility, sociability, and carrying capacity. A property of a thing may be said to be actual or manifest if the thing possesses it, and potential or dispositional if emerges under suitable circumstances. Table 9.2 exhibits a sample of familiar properties of both kinds. Dispositions have elicited philosophical puzzle and blunder for over 2 millennia. For example, Aristotle and his followers liked dispositions, or powers, because they are central to their simplistic explanation of change as the transition from potency to act, as when Michelangelo claimed to see and extract the forms hiding in a marble block. By contrast, empiricists mistrust dispositions because they are unobservable. In fact, one may observe change, not mutability, bending, not elasticity or plasticity, speech, not linguistic. Table 9.2 A sample of manifest and dispositional properties. Manifest or actual, dispositional or potential. Actuality, real possibility. Relative frequency, probability. Mass, weight. Kinetic energy, potential energy. Refraction, refractivity. Radioactive decay, probability of radioactive decay. Sickness, predisposition to a sickness. Performance, competence, ability, intellectual output, intelligence, election, eligibility, action, feasibility, production, productivity, good deed, goodwill, social division, social mobility, saving, propensity to save, test, testability, truth, plausibility, verisimilitude. 240. Ability, creations, not creativity, dying, not mortality, production, not productivity, and good deeds, not goodwill. According to empiricism, fragility is not an actual property of a glass pane, but only a construct. We say that a glass pane is fragile only because, if it were struck or dropped, it would be likely to shatter. We shall come back to this intrusion of the troublesome subjunctive conditional, which we first met in the previous section. Scientists take the manifest/dispositional distinction for granted, and attempt to relate dispositions to one another as well as to manifest properties. For example, the fragility of glass is explained in terms of the buildup of internal stresses, the solubility of table salt is explained by the sharp weakening of the ionic bond due to the high dielectricity of water, whereas sugar dissolves by bonding with water. Predisposition to diabetes and other genetic diseases is explained by the occurrence of certain genes. Sociability is explained in terms of the inability of individuals to fend for themselves. The nature/nurture controversy is solved by posing that we are born able, not accomplished. Our intellectual dispositions may or may not be actualized, depending on the circumstances. Political instability is accounted for in terms of conflicts of interest between different groups, and so on. Consider, for example, the bending of a light beam when striking a transparent medium such as water or quartz. The refractivity of a transparent body is placed on the same footing as its mass and shape, even though it becomes manifest only when light shines on it. Actual refraction, a process, is described by optics, in particular by the Snell-Descartes law. This law relates the refractive index n, a dispositional property of all transparent media, to the angles of incidence I and refraction r n equals sin I sin r. Elementary optics treats the refractive index n as an empirical parameter. By contrast, classical electromagnetic optics analyses n in terms of the electric permittivity and the magnetic permeability of the transparent medium. The formula n2 equals relates all three dispositional properties in question. Electric permittivity is the propensity of a body to form electric dipoles under the action of an electric field. Magnetic permeability is parallel. The quantum theoretical explanation of refraction, though still electrodynamical, is far more detailed and accurate because it involves the interaction between the incoming photons and the outer electrons in the crystal's atoms. Incidentally, most transparent crystals, including ice, quartz, and calcite, exhibit birefractivity. That is, a light beam incident on such a crystal splits into two, so that the crystal has two refractive indices, two dispositions. Actually, multiple dispositions occur in many fields. For example, the sex of sea turtles is determined by the air temperature. And every one of us assumes different personalities and enacts different roles in different circumstances. 241. Interestingly, a disposition at the individual level may show up as a manifest property of an aggregate. For example, the probability of a radioactive decay is a property of individual atoms, or rather their nuclei, whereas a mean half-life, like any average, is a manifest property of a large collection of radioactive atoms of the same species. Likewise, genetic predisposition to longevity is a property of individual organisms, whereas average longevity, or life expectancy at birth, is a statistical or collective property. In general, real probabilities are dispositional properties of individuals, whereas statistical parameters, such as average, median, variance, and skewness, are manifest properties of collections. Let us now look into the explications of dispositionals proposed by some influential philosophers. Take, for example, carbon monoxide, or CO, well known for its toxicity. A naive empiricist is likely to say that CO is toxic as shown by uncounted fatalities. But of course this only confirms the assertion that CO is toxic. On the other hand, a sophisticated empiricist, particularly if influenced by the recent literature on counterfactuals, might say that CO is toxic because, if it were inhaled, it would poison. Again, this amounts to resorting to experience without explaining anything. A toxicologist will say something quite different, namely, that CO is toxic because, when inhaled, it combines with hemoglobin with a bond that is about 200 times stronger than with oxygen, and thus prevents the transport of oxygen to the brain and other organs, which die as a consequence. In general, we may say that a disposition, or dispositional property, is a property actually possessed by a thing that, under appropriate environmental conditions, generates another property. Ordinarily, the latter property is manifest or ostensive, whereas the former is not. The logical form of the scientific analysis of a dispositional property D is this: thing X possesses the dispositional property D equals D if X has the actual property A, and if thing X interacts with another thing Y, then X acquires the relational property P. We rephrase this as definition 9.5 X dx equals df X and Yp, Yx and Y is a thing and P is a property and Xe and Pxy. This analysis shows that a disposition, potentiality, or propensity, is reducible to two actual properties, one, A, intrinsic, and the other, P, relational, the former represented by a unary predicate and the latter by a binary one. No reference to parallel worlds is made. As usual in science and technology, it is taken for granted that one is dealing with the only world there is. However, potentiality or possibility has not been eliminated in favor of actuality, as it would have been if we had mistakenly equated D with A. Possibility has just been shifted from the thing in question to the thing in its environment. 4. 242. Example: sugar is soluble in water if and only if water dissolves sugar. More deeply, dissolution happens because sugar bonds with water, a clear case of interaction. Likewise, democratic political leaders or parties are powerful if they can mobilize a large sector of the population, which amounts to saying that a large sector of the population will rally around them. More deeply, democratic politicians will be able to influence public opinion to the extent that they are perceived, rightly or wrongly, as defending the interests of a large sector of the population. Besides, dispositions are deemed to be just as real as manifest properties. Consequently, nothing need be said about fantastic worlds. The preceding analysis applies to the dispositions that may be called conditional, because they actualize only under suitable circumstances. The quantum theory introduces unconditional dispositions that get actualized regardless of environmental conditions. Thus, the probability that an excited atom, atomic nucleus, or molecule, will decay spontaneously, without external stimulation, within the next time unit, is an unconditional property of the thing in question in the given state. The quantum conditional dispositions are similar to the classical ones in that they actualize when the suitable environmental conditions arise. But they are non-classical in that they involve blunt, or distributed, as well as sharp values of the dynamical variables, such as momentum and energy. Einstein believed that this feature of quantons, namely, that their dynamical properties only exceptionally have sharp values, contradicts realism. This is not so, because realism is not committed to any particular feature of things except their existence. Whether certain physical properties are manifest or dispositional, sharp or blunt, and so on, is for science, not philosophy, to determine. More in Bunge 1979c and 1985a. Let us take a closer look at this question. Ordinarily a quanton, or quantum mechanical object, is in a superposition, sum, of two or more, perhaps infinitely many, states corresponding to sharp energy values or eigenvalues. The same holds for the other dynamical variables. Every one of the sharp values has a certain weight or probability. Interaction with the environment, example a measuring device, will destroy the superposition or coherence, only one of the sharp possible values will get actualized. In other words, the quanton has a conditional disposition to acquire a definite energy value, and much the same holds for the remaining dynamical variables, such as momentum and spin. The quantum theorists know how to calculate the probabilities in question, but only a few admit that we do not yet know the details of the mechanism of the said collapse or projection of the state function. More in Bunge 2003d and 2003e. So much for the concept of a disposition. Let us now peek at the way scientists test for dispositional properties, on the non-empiricist assumption. 243. That meaning precedes test, not the other way round. To test for a disposition, such as refractivity, we need to relate it to a manifest property, such as actual refraction. But not every manifest property will do because, whereas a few manifest properties are directly observable, most are not. For instance, atomic mass, basal metabolism, family cohesiveness, and economic output are not directly observable. In each case we must look for a suitable observable property that can reliably be taken to proxy for, or indicate, the corresponding disposition. That is, we need to invent and confirm at least one indicator hypothesis of the form, D equals F, M, where M is an observable manifest property. In the case of refractivity, one such indicator hypothesis is the Snell-Descartes law recalled a while ago. In general, one uses the following criterion. 9.1 A thing possesses a property, whether manifest or dispositional, if the given thing, or a different thing connected with it, exhibits an observable property lawfully related to the former. Note the difference between the definition 9.5 of a disposition and the criterion 9.1, which parallels the existence test and the ontology methodology differences. Whereas the definition tells us something about the object of interest, the criterion instructs us how to check whether the object of interest actually possesses the property elucidated by the definition. For example, the ability of litmus paper to turn color when immersed in an acid solution can be used to tell whether a liquid is acid, and the dielectricity of bone marrow is used to diagnose leukemia, because the value of that disposition doubles in leukemia patients. The distinction between definition and criterion is typically blurred by empiricism, in particular operationism, or operationalism, as first described by Bridgman, 1927. The gist of this doctrine is the thesis, reminiscent of Berkeley, that to be is to be measured. An example is Carnap's, 1936-7, classical explication of a disposition, such as solubility, in terms of a subjunctive conditional referring to test conditions. Thus, thing B is pronounced soluble in water just in case, if B were put in water, B would dissolve. This empiricist account of dispositions is good enough for everyday life, but useless in science. First, like all operationist accounts, it conflates a property with the way it is tested for. That this is a confusion between ontology and methodology becomes even more patent in familiar cases such as the tuberculine test. Human subjects are attributed tuberculosis if they exhibit a positive reaction, inflammation, to a tuberculine injection. But of course such inflammation is only an indicator that the patient has been invaded by Koch bacilli. The tuberculine test makes no reference to these germs. Likewise, the litmus test of acidity makes no reference to pH, or hydrogen ion concentration. Second, the positivist explication of dispositionals involves subjunctive. 244. Conditionals, which are anything but logically clear items. Indeed, they are not propositions, hence they neither satisfy the propositional calculus nor have a truth value, recall section 6. No wonder that such conditionals play an ambiguous and therefore indecisive role in argumentation. On the one hand, they invite considering hitherto overlooked possibilities, as in counterfactual historiography, or what-if speculation. On the other hand, subjective conditionals offer cheap and untestable excuses, such as if Hitler had not been mistreated by his father, he would not have become a mass murderer. We conclude that there is nothing mysterious, let alone unreal, about dispositions, as long as they are handled as real possibilities, namely, in terms of laws. We also conclude that nothing is gained by attempting to elucidate problematic concepts, such as that of disposition, in terms of logical and epistemological outlaws such as counterfactuals. Let the latter remain where they belong, in the conceptual wilderness. 8. Space and time. One usually thinks of space as the great container, and of time as the silent river. However, when pressed, everybody seems to agree that these are just metaphors. Space and time are not concrete things, since they possess no energy, the peculiarity of material things, Chapter 1, Section 1. Furthermore, space, not being a material thing either, cannot contain anything, likewise time, not being fluid, cannot flow. This is why we have no direct experience of space and time. We can certainly feel spaced things, but not space. Likewise, we can sense successive events, but not time. Leibniz, 1956-1715. 2. 1083, put it into a nutshell, space and time are orders relations, not things. More precisely, according to Leibniz, space is the order of coexistence, and time that of successives. Hence, the scientific materialist adds, if there were no things there would be no space, and if nothing changed there would be no time. Moreover, for either to exist there must be at least two distinct items, two things in the case of space, and two events in that of time. This, the simplest case, can be described by the trivial metric space, where S equals AB and D, AB, equals 1 if AB, whereas D, AB, equals 0 if A equals B. Thus matter, space, and time, though conceptually distinguishable, in reality constitute a single block, the universe. As we shall see below, Einstein's theory of gravitation confirms this view. Hence, Newton's absolute, self-existing, space and time are only fictions. But they are useful fictions, since they allow one to sketch real things and their changes against a rigid spatio-temporal grid that does not alter along with any changing things, except in the vicinity of massive bodies. 245. At first blush, the immateriality of space and time defies materialism, and their lack of independent reality poses a challenge to realism. However, I submit that a suitable relational, or adjectival, theory of space and time, such as the one proposed earlier, Bunge 1977a, meets this challenge to both materialism and realism. Indeed, this theory, hinted at in antiquity and revived by Leibniz and a few others, postulates that space-time is the basic structure of the collection of all material things. Space is rooted in the separation between things, and time in the separation between events, relative to the same reference frame. So, spatiality and temporality are vicariously just as material, and therefore just as real, as the properties of the material objects that generate them, only, they have no independent existence. But then, things and the changes in their properties have no independent existence either, there are only mutually spaced things and successive changes in things, an excellent approximation far from black holes. For the relevance of these ideas to contemporary physics, see Green 2004. However, empiricists have trouble accommodating space and time in their doctrine. Because space and time are imperceptible, a consistent empiricist should either deny space and time, or try to construct them out of experiential terms. The first move, actually proposed by Sextus Empiricus, would be too extravagant even for most philosophers, the only noteworthy exception being the Hegelian John McTaggart, see Jammer 1954. The second empiricist project was attempted several times, notably by Whitehead, 1919, and Nicod, 1923, the latter under Bertrand Russell's supervision. But the theories of space and time resulting from this empiricist approach are subject-centered, and consequently useless in physics and engineering. Imagine a railway engineer letting himself be guided by the psychological finding that subjects perceive parallel rails as meeting in the horizon. And those theories are of no interest to psychology either, because they make no use of the experimental investigations into the perception of spatiality and temporality. And of course Kant's view that space and time are intuitions rather than features of the real world, cannot be taken seriously by anyone who has ever measured distances or periods. Nowadays we distinguish three different concepts of space. 1. Abstract spaces of many kinds and dimensions, such as topological, projective, Cartesian, like the state spaces, Euclidean, and Riemannian. These are the objects of so many mathematical geometries. Experience and measurement are irrelevant to these theories. 2. Physical space and time regarded as objective features of the world. They are the object of the physical geometries contained in certain physical. 246. Theories, notably Einstein's theory of gravitation. Unlike the mathematical geometries, the physical ones are expected to be validated by precision measurements. 3. Phenomenal, or experiential, spaces, such as the visual and auditory spaces of humans and other animals. They are studied by cognitive psychology, which has found that the human visual and auditory spaces are not Euclidean. The abstract spaces pose no special philosophical problems beyond the ones raised by any other mathematical abstractions. By contrast, the physical and phenomenal, or psychological, spaces, and the corresponding theories, do raise philosophical perplexities. The oldest and most important of them are the following three. First, what kind of object are space and time, stuff or systems of relations? Second, are they related to matter, and if so how? Third, are space and time real or unreal, objective or subjective? All these questions were addressed above. Our answer was, in a nutshell, a materialist version of Leibniz's relational theory: space, time, and matter do not exist by themselves. The universe is composed of spaced things, and time is the rhythm of their change. Thus, space and time are vicariously material and real, objective, just as much as change. This view is not nearly as popular as its opposite, namely Kant's. When Kant abandoned Leibniz's system as codified by Christian Wolff, he adopted a subjectivist view of space and time. These two would be intuitive preconditions of experience, which in turn would make up the world. Thus, subjective space and time experience the world. In 1770 Johann Heinrich Lambert, that remarkable polymath, wrote to Kant, in Kant 1913, Volume 1, 101-2, that it cannot be denied that real existence change, and, since change is real, so is time. Kant did not listen. 11 years later he repeated the subjectivist thesis in his first critique. The controversy over the reality or objectivity of space and time remained unresolved until 1915, when Einstein invented his theory of gravitation, general relativity. According to this theory, space and time are fused, though not confused, into space-time. And in turn the properties of the latter are determined by the distribution of bodies and fields other than the gravitational one, in accordance with the central equation of the theory, G equals T. Here G designates the geometric tensor, and T the matter tensor. If T equals 0 everywhere, that is, for a totally hollow universe, physics steps aside, and G equals 0 describes a family of purely mathematical spaces. In other words, T 0 somewhere describes real matter cum spacetime. So, neither matter nor space-time exists by itself. If preferred, both matter. 247. And space-time are real though not independently from one another. This then is the contemporary answer to the millennia-old question whether space and time are real. They are real, though not in themselves but as features of matter, in the broad sense of the set of changing things. Once again, science answered a key philosophical question. 9. Free will and liberty. Free will is of course the ability to do what one wants. More precisely, it is the ability to have feelings and thoughts, as well as to make decisions and take actions that, though constrained by external circumstances, are not caused by them. In psychological jargon, free will is behavior, internal or overt, that is not stimulus-bound. A clear example is the refusal of a prisoner, soldier, or priest to obey orders at grave risk. Another case of free will is creativity, the invention of ideas that go beyond or even against sensory stimulation. Einstein, 1949, 49, 1950a, 60, understood the theoretical concepts required to account for reality as free creations of the human mind. They are free in the sense that they are independent of sense perceptions even when exceptionally triggered by the latter. Incidentally, this was one of Einstein's main objections to the positivists, their prejudice against such free creations. Free will violates of course the central tenet of Pavlov's reflex theory, the Watson-Skinner stimulus-response behaviorism, and Gibson's ecological psychology. By the same token, free will violates the narrow version of causal determinism, according to which only external stimuli count as causes. But it is consistent with causality lato sensu, since the implementation of any decision involves causal links such as those connecting events in the prefrontal cortex with events occurring in the neuromuscular system. Hence, free will is not to be defined as overcoming causation. Nor is free will definable as unpredictability, which is an epistemological and methodological category. Theologians and philosophers have debated for 2 millennia whether free will is real or fictitious. The problem is of great theoretical and practical importance, because it is about whether humans can take initiatives, break away from some environmental constraints, and even revolt against the terrestrial and celestial powers that be. Some theologians need free will to be able to legislate on sin and evil, as well as to justify the cruel punishments raining from above, and moral and legal philosophers need free will to make sense of autonomy and personal responsibility. However, regardless of these needs, the ontological and scientific question is whether free will is really possible. Idealists have no problem admitting free will, because the immaterial soul is assumed to escape the laws of nature. By contrast, vulgar materialists, Fissy. 248. Callists, nominalists, reject the free will hypothesis because they conceive of humans as complex systems abiding by the laws of physics and chemistry, none of which seems to make room for spontaneous or self-initiated processes. On the other hand, emergentist materialists admit the possibility of free will, and the concomitant self-consciousness, as results of evolution. Indeed, evolution involves the emergence of new kinds of things, satisfying laws absent from the lower levels of organization. For example, neurons can fire and associate spontaneously, not just in response to external stimuli. Since volition is a mental ability, and since everything mental happens in the brain, to find out whether free will is for real we must shift the focus from theology and speculative philosophy to the study of the human brain. In particular, we must look at its prefrontal cortex, which is known to perform the so-called executive functions. The first modern scientist to attack the free will problem, and to state that it can be solved by neuropsychology, was Donald O. Hebb, 1980. He argued that Kayal's anatomical investigations, as well as electroencephalographic data, had showed that the brain is more than a relay between receptors and effectors, that it is continuously active, even during sleep, and it always adds something to the input signal. Hebb's own research on sensory deprivation confirmed those studies. It showed that external stimulation distorts the ongoing brain activity, but is not its only source. We can experience desires and images, and form intentions and plans, in a spontaneous fashion, that is, in the absence of external stimulation. Since free will is control of behavior by thought, Hebb, Ibid. 139, and since not every thought occurs in response to external causes, free will is biological fact, not illusion. Of course, it can be either attenuated or enhanced by education and social circumstances, but not more so than other mental abilities and processes. Which brings us to our next subject, the possibility of liberty. The social counterpart of free will is liberty. This is the feature of a social order that enables individuals to do what they want. However, liberty is bounded, and what can be had of it comes at a price. It is not only that, as Thomas Jefferson said, the price of liberty is eternal vigilance. It is also the fact that not everyone can afford to be totally free, nor should anyone so feel, to do exactly what he wants. In fact, even in the freest of societies, individuals have obligations, particularly those of respecting other people's liberties, and of sharing the burden of maintaining the social order that ensures them. Besides, in deeply divided societies only the members of the ruling minority have the wherewithal required to enjoy security, clean air and water, beautiful landscapes, and access to higher culture. Moreover, liberty, like any other value, is part of a package or system. No. 249. Value can be realized in isolation from all other values. In particular, no one can be free in a community of utterly selfish individuals unwilling to lend a hand when needed, and this for the simple reason that no one, not even the autocrat, is self-sufficient and omnipotent. The revolutionaries of 1789 had it right: liberté, égalité, fraternité. I venture to add idoneité, that is, technical competence, for without it even the best intentions are unlikely to come to fruition. Sadly, everyone knows that none of the societies currently in existence realizes the liberty, equality, solidarity, competence ideal. Does this prove that we should stop dreaming up utopias? Hardly. It only goes to prove that so far we have been unable to educate and mobilize people to work, rather than fight, for that ideal. 10. The word transcendental has earned a bad reputation because it has all too often designated otherworldly items. However, it is a legitimate name for anything that transcends, overreaches, experience. So, it applies not only to deities but also to fictions, electrons, nations, and things. Moreover, some transcendental items, such as possibility, disposition, and space-time, are indispensable to account for concrete things and their changes. They are needed because they have real counterparts. For example, biological species are collections, not concrete individuals, but they are not arbitrary or conventional sets. Likewise, although the law statements are abstract objects, they represent real patterns. In general, the universals are in re rather than anti-rem or post-rem. 250. 10. From Plato's cave to Galileo's hill. Realism vindicated. Although philosophical realism is practiced by all sane people, anti-realism flares up once in a while, even in such unexpected quarters as marketing and management. In particular, realism is one of the bêtes noires of postmodernism, that bulldozer of everything that is good about modernity, in particular, trust in reason and the search for the true, the good, and the right. Hence, if we wish to stop that bulldozer, we must defend philosophical realism among other things. The philosophical realism I advocate is a comprehensive doctrine. Indeed, it is a system with 7 components: ontological, epistemological, semantic, methodological, axiological or value theoretic, ethical, and practical. Here is an abbreviated formulation of the 7 constituents of integral philosophical realism. R. Ontological: R equals the external world exists by itself. Epistemological: R equals the external world can be known. Semantic: R equals external reference and factual truth. Methodological: R equals reality checks and scientism. Axiological: R equals objective as well as subjective values. Ethical: R equals moral facts and moral truths. Practical: R equals efficiency and responsibility. Note the absence of 2 realisms from the above list, political and aesthetic. The former, realpolitik, is a synonym for the unprincipled struggle for power. It is political cynicism and expediency leading to barbarism. As for aesthetic realism, it is so broad a category that it embraces the best literature as well as the conservative, academic, visual arts. The confusion of philosophical with aesthetic realism led Lyotard, 1980, 77, the inventor of the word postmodern, to proclaim the lack of reality, a postmodern gem. Integral philosophical realism is a system, or organic whole, rather than a 251 set of disconnected opinions. Thus, practical realism is the thesis that action should be efficient, as well as consistent with a modicum of morality, if only because immoral action is ultimately self-defeating. Ethical realism promotes addressing real-life moral problems with the help of the relevant scientific or technological knowledge. An axiology is realist insofar as it deals with both objective and subjective values, and justifies the former with the help of solid knowledge and cogent arguments. A methodology is realist if it adopts the strategy that scientists and technologists actually use to study or alter reality. A semantic theory is realist if it contains a theory of reference that allows one to find out what predicates and propositions refer to, and adopts the correspondence view of factual truth. An epistemology is realist if it makes contact with cognitive psychology and shows that the scientific exploration of the universe presupposes ontological and epistemological realism. Finally, the realist ontologies assume the independent, i.e., subject-free, existence of the universe. The reverse stream, from theory to praxis, is equally strong. Indeed, realist ontologies support an epistemology that encourages the study of the real world, distinguishes primary from secondary properties, and discourages fruitless speculations about impossibilia such as disembodied spirits and parallel worlds. In turn, a realist epistemology elicits a semantics that starts with semantic theories of reference and factual truth. Such semantics encourages a methodology centered in the scientific method, and consequently it admits the subject/object dichotomy, and encourages an account of secondary properties in terms of primary properties. The conjunction of realist methodology, semantics, epistemology, and ontology suggests a realist axiology that regards valuation as a process occurring in a brain immersed in a social network. In turn, such an axiology invites the realist construal of moral norms as rules to tackle objective moral issues. And a realist ethics suggests a practical philosophy that helps tackle practical problems both efficiently and in accordance with moral principles. Let us now proceed to arguing for all 7 branches of philosophical realism. 1. Ontological realism, brain and history. Ontological realism is the thesis that the universe, or reality, exists in seet per se, in itself and by itself. Only a tiny part of reality, namely, the human social world, emerged, subsists, and changes because of us and for us, but its existence does not depend on the knowing subject. In other words, the subject, knower, or explorer, is a real thing surrounded by real things, most of which have pre-existed him and did not require his assistance to come into being. 252. And, once they arise, the social inventions or constructions are just as real as the mountains. We shall privilege 4 arguments in support of ontological realism, those from physics, biology, cognitive neuroscience, and history. The first argument is that all the basic physical laws, such as Newton's second law of motion, Maxwell's triplets, and Schrödinger's equation, are invariant under certain changes of reference frames, in particular observers. Only the derived law statements, such as Galileo's law of falling bodies and the law of the Doppler effect, may be frame-dependent. But reference frames are special physical systems, not necessarily manned ones, see Bunge 1967b. The argument from biology is that all organisms, even bacteria and subjectivist philosophers, draw nourishment and energy from their environment, and are equipped with sensors of external signals. This is why organisms die if totally isolated from their environment, and face high risks when their sensors malfunction. In short, we are constitutional realists, tenured professors of philosophy accepted. The third argument, first proposed by Condillac in 1754 with the help of his famous imaginary statue, boils down to this. Odor comes from smelling some external thing or from remembering such experience. The other 4 classical senses work similarly. Proprioception was unknown at the time. Kondelik's argument may be updated as follows. The mental functions are brain processes, some of which represent external events. For example, olfaction is a long and complex causal chain that can be summarized thus: volatile molecules in the subject's environment, chemical receptors on the cilia of olfactory sensory neurons, olfactory bulb, olfactory cortex, other brain regions, in particular the organs of emotion. The first and last links of the olfaction chain may be missing, olfactory hallucinations may occur, and we may not be aware of subliminal olfactory stimuli. Likewise, the blind may detect shadows without perceiving them consciously. In short, sometimes the brain detects external stimuli, though not always consciously. And at other times the brain generates illusions or hallucinations, it hears voices, feels phantom limb pain, has religious and out-of-body experiences, and so on. Only a confrontation with harsh reality can correct our wrong representations of it. The brain could not exist without the world surrounding it, from which it draws not only nourishment but also the stimulation required for its normal development and functioning. The role of the environment in the development of the normal brain was shown experimentally by Hubel and Wiesel, 1962, in a famous experiment that earned them the Nobel Prize. This experiment consisted in surgically closing an eye of a newborn kitten, and removing the 253 stitches after 12 weeks. The result was that the cat never developed depth vision because the stripes of the primary visual cortex corresponding to the blind eye were invaded by neurons in the same area stimulated by the intact eye. In short, the genome does not suffice for normal development, stimulation by the external world is needed too. Another well-known case is that of individuals who become blind after birth. Their hearing improves because some of the neurons formerly attached to vision are drafted by the auditory area. In short, environmental stimuli contribute powerfully to the development of the brain. When such stimuli are screened off, the brain ceases to develop or function normally. Indeed, Hebb's classic experiments on sensory deprivation in humans have shown that, in the absence of external stimuli, the subject hallucinates and loses count of time. In other words, bracket out the world, the way Husserl recommends to capture the essences of things, and you are likely to go crazy. Thus, Hilary Putnam's mythical brain in a vat would not only be solipsistic, it would also be quite deranged. Certainly, no two individuals see the world in exactly the same way, for no two brains and no two life histories are identical. Still, all persons, even the severely autistic, agree that there are certain things around them, such as trees, buildings, and other people, that exist on their own. And emotionally salient and surprising events, such as gunshots and plane crashes, are likely to be perceived correctly by everyone within earshot. Moreover, in perceiving such events, different brains have been found to tick synchronically. Thus objectivity, or at least intersubjectivity concerning sensory stimuli, seems to be hardwired in the brain. Most of the individual differences concern intellectual and moral matters. So much for the argument from cognitive neuroscience. Finally, the argument from history consists in pointing out that all of the historical sciences, from cosmology and geology to evolutionary biology and historiography, take the past for granted. Moreover, they assume that no study of the past can alter it. True, every generation of historians rewrites historiography. The same holds for students of the evolution of the universe and its constituents, from molecules to rocks, organisms, and social systems. The reasons for scientific, not ideological, historical revisionism are well known. The historical record is incomplete, new evidence has been unearthed, new methods have been invented, new hypotheses have been suggested, or whole new philosophies of history have been proposed. In short, historians cannot alter the past, they only try to fill lacunae or correct mistakes in previous accounts of what happened. Only a social constructivist could affirm that the past, not just its study, is a social construction, but he does not bother to offer any evidence for this. 254. Bizarre claim, other than confusion between the past, history, and its descriptions, historiographies. For example, after canvassing the opinions of a number of American historians, Novick 1988 concluded that historical objectivity is nothing but a noble dream. Travel to the past is physically impossible, and history is irreversible. If we could tamper with the past, we would alter the present without moving a finger, something that not even the occultists dare promise. 2. Epistemological realism, kicking and exploring. Epistemology deals with the subject-object relation. It is expected to tell us some generalities about cognition and its object. See, example Bunge 1983a and 1983b. Actually, epistemology is multiple rather than one. There are as many epistemologies as ontologies, realist and irrealist, materialist and idealist, and so on. Epistemological realism may be compressed into one definition and 6 theses. The definition is this: an item is real if it exists independently of the subject or knower. Note that this definition cannot double as a reality criterion, for it does not tell us how to find out that the object persists while we are not looking. Ordinarily, to find out whether a given item is real, or else a figment of our imagination, we watch whether it influences something else, or whether we can act effectively upon it. For instance, Boswell tells us that Samuel Johnson claimed to have proved the reality of a stone by kicking it and feeling pain in his foot. However, Berkeley might have rejoined that the kick just proved that the stone was there only because Dr. Johnson had perceived it. Kicking, then, is not decisive, except for scoring soccer goals. Besides, in most cases we cannot act upon a thing to find out whether it exists really. For example, we cannot kick the sun, let alone the Milky Way or the universe as a whole. Seeing the sun is certainly a mighty clue, but not one that would satisfy Berkeley. We accept this sensory evidence because we can hide from sunshine, and also because we can explain the process that ends up in our perception of the sun, photons emitted by the sun retina optic nerve visual cortex. That is, we accept a visual sensation as evidence for the independent existence of external visible things because we can explain the causal chain that goes from the sun to the brain. In sum, kicking and observing a reaction is highly suggestive but not sufficient to certify the reality of an entity. So much for the definition and the criterion of reality. Let us now state the theses of our scientistic version of epistemological realism. 255. 1. Reality is scrutable, or, better, it is possible to know some facts, though usually only partially and gradually. Realism does not require exact truth, our knowledge may be only rough and sketchy. Moreover, accuracy is not always more valuable than insight, tractability, and testability. Thus, a rough but deep, mechanismic, model is a better exploratory tool than a highly accurate but shallow black box. 2. Indirect knowledge is the deepest, it is attained via theories and indicators rather than through mere perception or instant intuition. This thesis opposes direct realism, that is, the empiricist opinion that we do not need reason to get to know anything. This opinion does not even hold for knowledge of everyday matters, since all cognition depends upon past experience, expectation, attention, and conjecture. For example, the paleontologist sees fossils strewn among rocks that are likely to escape the layman. Time passes more slowly when we pay attention to external events than otherwise, and understanding someone's behavior requires reading his mind, that is, conjecturing some of his thoughts. 3. Fallibilism, we are bound to err sometimes, we may employ deficient techniques, make false assumptions, simplify excessively, or elicit false data. Fallibilism is of course the skeptical ingredient of epistemological realism. This ingredient, absent from naive realism, is the mark of critical realism. For meliorism, given any piece of knowledge, in principle it is possible to improve on it, to make it more comprehensive, accurate, or deep. Meliorism moderates the impact of fallibilism, it prevents us from falling into the barren trap of radical skepticism. And it is not an article of faith. An analysis of the simplifying assumptions involved in constructing any hypothesis and in designing any experiment suggests that, by removing any such fictions, more accurate results should be obtained. 5. Moderate pluralism. In principle, any set of facts can be represented by alternative hypotheses or theories. And, whereas some rival constructs are equivalent in some respects, others differ in accuracy, generality, or depth. 6. Objective knowledge, backed by solid evidence and sound theory, is far superior to subjective hunch. For instance, knowing that the defendant in a murder case was abroad at the time of the murder, demolishes whatever suspicion his police record or the color of his skin may have elicited in a juror. Incidentally, objectivity or impersonality must not be confused with intersubjectivity, or consensus about a matter of knowledge. The reason is that consensus can be reached through manipulation or coercion, regardless of 256. Evidence or argument. In science and technology, intersubjectivity, or even consensus, is a bonus of objectivity and rational discussion. Typically, phenomenology, feminist philosophy, Bayesianism, pseudoscience, and postmodernism replace objectivity with either subjectivity or intersubjectivity. For example, two prominent Bayesian theorists announce, "We can find no real role for the idea of objectivity except, perhaps, as a possibly convenient, but potentially dangerously misleading, shorthand for intersubjective communality of beliefs." Bernardo and Smith 1994, 237. Objectivity differs also from both value neutrality and impartiality, three concepts that Max Weber, 1988b, conflated in his influential position paper. Indeed, one can be objective yet at the same time have certain preferences, for instance, truth over falsity, democracy over dictatorship, or equity over inequity. Likewise, objectivity is compatible with partiality. As Rescher, 1997, 43, put it, being objective about determining the facts does not demand being prepared to welcome them as is and refusing to try to change the conditions of things that they represent. Partisanship is to be avoided only if it interferes with either fairness or the search for truth, as when the free trade mantra is sung as the panacea for national development, even though the relevant statistics show that it only favors the economically and politically powerful. What may be called the explorer's argument is this: anyone who endeavors to explore a territory or investigate a concrete thing, event, or process assumes that it exists or may exist. Thus, the physicists who attempt to find Higgs bosons with the help of high-energy particle accelerators, assume that it is really possible for such particles, postulated by a theory, to exist. Likewise, the evolutionary biologist who digs for a fossil intermediate in age between two known fossils assumes that the missing link may exist. And the archaeologist who looks for human remains or traces of work near a ruin assumes that the people who made them are likely to have existed. All explorers hope to confirm their hunches, they are not falsificationists a la Popper. In particular, miners dig for gold, not to falsify the hypothesis that there is none in the plot they have staked. What will an explorer think if he fails to find what he was looking for? Either that the hypothesized thing never existed, or that it is somewhere else, or that it got destroyed or stolen. In the first case he will have falsified his hypothesis, but in the other two cases he may entertain the hope that someone else, equipped with better instruments or truer ideas, will confirm his hypothesis. In either case, the explorer assumes that some of the things he took for granted or assumed are out there. This is why archaeology, evolutionary biology, and geology are not armchair occupations. As for cosmology, it is certainly a theoretical discipline, but one motivated and checked by astronomy. 257. Caldata, and these in turn are about celestial objects that exist or have existed in reality. 3. Semantic realism, reference and correspondence. I submit that semantic realism is the view that, a. some propositions referred to, are about, facts, and, b. some factual propositions are true to some extent. Thesis, A, is rejected by the textualists, in particular the deconstructionists, such as Derrida, according to whom every symbol refers to other symbols. And radical sceptics, Puranists, reject thesis, B. Everyone else subscribes to both theses. But not everyone realizes that the key concepts the theses involve, those of reference and truth, are highly problematic. Most semantic theories, in particular possible world semantics, fail to elucidate the concept of reference. They do not help finding out what a speaker is talking about. They also confuse reference with extension, as when Ptolemy's epicecles are said to be non-referential, whereas Kepler's orbits are regarded as referential. As a matter of fact, or rather logic, all propositions are referential even if they are undecidable or about nothingness. Thus, fairy tales refer to fairies. And tautologies, logical truths, refer to anything at all. Since they are content-free, they do not depend on specific reference. Bunge 1974c. Note the difference between reference and representation, see Bunge 1974a. Although tautologies, conventions, and statements in pure mathematics have referents, whether precise or nondescript, they do not represent anything in the real world. Thus, a definition of velocity refers to a moving thing but does not represent any feature of it. On the other hand, the statement that particles cannot attain the speed of light represents a property of things endowed with mass. See Table 10.1. My theory of reference, Bunge 1974a, posits that the referent of a simple statement, of the form B is A, P, is B, the referents of a proposition of the form B and C are related are B and C, and the reference class of a molecular statement, such as P and Q, and if P, then Q, equals the union of the partial reference classes. This semantic theory allows one, in particular, to identify the referents of theories of uncertain referents, such as relativistic and quantum mechanics. It can be shown that these theories refer exclusively to physical things, that they make no reference to observers. Bunge 1967b. The way to proceed is to analyze the key concepts in the postulates, such as the Schrödinger equation. This formula specifies the effect of the Hamiltonian, or energy operator H, on the state function. By hypothesis, H represents the energy of the thing or things in question, such as a proton and an electron joined by their electrostatic interaction in the case of a hydrogen atom. Neither experimental devices nor observers are mentioned in H. Hence H refers 258 exclusively to the microphysical entities assumed in writing it. The same holds for the state function. Anything else is philosophical contraband. As for truth, most philosophers agree that it can only be predicated of propositions, that is, the objects designated by sentences. It may be argued that diagrams and pictures too may be more or less true, but we shall not pursue this possibility here. However, philosophers are notoriously divided on this question. Besides radical scepticism, there are no truths, and relativism, all truths are local or tribal social constructions. The main views on truth are the following. 1. Redundancy, or deflationary, theory. The concept of truth is redundant. That is, to state P is the same as to assert the truth of P. 2. Coherence theory. A proposition is true in a body of propositions if and only if it is consistent with the remaining constituents of that body. In particular, an abstract proposition, such as the operation is associative in S, is true in a system if and only if either, A, it is satisfiable, or has a model or example, or, B, it is deducible from the basic assumptions, postulates, of the system. Obviously, the concept of truth as coherence applies only in mathematics. 3. Correspondence theory. A factual proposition is true if and only if it corresponds to, represents, the facts it refers to. Peirce, 1986, 282, put it thus: truth consists in the existence of a real fact corresponding to the true proposition. More precisely, a factual proposition is, factually, true if and only if it has been empirically confirmed, or if it is entailed by propositions that have passed the empirical tests. This concept of truth as correspondence applies to ordinary knowledge, factual science, and technology. Table 10.1 Some conceptual objects represent items in the real world in a more or less faithful, true, fashion, whereas others refer but do not represent. Still others, such as string theory, are still in limbo at this time. Conceptual items real world. Model things things. Attributes properties. Singular propositions facts. Law statements patterns. Conventions. Logic. Mathematical fictions. Metaphysical fantasies. Falsities. 259. The correspondence theory is usually taken to assume that every factual proposition has a precise truth value, and is moreover true or false, whether or not we know it. This claim strikes me as unrealistic, because factual truth values can be legitimately attributed only on the strength of truth tests. If no such test can be performed, the corresponding proposition lacks a truth value. Examples: A. It was snowing in Montreal when Christ was born. B. Christ's last thought was that all his disciples scuttled away when he was arrested. C. Some Corinthians must have replied to the epistle that St. Paul addressed them. See Figure 10.1. Unlike stars and cells, whose properties are subject-independent, propositions are constructs, not givens with objective properties. We construct, evaluate, and modify all propositions. Hence, a pinch of constructivism is justified with respect to constructs, provided it is not of the voluntarist kind. Since propositions are evaluated in the light of more or less rigorous tests, their truth value, if any, may change in the course of research rather than being innate and constant. See Bunge 1967a. Only Platonists, naive realists, and those who confuse truths with facts are entitled to pretend that propositions are true or false from birth and remain so forever. So far we have dealt with the propositions of ordinary knowledge, factual science, and technology. How about moral propositions? If we grant that there are moral facts, such as wars, and therefore moral truths, such as it is wrong to wage war if unprovoked, then we may admit the following definition. A moral proposition is true if a. It follows from higher moral principles, such as enjoy life and help live, and b. Its implementation contributes to lessening misery. The moral postulates meet trivially condition a. Because every proposition entails itself. Let us now evaluate the three views of truth sketched above. According to the redundancy theory, saying that P is true does not add anything to P. For instance, it is obvious that snow is white is true if and only if snow is white. The redundancy thesis has been defended by such famous philosophers as Frege. Figure 10.1 Factual truth values derive from truth tests. Hence, untested propositions have no truth values. Test. Fact, S. Represents. Proposition truth value. 260. Wittgenstein, Ramsey, Eyre, Strawson, and Quine, in addition to many younger scholars, see Horwich 1990. The redundancy thesis about truth is false for the following reasons. A. It does not distinguish between a truth claim, of the form P is true because of Q, and a groundless pretense. B. It fails to distinguish between different kinds of truth, such as formal and factual. C. It only concerns low-level statements that can be confronted directly with reality, such as the cat is on the mat, but it fails for high-level statements, such as Newton's laws of motion, which require deductions, indicator hypotheses, and sophisticated empirical procedures. D. It draws no difference between making a statement and justifying it. E. It does not distinguish between making a statement for the sake of argument, in which case one does not assign it a truth value, and asserting it either as postulate or as theorem. F. It makes no room for partial truths, such as the earth is spherical, hence for statements of the form P is truer than Q, much less for any of the standard procedures of successive approximations, and g. It does not allow us to state methodological norms such as abstain from attributing truth values to untested propositions and prefer the truest of all hypotheses. In conclusion, we should keep the distinction between a statement and the various meta-statements that can be made about it, in particular those of the form the truth value of P is such and such. This distinction is particularly important when we mistakenly assert a falsity or deny a truth. Such distinction becomes a matter of life and death when interpreting the outcomes of medical tests, as in the case of false negatives. Next in our list comes the coherence view, usually dubbed theory. This thesis is obviously correct with regard to logic and mathematics, particularly whenever truth can be equated with provability. But the thesis leaves us in the lurch in the cases of ordinary knowledge, factual science, technology, and the humanities. For example, the great majority of scientific theories, though presumably consistent, have proved to be at variance with the facts, which is why they have been corrected or rejected. This shows that consistency is not enough. In any domain dealing with facts we need agreement with, or adequacy to, the pertinent facts in addition to internal consistency and external consistency, or compatibility with other pieces of the background knowledge. The correspondence theory of truth refers only to factual statements, such as empirical data and scientific hypotheses. It captures the intuition that factual truth, unlike formal truth, consists in adequacy to reality. In everyday life, science, and technology we first assert tentatively a proposition, then check it for truth, and finally, with luck, we pronounce it true. This will be the case if the proposition in question represents correctly the facts it refers to. However, the correspondence theory has the following flaws: a. It is a vague thesis. 261. Rather than a theory proper or hypothetico-deductive system, b. It does not tell us what negative and general propositions correspond to, c. It makes no room for partial truths, and d. It leaves external consistency, systemicity, out. Still, all of the above defects can be corrected, at least in principle, see Bunge 2003a. The corrections result in a fourth and last candidate, the synthetic theory of truth. This embryonic theory may be compressed into a definition and a criterion of factual truth. The definition is this: the proposition P asserting fact F is true if and only if F occurs. This definition is the so-called correspondence theory of truth, adopted tacitly by nearly everyone. Of course, it is rejected by the subjectivists, because they deny the very existence of objective facts to be represented in the brain. Finally, the criterion of factual truth is this: a. P is compatible with, and exceptionally equivalent to, the relevant evidence, and b. P is consistent with the bulk of the pertinent background knowledge. Notice the above distinction between the definition and the criterion of truth. The former tells us what truth is, and the latter suggests how to identify it. This difference underlies the use of indicators, such as the frequency of Geiger clicks as a measure of radiation intensity, and corticosterone level as a measure of stress. Failure to distinguish between truth and evidence for it is the source of some varieties of anti-realism. One of them is the holistic and pragmatist claim that there is no bridge between our theories and the world they claim to describe, because those theories would only describe the relevant evidence. Davidson 1984, Clough 2003. Such confusion between reference and evidence amounts to conflating stars with telescopes. The same conflation is also inherent in the so-called verification theory of meaning, characteristic of the Vienna Circle and operationalism, and also recommended by Davidson. This theory is obviously false. Measurements and experiments can tell us whether a hypothesis is true, not what it means. Moreover, meaning precedes test, if only because we must know what a hypothesis is about before designing a test for its truth. Further criticisms in Bunge 1967a, 1974a, and 1974b. A more popular variety of anti-realism derived from the failure to distinguish the concept of truth from its criterion is the neo-positivist replacement of true with confirmed. Putnam, 1981, 64, once adopted this doctrine and rechristened it internal realism. According to it, a true statement is a statement that a rational being would accept on sufficient experience. For example, every morning the Aztecs confirmed their belief that the previous day's human sacrifices made the gods bring back the sun. Clearly, Putnam confused the concept of factual truth with the empirical truth criterion. 262. So much for the statement of our version of semantic realism. Let us now propose some arguments for it. The most popular of them is this: there must be something out there if a theory about it turns out to be true. This argument is particularly persuasive if the existence of the thing in question was predicted by the theory in question, as in the cases of Neptune, electromagnetic waves, positive electrons, neutrinos, and hominids and other extinct organisms. What if the evidence pertinent to a theory is unfavorable to it? This may be either because the theory is false while the evidence is firm, or because the theory is true while the evidence is not. Only further empirical or theoretical work may settle the question. The postulated entity may turn out not to exist. This will be a tragedy for a beautiful theory, but not for realism. The existence of the universe is always presupposed rather than questioned. Paradoxically, an even stronger support for semantic realism is the argument from error, Bunge 1954. Indeed, the very concept of a scientific error, whether conceptual or empirical, presupposes the real existence of the entity or feature in question. For example, we know that the figures for unemployment rates are only approximately true, because many unemployed get discouraged and stop going to labor exchanges in search for jobs. In other words, there are jobless out there who have not been counted. At other times we count twice what is actually a single thing, as is the case with the double images created by gravitational lenses. Realism thus accounts for both error and its reduction. It explains scientific and technological progress as a product of our effort to improve the description and explanation of the outer world. True, some irrealist philosophers admit the possibility of improving scientific theories, but they are likely to hold that it is meaningless to inquire into the absolute correctness of a conceptual schema as a mirror of reality. Quine 1953, 79. However, they do not bother to elucidate how improved theory differs from truer theory. Worse, they cannot perform such elucidation because, lacking the concept of objective truth, they cannot employ that of error as discrepancy between theory and reality. Some realists, such as Popper, 1972, make much of scientific progress, but declare the success of science to be miraculous, and therefore unexplainable. Putnam, 1975, has correctly argued that the success of science would be miraculous if its theories were not at least approximately true. But phenomenalists like Van Frassen, 1980, and pragmatists like Lawton, 1981, have claimed that we should not talk of miracles or even of truth. Success would suffice. But what does success mean in science other than truth? The Nobel Prize is not awarded to saints for performing miracles, nor is it awarded to successful engineers, businessmen, or politicians. It is only awarded to science. 263. Scientists who have found, discovered or invented, some important truths about a part or feature of reality. Science does not and could not possibly prove realism, because every scientific proposition, whether datum or hypothesis, refers only to facts of a particular kind. Science does more for realism than confirming it, it takes realism for granted. In other words, scientists and technologists practice semantic realism even if they occasionally pay lip service to an anti-realist philosophy. They presuppose both the independent existence of the world and the possibility of producing objective truths about some of it. So do laymen when going about their daily business, mindless of the subjectivists, conventionalists, pragmatists, and constructivist relativists, all of whom deny the possibility of objective truth. More on this in Durkheim 1988-1901, Weber 1988b 1904, Lenin 1947-1908, Einstein 1950a 1936, Popper 1956, Sellers 1961, Smart 1968, Kuth 1978, Trigg 1980, Newton-Smith 1981, Agassi 1990, Stove 1991, Brown 1994, Siegel 1987, Vasher 1991, Nyanalato 1999, and Hunt 2003. To appreciate the centrality of truth in daily life, imagine two lands, Analetheia, whose inhabitants deny truth, and Anapistia, whose citizens deny falsity. Both place names have Greek roots. Aletheia f means truth and apistia falsity. The Anapistians hold that anything goes, whereas the Analetheans maintain that nothing goes. The former are too open-minded, that is, gullible, whereas the Analetheans are excessively closed-minded, that is, radical skeptics. Of course, the natives of both lands contradict themselves when holding that their own views are right, but they do not realize this. Nor can they debate one another, the Analetheans, because they have no convictions, and the Anapistians because they see nothing wrong in whatever their counterparts may claim. Worse, the Analetheans cannot use any truths to shape their own lives, and the Anapistians unwittingly use falsities galore. Consequently, life in both lands, like that of Hobbes's primitives, is nasty, short, and brutish. Not to worry, though, because in the real world all Analetheans and all Anapistians are college professors who earn sheltered lives teaching radical skepticism, constructivism, or relativism, instead of working hard to try and find new truths. 4. Methodological realism, reality check and scientism. Methodological realism amounts to both the demand for reality checks, empirical tests, and the adoption of scientism. A reality check is of course the confrontation of a proposition, in particular a hypothesis, with the pertinent. 264. Empirical data and pertinent theories. Note that this is not a direct confrontation of a proposition with the fact that it refers to, but with a datum about it. Whereas a proposition cannot be compared with a fact, it can be contrasted to another proposition. See Figure 10.2. As for scientism, it is the thesis that the scientific method is the best strategy for attaining the more objective, more accurate, and deepest truths about facts of any kind, natural or social. This was the central thesis of the famous speech delivered by Condorcet, 1976, in 1782 to the Académie Française. Scientism has since been a key principle of both positivism and scientific realism. In fact, it is the main bone of contention between the pro-science and the anti-science camps. True, Hayek, 1955, famously claimed that scientism is something quite different, namely, the attempt on the part of some social scientists to ape their colleagues in the natural sciences, in ignoring the inner life of their referents. But this arbitrary redefinition involves confusing naturalism, or reductionist materialism, as practiced, example by the sociobiologists, with scientism. For the standard definitions of both terms, see, example Lalonde 1938 and Bunge 2003b. The opponents of scientism hold that subjectivity cannot be studied scientifically. This is not true. Psychology is the scientific study of the mind, Heb 1980. The proponents of scientism admit of course the difference in both subject matter and special techniques between the sciences of the inner and the outer worlds. But it also holds that these differences are no obstacle to using the same general method in all of the sciences, and this for the following reasons. All existents are material, all investigators have similar brains, and they all share the goal of finding objective truths about patterns as well as particulars. This thesis is sometimes called methodological monism. A merit of methodological monism is that it allows social scientists to use some of the techniques and findings of the natural sciences, as when social psychologists make use of neuroscience. Another is that it renders the biosocial sciences, demography, anthropology, psychology, linguistics, etc., POS. Fact indicator observation. Figure 10.2. A factual hypothesis refers to a fact that, when under observation, is somewhat different, and is the referent of a datum or piece of evidence. Hypothesis confrontation evidence. Reference 265. Seibel, whereas the natural/cultural dichotomy stemming from Kant overlooks them, see, example Bunge 2003a. The usual argument for methodological realism is the success of the scientific method. This is certainly a strong argument. But what about the failures of the scientific endeavor, particularly in psychology and the social studies? It might be argued that any particular failure only suggests that there was some flaw in the application of the scientific method, for instance, that the sample was either too small or not random, that the experimental design overlooked certain variables, or that a single line of evidence was used when the complexity of the matter required employing multiple lines. However, such excuses are unlikely to persuade the scientific skeptic. The skeptic about the reach of the scientific method might be swayed by the hermeneutic argument that the cultural, or social, sciences, unlike the natural ones, attempt to understand social facts in terms of meaningful behavior rather than to explain them. Regrettably, the hermeneuticists do not elucidate their slippery notion of meaning, although from the context one suspects that they mean intention or goal. If this is the case, then the hermeneutic thesis in question is false, since cognitive neuroscience studies intentions as processes in the prefrontal cortex. Social psychologists and sociologists use the scientific method to investigate goal-seeking behavior, and social technologists, such as management scientists, social workers, and legislators, attempt to steer behavior. Nor is it true that the social sciences are bound to explain the familiar by the familiar, as the intuitionists, phenomenologists, ethnomethodologists, and the doctrinaire partisans of the Verstehen, understanding, approach hold. The serious social scientist is likely to go beyond common sense knowledge, and is thus bound to cast doubt on much conventional wisdom, as well as to come up with some counterintuitive hypotheses. Let the following examples suffice to shore up the thesis that social scientists have found some counterintuitive generalizations. The more similar, the fiercer the competition. Ecological law: rebellion occurs not when oppression peaks, but when it starts to slacken. Alexis de Tocqueville: free trade favors only the powerful. Colonialism ends up by impoverishing the colonial powers as well as the colonies. John Hobson: and the spread of higher education lengthens the jobless queues. Raymond Budden. Each of these counterintuitive hypotheses can be supported not only by statistics but also by unearthing the pertinent mechanism. For example, the more similar two groups of organisms, the more needs they will share, and thus the closer their niches. Counterintuitiveness is of course even more pronounced in the natural sciences. Just think of the paradoxes. Counter 266. Intuitive hypotheses, of relativistic and quantum physics. To hold that science does not differ radically from everyday knowledge, just because both make use of empirical evidence, Hawk 2003, is beside the point. The point of engaging in scientific research is to build and check theories about factual items inaccessible to common sense. Ordinary knowledge, even enriched with logic and empirical evidence, equals ordinary knowledge. To sum up, scientific hypotheses are expected to be testable, and moreover to undergo tests if found interesting. And scientism, far from being an ideology, as Hayek and Habermas have claimed, is no less than the epistemic engine that has been driving all of the sciences since the early 1600s. 5. Axiological realism, objective values. The conventional wisdom about values is that all of them are subjective, that value lies only in the mind of the evaluator. Accordingly, there would be no objective and true value judgments. This is the opinion of the axiological nihilists, such as Nietzsche, of the emotivists, such as Hume and the logical positivists, and of the intuitionists, such as G.E. Moore and Max Scheler. By contrast, axiological realists hold that, whereas some values are indeed subjective, Others are objective because they are rooted in biological or social needs, see Bunge 1989 and Budin 2001. For example, whereas beauty may well be only in the eye of the beholder, security and peace are objective social goods. That the preceding is not a dogma but an objective truth is suggested by the fact that insecurity and war put life at risk and therefore drag all the other values down. In other words, axiological realism rejects the dogmatic view that values must be accepted blindly either because they have a supernatural source or because they are purely a matter of feeling or intuition. Axiological realists are not intimidated by G.E. Moore's branding of the attempt to join value to fact as perpetrating the naturalistic fallacy. Rather, realists regard the fact/value dichotomy as a supernaturalist or irrationalist fallacy. However, value objectivism does not entail value absolutism. First, one and the same item may be objectively valuable in some respects but disvaluable in others. For instance, riding a good bicycle is good for the body but it tempts thieves, and giving alms may make one feel good but it postpones social justice. Second, some values have to be restricted in order to secure others. For example, not all knowledge is valuable, thus, knowing the sex of a human fetus may lead to aborting female fetuses. Besides, some values are bound to conflict with others. For instance, privacy calls for limiting the right to know. Values may be individual or social. Individual values may be defined in 267 terms of individual needs and desires. Anything that contributes to meeting a basic need, such as food, shelter, or company, may be said to have a primary value. A secondary value is anything that contributes to satisfying a legitimate desire, that is, one whose satisfaction does not prevent anyone else from meeting his basic needs. For a finer partition and a quantitation see Bunge 1989. The social values, such as security, social cohesion, democracy, progress, and peace, promote individual welfare and peaceful social coexistence. However, sometimes they conflict with individual values. For example, security may conflict with liberty. However, such conflicts are best solved through negotiation and compromise rather than by coercion. In any case, the social values are just as objective and important as the individual objective values. Finally, scientism suggests that values, whether subjective or objective, can be investigated and defended or attacked on scientific grounds instead of being handed over to ideologues. For instance, artistic appreciation has been investigated experimentally, example Berlin, et 1974, Zeki 1999, basic needs are being investigated by physicians and social psychologists among others, and policy scientists are expected to design policies aiming at defending certain objective values. Thus, axiology should be regarded as straddling philosophy, science, and technology. 6. Ethical realism I. Moral facts and moral truths. Ever since Hume, most philosophers have adopted ethical subjectivism or relativism. Consequently, they have held that there are no moral facts, and that therefore moral statements are neither true nor false. That is, the ethical tradition is irrealist. Let us put this tradition to the test in two typical cases, those of theft and altruism. I submit that the actions of both kinds are moral because they affect the persons at the receiving ends. And at first sight, the corresponding norms, don't steal and help the needy, can be neither true nor false. However, they are true if the moral norm try to help others is postulated. So far, all may look rather clear and simple. But it is not quite so, because the norms in question have duals, or counter-norms, regarding mitigating circumstances, as is the rule with all social norms, see Merton 1976. Thus, we usually postulate that lying and stealing are wrong, except when human life is at stake. Likewise, we set limits on altruism, we do not normally require helping others at the risk of one's own life. In both cases the facts of the matter are placed in context, and so are the corresponding moral principles. In a situational or systemic perspective, then, lying, stealing, and helping others without expecting reward are moral facts. 268. And the norms and counter-norms attached to those facts are true because they match the maximal moral principle: enjoy life and help others live enjoyable lives, Bunge 1989. In other words, the moral norms should be placed in social context rather than be separated from it, since they are to be used in real life. This is a requirement of moral realism, the view that there are moral facts and therefore moral truths as well. Though at variance with mainstream ethics, in particular with Kantianism, emotivism, and standard, subjective, utilitarianism, moral realism has been gaining currency in recent years. See, example Lovenbond 1983, McGinn 1985, Bunge 1989, and Rothschafer 1998. However, in many cases this view has been presented as a byproduct of the philosophy of language, or rather linguistic philosophy. Hence, this variety of moral realism is unlikely to appeal to any thinkers who regard words as conventional. Moreover, some moral realists, such as Platt, 1979, are intuitionists, hence distant from rationalism as well as from empiricism, and others, such as Wiggins, 1976, write about the meaning of life. But no one who takes science and technology seriously, and regards them as inputs to philosophy, can condone intuitionism, and genuinely analytic philosophers distrust musings about the meaning of life. Still other moral realists, particularly Brink, 1989, profess ethical naturalism and objective utilitarianism. However, naturalism, unlike emergentist materialism, is untenable, since moral rules are social, hence partly artificial, as well as biological, or psychological. And utilitarianism does not account for the well-known fact that we often make sacrifices without expecting reward. For these reasons, I will presently sketch a different variant of moral, or rather ethical, realism. According to the correspondence theory of factual truth, the thesis that there are moral truths and falsities presupposes that there are moral facts. In turn, this presupposes that moral truths are just as factual as the truths of physics, biology, or history. Now, the vast majority of philosophers deny that there are moral facts. Harman 1977, Nino 1985, and Rothschafer 1998 are exceptions. They base this denial on the fact-norm dichotomy usually attributed to Hume. Let us peek at the latter. Hume was certainly right in asserting that what ought to be is not the same as what is, that norms are not of the same kind as factual propositions. However, I submit that he was wrong in holding that the value/fact gap is unbridgeable. He was mistaken because we move daily from the one to the other, namely, when taking action. For instance, if I tell myself that I must pay my debt to someone, and proceed to paying it, I cross the gap between ought and is. Likewise, when I take note of an unjust situation and attempt to remedy it, I go the other way. 269. In other words, is and ought are undoubtedly distinct, they are separated by a conceptual or logical gap. But in practice this is just a ditch that we can jump over through action. Moreover, it is a ditch that not only conscious beings can cross. It can also be crossed by any artifact endowed with a negative feedback device capable of leading the system from its current state to the final state judged valuable by the operator or user. Furthermore, I suggest that every fact involving rights or duties, whether met or not, is a moral fact. For instance, poverty is a moral fact, not only a social one, because poverty involves unnecessary suffering and degradation. This is why it elicits moral emotions, such as compassion and shame. Involuntary unemployment is a moral fact too, because it violates the right to work, the source of all legitimate income necessary to meet basic needs and legitimate desires. Analogously, job creation is a moral fact, not only an economic one, because it satisfies the right to work. Another case of moral, or rather immoral, fact is the dumping of toxic waste, and this because it violates the right we all have to a clean environment. For the same reason, dragging a water body to remove toxic waste is a moral fact. In short, life in human society is packed with moral facts, and therefore with moral problems that can be tackled with the help of factual and moral truths. How should moral facts be identified or individuated? One option is to use this definition: a fact F is moral equals F poses a moral problem to some person in some culture. In turn, a moral problem is an issue whose examination and solution calls for, among other things, the invention or application of moral norms. And of course the latter pose ethical and meta-ethical problems, which may have solutions leading to altering some moral precept. In turn, such change may have an impact on individual behavior and therefore on the original moral problem, for example, in contributing to either solving or worsening it. The moral facts and our moral, ethical, and meta-ethical reflections on them are then components of a feedback loop. In the end, then, moral truths resemble the truths of science and technology. But of course the two differ in an important respect. Unlike the latter, the former are contextual, situational, or relative. Indeed, since moral truths concern in the last analysis rights and duties, and since these are relative to a culture and its moral code, moral truths are contextual. In this regard, and only, moral fact, moral problem, moral principle, S. Modified moral principle, S. Meta-ethical problem, S. Ethical problems. 270. In this, moral truths resemble mathematical truths, in that they hold in some theories but not in others. However, this context dependence of moral rules is not absolute. It does not involve the total relativity defended by the anthropological relativists and the social constructivists. This is so because all viable moral codes share certain principles, such as those of respect of the other and reciprocity. In other words, some rights and duties are basic, hence cross-cultural and non-negotiable, while others are secondary, and therefore local and negotiable. The right to enjoyable and non-harmful life, and the duty to help the needy when no one else can, are absolute and universal, whereas property rights and religious duties are not. The natural law theorists, whether secular like the ancient Stoics or religious like Thomas Aquinas, deny of course this partial relativity of the moral norms. In fact, they hold that all moral rights and duties are natural and therefore universal or absolute, that is, context-free. But since as a matter of fact some moral codes do not admit certain rights and duties enshrined in alternative codes, the natural law theorist cannot hold that the corresponding propositions are universally true. And if he nonetheless insists on his claim, then he cannot hold that such moral truths correspond to any facts. Instead, he must either state that they are just as formal as the mathematical theorems, or he must adopt a non-realist theory of truth. Given these difficulties, the natural law theorist will perhaps take refuge in the traditional opinion that moral norms are neither true nor false, but only effective or ineffective, just like cooking recipes or medical prescriptions. But if he adopts this instrumentalist, or pragmatist, stand, he relinquishes the right to call himself a natural law theorist. In short, moral facts are social, not natural, they belong to the fabric of society, not to that of nature. Moreover, those facts are artificial, that is, made, not found, they do not occur in the absence of moral agents. For example, there are still people among us, even Harvard law professors, who justify torture, the death penalty, and military aggression. This is why moral naturalism, or the view that morals are in our genes, is false. Morality is made and learned, not found, or inherited. This is why it can be perfected or degraded, as well as be made the object of legislation. Like any other social facts, moral facts can be perceived, evaluated, differently by different people, or by the same persons under different circumstances. Interestingly, all such perceptions can in principle be objectified, that is, they can be detected by impartial observers. For example, Rilling and co-workers, 2002, found that the reward, or pleasure, brain centers of experimental subjects playing a prisoner's dilemma light up when they cooperate. 271. With the experimenter. That is, it feels good to do good deeds, unless one has been educated in the hard school of mainstream economics, for which selfishness is the supreme virtue. That is partly why we often help others without expecting reciprocity. Experimental economists found long ago that small-scale business transactions involve a moral factor ignored by standard microeconomic theory. Thus Kahneman, Nitschke, and Thaler, 1986, S299, wrote, a realistic description of transactors should include the following traits. 1. They care about being treated fairly and treating others fairly. 2. They are willing to resist unfair firms even at a positive cost. 3. They have systematic implicit rules that specify which actions of firms are considered unfair. Another empirical finding that falsifies the dogma that people act always only in their own best interests, that is, rationally, is the following. From a rational, selfish, viewpoint, it is obvious that whoever punishes someone else should not expect altruistic cooperation on the victim's part, regardless of the fairness of the sanction. However, this is not the case, that is, fairness can make all the difference. Indeed, the experiments of Fair and Rockenbach, 2003, suggest that sanctions perceived as fair make no dent on altruism, whereas sanctions revealing selfish or greedy intentions all but destroy altruistic cooperation. In short, the utilitarian philosophers, neoclassical economists, and sociobiologists have been wrong in disregarding the moral factor or in construing altruism as enlightened selfishness. Experience and experiment show that common decency, fairness, and loyalty do matter in transactions of all kinds, even in business deals among strangers. So does unilateral generosity. Most of us spend time giving directions to strangers, tip waiters even when abroad, give to charities, prefer to deal with firms that treat their employees fairly, and boycott firms, products, and entire countries suspected of being morally tainted. I submit that all such facts are moral facts. If there are moral facts, then there should be moral truths. Certainly, most philosophers do not even entertain the possibility of moral truths corresponding to moral facts. In some cases the overlooking of this possibility is ultimately due to their thinking of moral principles or norms as imperatives, of the type of "thou shalt not kill." And although an imperative may or may not be pertinent, efficient, or good, it can be neither true nor false, because it neither affirms nor denies any matters of fact. This objection overlooks the fact that the linguistic wrapping of an idea is superficial because conventional. Indeed, any ordinary knowledge idea may be expressed in different ways in any language and, a fortiori, in different languages. The writer ordinary excludes mathematical, scientific, and techno. 272. Logical ideas, these require symbols that, though conventional, are fairly universal. Since there are several thousand living languages, it is possible to give thousands of translations of any non-technical statement. In particular, any moral imperative may be expressed by a sentence in the indicative mood, with hardly any loss of content or practical value, in particular psychological or legal. For example, "Thou shalt not kill" can be translated into "killing is evil, murder is the worst sin, it is forbidden to kill, if you kill, expect to be punished," and so on. The first two translations designate a proposition that holds, is true, in any moral code that affirms the right of all persons to life, and false in any code that does not admit such a right. Note that the principle in question holds tacitly only for persons, not for human embryos or for non-human animals. As for the legal counterpart of the moral principle in question, that is, it is forbidden to kill, it holds, is true, in the criminal codes that do not equate justice with revenge. In short, it is possible to propositionalize any given imperative. Such propositionalization is necessary to find out the truth value, or the truth conditions, of moral maxims. Once a translation of an imperative into an indicative has been performed, one should proceed to a second translation, one in terms of rights and duties, or else virtues and vices, or good or bad consequences of an action. For example, help thy neighbor can be translated into it is good to help your neighbor, or helping one's neighbor is good. The truth of this maxim becomes obvious upon expanding it into if you take your neighbor's interests into account, or wish to count on her in an emergency, or wish to be at peace with yourself, you'll help her likewise. The precept saving is virtuous while waste is not is true in a world suffering from increasing scarcity. The fact that almost all economists recommend increasing spending during recessions, while decreasing it during periods of expansion, only suggests that they are as amoral as short-sighted. The methodological rule that holds for moral truths also holds, of course, for moral falsities. For instance, the thesis that what is good for the economy is good for the individual is false because the economy can be stimulated in the short term by spending on superfluous or even noxious commodities, such as sports cars and weapons. Likewise, the maxim what is good for the government, or the corporation, church, or party, is good for all is false every time the government, or the corporation, the church, or the party, overlooks the welfare of the majority. Now, if there are moral falsities there must also be moral lies, that is, sentences expressing what the speaker knows to be moral falsities. For example, the claim that there are inferior human races is not only scientifically 273 false, it is also a moral falsity because it has been utilized to justify the exploitation or oppression of certain ethnic groups. And, whereas the statement of a moral falsity may be a mere error, that of a moral lie is nearly always sinful. The exception is of course the white or pious lie told to avoid unnecessary suffering. 7. Ethical realism. 2. Testability of moral norms. If all the moral norms, whether universal or local, concern moral facts, then it must be possible to subject them to empirical tests. I submit that a moral norm other than the maximal moral rule is justifiable if, and only if, a. it fits a moral fact, b. it is consistent with the supreme postulate of the moral code in question, and c. it is effective in promoting processual conduct. The maximal moral norm is the benchmark against which all the other components of the code are gauged. And it is justifiable by its logical and practical consequences. Much the same holds for the axioms of a mathematical or scientific theory, they can only be justified by their consequences. I submit that the moral norms can be tested in 3 different though mutually complementary ways. The first test is that of coherence, that is, compatibility with the higher level principles. The second is that of compatibility with the best available relevant knowledge, ordinary, scientific, or technological. The third test is that of the contribution to individual or social welfare. Let me explain. The moral norms, just like the scientific hypotheses and techniques, ought to be compatible with the highest level principles, in this case the moral and metaethical maxims of the system in question. In the case of Agathonism, the maximal principle is enjoy life and help others live an enjoyable life. Any rule that facilitates the implementation of this principle will be deemed to be morally correct, otherwise incorrect. Example of the former, take care of yourself, your kin, and your neighbor. An example of the latter kind is any rule leading to negative discrimination on the ground of age, sex, race, class, or religion. By contrast, positive discrimination, as in affirmative action, is justifiable when it corrects unfair imbalances. The second of our tests is that of compatibility with the best available knowledge. For example, we should discard any rule that ignores positive moral feelings, such as compassion, or negative moral feelings, such as shame and envy. The same holds for any rule that overlooks the fact that moral rules are social constructions, and that their implementation is likely to affect individual action and therefore human relationships. For instance, a rule that 274 commands human sacrifices to a divinity is not only cruel, it is also inconsistent with modern knowledge about myth and social convention. The third and last of our tests is that of efficiency. Evidently it consists in finding out whether the given norm facilitates or hinders the realization of the basic underlying values, such as those of survival and self-government, and the freedoms to love and learn. In this regard, the moral rules resemble the rules of modern technology, both are based on laws, and both are tested by their efficiency in reaching certain goals. Furthermore, the efficiency of moral rules, like that of the technological ones, can be estimated by the scientists and socio-technologists who study or control human conduct. A moral rule is good only if it is efficient on top of aiming at contributing to individual or social welfare. But, in order to be efficient, a rule must start by being viable, which in turn presupposes epistemological realism. For example, if threatened, levitate is not a viable rule. However, even if a moral rule were to pass all three tests, it should be regarded as perfectible. Centuries of scientific and technological experience, not to mention social experience and philosophical critique, ought to dissuade us from chasing infallibilist mirages, in particular that of a perennial ethics fashioned for perfect humans in the perfect society. We ought to have learned by now that no moral code and no ethical theory can guarantee right conduct. We may only hope to improve on the existing moral codes and ethical theories through conceptual analysis and comparison with empirical data. For example, we must reject moral positivism, as well as legal positivism, for being both relativist and conformist. Such ethical fallibilism is far from natural law, moral intuitionism, and the ethical doctrines attached to religious dogmas. Still, unless accompanied by meliorism, fallibilism is destructive. I suggest that we can and must seek moral and ethical progress through theoretical work and social action, voluntary as well as institutional. The abolition of slavery, torture, and the death penalty, as well as other progressive reforms of the penal code, are instances of real moral progress. Ethical meliorism may be justified as follows. First, morals co-evolve with society, and moral philosophy evolves along with the rest of philosophy as well as with the social sciences and technologies. Second, if we try we may discover and correct moral deviations and ethical mistakes, although sometimes either calls for some intellectual or even civic courage. Take for instance the slogan "Freedom or Death," shouted since ancient times by uncounted freedom fighters, ideologists, and nationalist politicians. At first sight all friends of liberty ought to embrace it. But on closer inspection one realizes that the precept in question ought to be optional. To begin with, even a slave's life may be worth living, particularly if it allows for some hope of 275. Emancipation. Second, no one, not even the state, has the moral right to force anyone to fight till death for any cause. Third, the price exacted by any war without quarter can be staggering, not only because of the number of casualties but also for making the life of the survivors more difficult. The above slogan is justified only in two cases: when there is solid evidence that the enemy won't give quarter and when the price of personal liberty is treason. What is the status of moral axioms? Are they wishful thoughts, commandments, conventions, or testable hypotheses? Our preceding discussion points to Einstein's view, 1950b, 8 ethical axioms are found and tested not very differently from the axioms of science. Die Wahrheit liegt in der Bewahrung. Truth is what stands the test of experience. In the cases of moral norms and ethical principles, the relevant empirical data concern human welfare. For this reason, the biological and social indicators, such as life expectancy, infant mortality rate, number of school years, and median disposable income, are more relevant to moral norms and ethical principles than are academic discussions on moral mini-problems or pseudo-problems, such as those posed by blasphemy, masturbation, homosexuality, abortion, in vitro fertilization, sex change, gay marriage, clonation, or suicide. All of these pale by comparison with war, misery, and tyranny, see Waddington 1960. Assuming that we have solved the problem of validating moral rules, what can we say about testing ethical theories, that is, systems of ideas about the nature, root, and function of moral norms? I hold that such theories are testable much in the same way as scientific and technological theories, that is, by their agreement with the relevant facts and their compatibility with other theories. Let me explain. I submit that any ethical theory should meet the following conditions. 1. Internal consistency, non-contradiction. 2. External consistency, compatibility with the bulk of scientific and technological knowledge about human nature and institutions. 3. Ability to account for viable, livable, moral codes. 4. Usefulness in suggesting social reforms necessary for the exercise of free and enlightened moral judgment. 5. Usefulness in analyzing moral and ethical concepts and principles. 6. Usefulness in identifying and tackling moral problems, and in settling moral conflicts. The condition of internal consistency does not apply to stray ethical opinions, such as Machiavelli's or Nietzsche's immoralism. The condition of 276. External consistency disqualifies ethical emotivism, such as Hume's and the Vienna Circles, and ethical intuitionism, such as Moore's and Skeeler's, since these views overlook the rational and empirical inputs to all moral deliberations. The same condition disqualifies utilitarianism, for it ignores the reality of moral feelings, such as empathy and shame, and it makes use of subjective values and subjective probabilities. It also disqualifies all the non-consequentialist ethical theories, in particular Calvin's and Kant's. The fourth condition disqualifies naturalism, or vulgar materialism, for it ignores the social root and social efficiency of morals. The fifth disqualifies all of the moral doctrines associated with philosophies hostile to logical analysis, such as intuitionism, phenomenology, existentialism, and dialectical materialism. And the sixth disqualifies all of the moral doctrines that are but arbitrary inventions of intellectuals far removed from social reality, which, alas, has been the case with most moral philosophers. Let us wind up our discussion of moral realism. The thesis that there are moral facts and moral truths has at least three consequences. First, if there are moral facts, then the moral principles are not dogmas but hypotheses, as Ingenierose, 1917, and Einstein, 1950b, proposed. And, being hypotheses, they must be confronted with the relevant facts, and revised if they do not match them. However, it does not follow that moral facts are just as inevitable as astronomic events. Whether or not such facts happen depends on us, moral agents. Second, if there are moral facts, then moral judgments are not totally subjective and relative. Rather, on the contrary, it is possible to evaluate such judgments in the light of experience, as well as to discuss them rationally. Moreover, it is possible to adjust action to morals and conversely. In particular, it is possible and desirable to reform society so as to minimize the frequency of destructive moral facts such as crime, war, oppression, and exploitation. Third, if the moral and ethical principles are empirically testable hypotheses, as well as guides for individual and collective action, then it is possible and desirable to reconstruct moral codes, as well as ethical theories, in a rational manner. In particular, it is possible and desirable to reconstruct morality and its theory in such a manner that the following conditions be met. 1. Realism, adjustment to the basic needs and legitimate aspirations of flesh and blood people placed in concrete social situations. 2. Social utility, ability to inspire prosocial conduct and progressive social policies, as well as to discourage antisocial ones. 3. Social plasticity, adaptability to new personal and social circumstances. 4. Equity, efficiency in the task of decreasing social inequalities, though without imposing uniformity. 277. 5. Compatibility or coherence with the best available knowledge of human nature and society. In sum, there are moral facts and moral truths. The former are part of the fabric of reality, and moral truths intertwine with other factual truths. Consequently, moral realists are expected to assume social commitments, that is, to practice morality in addition to teaching it. 8. Practical realism, efficiency and responsibility. Praxeology, or action theory, is the branch of practical philosophy concerned with deliberate human action. In its narrow construal, praxeology seeks to determine the conditions for efficient action regardless of moral considerations. Von Mises 1966, Kotarbinsky 1965, Gaspersky 1993. I submit that, since our actions may affect others, we should try to foresee their consequences and assume responsibility for them, a duty that the ethical non-consequentialists exempt themselves from. Not to do so is unrealistic, because it involves leaving out an important component of the outcome of anyone's actions. The obvious consequence for praxeology is that it should include responsibility and accountability along with efficiency. In other words, a realist praxeology presupposes a realist morality. Further, it is doubtful that there can be general efficiency conditions. Indeed, maximizing the output/input ratio of any artifact, whether physical, biological, or social, requires the study of the specific actor/object interface. Thus, it is not the same to design or construct an efficient engine, an efficient factory, or an efficient school. This is why the study of efficiency is a task for engineers, management scientists, ergonomists, and other technologists, rather than a task of action theorists. The most advanced and popular of all action theories is rational choice theory. According to it, every action, or at last every rational action, is undertaken freely and in the light of a cost/benefit calculation, and it obeys the utilitarian imperative maximize your expected utilities. See, example Becker 1976. This theory, born in neoclassical microeconomics, has spilled over other social sciences, and even ethics. Regrettably, rational choice theory is conceptually fuzzy because neither of its two key concepts, those of subjective probability, perceived likelihood, and subjective utility, pleasure, is mathematically well defined. See Eichner, ed. 1983 and Bunge 1996. Besides, the theory is empirically untenable because, a. most events in ordinary life are not random, hence they cannot be assigned probabilities proper, recall chapter 4, b. most problems in daily life are solved by following ready-made rules, without resorting to sophisticated cal. 278. Culations, c. real-life actors are seldom free, and they are never omniscient, and, d. normal people are constrained by social and moral norms. Consequently, rational choice theory is not a realistic guide to life. To go back to the scope of praxeology, I submit that philosophers are not equipped to design efficiency rules. What philosophers can do is to analyze the system of concepts centered in the notion of action, as well as to link praxeology to ethics. Here we shall only sketch a few such ideas insofar as they relate to the realism requirement. See Bunge 1998 for details. I suggest that a good action is one that satisfies two conditions, the technical condition of optimal efficiency, and the moral condition of being more beneficial than harmful. As a rule, optimal lie midway between minima and maxima. The reason is that the variables that describe a system are interrelated, so that when one of them increases others are bound to decrease. In particular, we should not aim for maximal efficiency, because it is bound to sacrifice other values, such as welfare and environmental protection. But, of course, we want to limit overall waste. Utilitarians disregard the moral aspect of action, but of course this aspect is taken into consideration by anyone who respects other people's rights. Now, every human action is bound to affect other people, as a rule positively in some respects and negatively in others. Hence, before doing something important we should estimate the costs and benefits of the action in question to self and others. For example, before preaching the virtues of globalization, or free trade, we should find out how to correct or compensate for the increasing imbalances that it generates. Optimally efficient design and implementation implies ontological, epistemological, and semantic realism. Indeed, an irrealist approach to action guarantees practical failure because of flawed design, incompetent execution, or both. And right action implies moral realism, the view that there are moral, and immoral, facts and rules. In fact, moral anti-realism, in particular the view that morals are subjective, leads to overlooking the rights of others, hence the harm that action may cause them, and the actor by reaction. Let us finally glance at one aspect of praxeology, political philosophy. This is the branch of practical philosophy that studies the merits and demerits of the various historical and possible social orders, and the ways to perfect or undermine them. A realist political philosophy is expected to have two roots, a realist praxeology and a realist social science. Both roots are necessary to avoid costly failure. Political science teaches that political action can only succeed if its underlying strategy is based on a realist study of the polity in question, one that, through statistics, opinion polls, and public debates, exhibits flaws, aspera. 279. And possibilities. It also teaches that, while the vast majority of people favor reform, only elites opt for revolution. There are two reasons for this preference of ordinary folks for evolution over revolution. One is that most people wish to get on with their lives rather than devote themselves to a risky cause. The other reason is that all social action is likely to have unanticipated consequences, some good but others harmful, and small mistakes are easier to repair than big mistakes. Social reform, however, is not the same as piecemeal social engineering. Indeed, sociology suggests that sectoral social reforms are bound to fail, because society is constituted by many interdependent sectors or subsystems rather than by a single one, such as the economy, the polity, or the culture. In other words, only systemic, or integral, political programs may succeed, and this provided they win the support of ample sectors of society rather than appealing only to a sect. Thus the correct slogans, study reality before attempting to change it, and try to improve everything at once, though gradually rather than abruptly. More in Bunge 1998. In short, to improve on a ghastly social reality while avoiding both utopia and dystopia, we should design social policies and plans based on both realist social studies and moral means-goal pairs. See Figure 10.3. 9. Scientific hylorealism. Realism is essential to the empirical exploration and transformation of reality. The reason is that no one can investigate the inscrutable or alter the inaccessible. Now, realism can be wedded to idealism, as in the case of Plato, materialism, as in Democritus, or to dualism, as in Aristotle and Descartes. For materialism see Chapter 1, Section 6. Which combination is likely to be the more fertile? An objective idealist, or Platonic realist, is bound to make claims that are at best untestable and at worst false, such as that the laws of nature precede the law-abiding things, Heisenberg, that the real plants are but imperfect copies of the ideal Erbpflanze or primeval plant, Goethe, that in the beginning was the Word, St. John, that the Word is the abode of being, Heidegger, or that disembodied ideas can move neurons, Ecclesiastes. A dualist or hylomorphist, like Aristotle, would make only half of the claims of this kind, and so he would fail to satisfy the upholders of the other half. Only a consistent materialist will insist that solely material objects, that is, changeable things, are objectively real. By the same token, he will look for universals, particularly laws, in re rather than anti-rem. Realism, then, is not enough. Indeed, what is the point of professing realism while admitting the reality of supernatural beings or extrasensory perception, the independent existence of ideas, Dilthey's objective mind, or Popper's World 3, or parallel universes? All this idealist fog burns in the strong light of materialism, which postulates that there are no ideas without brains, recall Chapter 1, Section 6. In short, realism without materialism is vulnerable. Realism can only stay sober, testable, and effective, as well as open to new ideas, provided it is combined with materialism and scientism. Materialism without realism and scientism is dogmatic because only the investigation of reality can corroborate it. Worse, vulgar materialism can be obnoxious. Think of Nietzsche's joint adoption of vulgar materialism, physicalism, pragmatism, in particular fictionism and vitalism, anti-scientism, and immoralism. Remember also that, partly because of his epistemological and ethical nihilism, Nietzsche helped discredit rationality and pave the way to postmodernism and fascism, see, example Volin 2004 and Vasher 2004. Finally, materialism, not even combined with realism, suffices to guide the search for truth and smoke out pseudoscience. Think of the socio-biological attempt to explain everything human, even politics, crime, morals, and religion, exclusively in genetic and evolutionary terms. Surely, all this is both materialist and realist, but it fails the empirical tests, it is sheer fantasy. Scientism, the thesis that scientific research is the best cognitive strategy, must be blended with materialism and realism if we wish to keep pseudoscience at bay. Caution, far from involving radical reductionism, scientism is compatible with emergentism, see Bunge 2003a. In sum, to help understand and control reality, materialism must be combined with realism and scientism. This triad may be called scientific hylorealism. 10. Integral philosophical realism is a system that embraces all the branches of philosophy except logic. It covers ontology, semantics, epistemology, methodology, value theory, ethics, and action theory. I submit that it is the philosophy 281 that nearly everyone practices when trying to solve everyday problems. Only philosophers can profess anti-realism, and this solely while writing or teaching. See Table 10.2. Mathematicians do not face the choice between realism and anti-realism because they do not study reality, they deal only in fictions. By contrast, scientists and technologists behave like realists, even if some of them pay lip service to anti-realist philosophies, because their task is to study or design real things. Likewise, serious philosophical investigation is realist, it faces facts, tackles genuine problems, and incites us to go beyond appearance, idle fiction, and knee-jerk action. Only philosophical realism encourages us to chase reality in order to understand or control it. However, realism is not enough. To be deep and efficient, it must fuse with scientism. The moment it does so, realism attracts materialism. This is so because science shows that all the constituents of reality are material, ideas being only processes in highly evolved brains. Thus, scientism somehow entails realism and materialism. Therefore, any attack on either component of this triad is bound to cripple the other two. Furthermore, scientism suggests the possibility of building a scientific practical philosophy. This would include a moral code and a political philosophy designed for real persons in real societies, rather than for angels in utopias. That is, such a code would be designed for individuals facing real moral dilemmas in real social systems, persons with needs and aspirations, as well as with rights and duties. I suggest that scientists and social technologists are best equipped to find out which needs are real, which aspirations legitimate, compatible with meeting other persons' needs, and which types of social organization are beneficial to nearly everyone, as well as viable and sustainable. Obviously, this project goes beyond the limits of the present book, see however Bunge 1989 and 1996 for previews. Table 10.2 Integral philosophical realism versus anti-realism, nihilism, or Galileo and Einstein vs. Nietzsche and Heidegger. Discipline item Realism anti-realism. Ontology universe real and single unreal or plural epistemology knowledge possible impossible semantics truth some none methodology best strategy scientific method intuition axiology values some none or evil ethics morals ego altruism egoism praxeology actions right none or antisocial. In sum, we have defended not only realism but also materialism, scientism, and the project of a scientific ethics. Far from constituting an unstructured set, these four theses constitute the coherent system of research projects shown in this diagram. Scientism. Realism practical philosophy materialism. Scientific philosophy. 283. Fact and pattern. There is an amazing confusion in the contemporary philosophical literature concerning the basic ontological concepts of thing, system, property, state, event, process, fact, and law. For example, some logicians, echoing Plato, state that a fact is whatever makes a proposition true. Wittgenstein, 1922, held that the world is the totality of facts, not things, as if facts were above concrete things. Likewise, David Armstrong, 1999, has proposed to start ontology with the concept of a state of affairs, as if this could exist separately from things. Whitehead, 1919, had famously defined a thing as a bundle of events, as if an event were anything other than a change in a concrete thing. Kim, 1998, defined an event as a property exemplification, rather than a change in one or more properties. And so on. Never mind that ontological concepts can only be elucidated in an ontological theory rather than one by one. And never mind what the people who study and manipulate facts, namely, the scientists and technologists, mean by fact and its kin. The situation concerning patterns, regularities, or laws is just as bad. For example, very few philosophers distinguish objective laws or patterns from the hypotheses representing them, a distinction familiar to every physicist at least since Ampere, 1834. This is why, when confronted with a law statement that proves to be only approximately true, some philosophers have concluded that nature is inexact, Baudru 1898. And, of course, many worlds metaphysicians feel free to imagine worlds satisfying quaint laws or even none, as if metaphysics were a branch of fantastic literature. Recall Chapter 9, Section 6. Worse, nowadays scientific facts, meaning facts studied by science, are often said to be social constructions or conventions on par with road signs and table manners. According to this collectivist variety of subjectivism, there would be no difference between facts and data, laws and rules, or even sitters. 284. And portraits. All this, they claim without offering any evidence, should be lumped into a single category, that of social construction. Accordingly, the notions of reality, objectivity, and truth would be redundant. Scientists would not study facts, they would make them up. They would even restrict themselves to chatting, making inscriptions, and negotiating with colleagues, example Rorty 1979, Latour and Wilger 1986. These extravagances have been so ridiculed, example by Sokal and Brickmont 1998, Bunge 1999, and Brown 2001, that one of the main offenders, Latour 2004, has recently recanted. Given the above-mentioned confusions, it may be apposite to re-examine the ideas of fact, pattern, and their kin that are utilized in the scientific and technological literature. They might prove useful to understand what scientists, technologists, businessmen, and policy-makers are up to. One thing, property and predicate. The most basic or general concept of a thing is that of a bare substantial individual. This is defined as anything that can join another individual to form a third individual. More precisely, we stipulate that X is a bare substantial individual if and only if X can associate, join, or concatenate with other individuals, forming further individuals. Shorter, X belongs to a collection S having the structure of a semi-group. For a detailed formalization and discussion of this concept and its kin, See Bunge 1977a. Of course, real things have other properties, such as energy, in addition to the ability to join with other individuals. A real thing is a substantial individual endowed with all of its properties. In turn, a property of a thing may be conceptualized or represented by an attribute or an array predicate. And a predicate f may be analyzed as a function from a certain domain A to some codomain B, or f, AB, where A may be the Cartesian product of a number n of collections, Bunge 1974a. In particular, if f is a qualitative unary predicate representing an intrinsic property P of substantial individuals, or members of the collection S, f may be analyzed as the function f, S propositions containing f. Thus, if B is a substantial individual, that is, if B is in S, then the value of f at B is f, B, read B is attributed f-ness. Note that this analysis of predication differs from Freya's, who characterized predicates as functions from individuals to truth values. All of the qualitative properties, such as cohesiveness and stability, are representable by such unary predicates. If G is a binary attribute representing a relational property Q of pairs of things, such as separateness or interaction, then 285. G, S times S propositions containing G. For example, if B and C are in S, G, B, C, is read G is predicated of the ordered pair of individuals. The generalization to higher order predicates is obvious. Note that we have tacitly distinguished properties from functions, in particular predicates or attributes. This distinction is unnecessary in logic and mathematics, where the two concepts coincide, because all the mathematical objects are of a single kind, namely constructs. But the distinction is indispensable everywhere else, for one and the same property of a substantial individual may now be conceptualized as a given attribute and later on, in the light of new knowledge, as a different attribute. Remember the historical changes undergone by the concepts, or rather the words, energy and quantity of motion. Realists assume that the physical world took no notice of such conceptual changes. Hence the need to distinguish attributes predicated of things from properties possessed by things. Another rationale for the distinction in question, and one that necessarily escapes the irrealist, is that not all predicates represent properties of real things. In particular, negative predicates, such as mindless, and disjunctive predicates, such as conducting or working, represent no properties of things even though they may occur in our discourse about things. Disjunctive predicates are legitimate provided they define genera, that is, logical sums of species. Examples: herbivores carnivores equals omnivores, and blue collar white collar equals worker. A third reason for drawing the predicate property distinction is that, whereas predicates satisfy some system of predicate logic, and the set of all properties is a Boolean algebra, the properties of things satisfy natural or social laws. More on this below. The following rather typical examples, taken from Bunge 1977b, should suggest the rich variety of property representing functions we must cope with, and will prepare the ground for a general definition. Example 1. Dichotomic global property. Let f, a b represent stability. Then, A equals collection of all concrete systems, physical, chemical, biological, social, or technical. B equals set of all propositions of the form X is stable, where X is in A. Example 2. Qualitative global property. Let f, a b represent social structure. Then A equals S times T, with S equals set of all human societies, T equals set of all time instants, B equals family of all collections of persons. 286. And, for S in S, and T in T, F, St, equals family of all social groups included in society S at time T. Example 3. Quantitative global property. Let F, A b represent the electric charge on a body. Then A equals C times T times UC, where C equals collection of all bodies, T equals set of all instants, UC equals set of all electric charge units, B equals set of all real numbers, so that f, c, t, u, equals r, for c in c, t in t, u in uc, and r in, abbreviates the electric charge of body c, at time t, expressed in unit u, equals r. Example 4. Quantitative global stochastic property. Let f, a, b represent the momentum probability distribution of a quantum. Here a equals q times t times 3. Where q equals collection of quantons, quantum mechanical entities, of a certain species, equals set of all reference frames, t equals set of all time instants, b equals real line, so that f, q, f, t, p, dp abbreviates the probability that quantum q, relative to frame f, at time t, has momentum lying between p and p plus dp. In standard notation, f equals 2, where is the Fourier transform of the state function. Example 5. Quantitative local property. Let f, a, b represent the gravitational potential. Then a equals g times e3 times t times ue, where g equals collection of all gravitational fields, equals collection of all reference frames, E3 equals Euclidean 3 space, T equals set of all time instants, UE equals set of all energy units, B equals real line, so that F, G, F, X, T, U, equals R abbreviates the scalar gravitational potential of field G in G, relative to frame F in, at point X in space E3, and at time T in T, expressed in energy unit U in UE, equals the real number r. Further, the field intensity is defined as the gradient of the field potential. Both magnitudes represent the same thing, namely, the field. The choice between them is a matter of convenience. Example 6. Population is a conspicuous biological and sociological property. It may be conceptualized as a state function p, s times t. From pairs to the natural numbers. Every value p, st, equals n, for n in, represents a possible individual property of s at t, whereas the function p itself represents a general property, or a property of. 287. All the members of the collection S. Shorter, p is universal in S, or p is a universal of S. In each of the above cases the central predicate f represents a property of entities of some kind, or a general property, such as age. And the value of f for some particular entity or thing is an individual property, or property possessed by the individual in question, such as being 30 years old. Individual properties are called tropes in contemporary ontology. 2. State and state function. Some properties, or rather property representing functions, are of special interest to us. They are those describing the states a thing can be in. For example, the mass, stress, and force densities in a mechanical system determine its dynamical properties. They are therefore called state variables or, better, state functions. By contrast, stability, though a property of systems, is not a state function but a sort of outcome of the interplay of certain properties. Nor are t, time, f, reference frame, or u, unit of some kind, state functions, nor, indeed, are they functions of any kind. They are arbitrary members of certain sets, and they are not possessed by anything in particular. They are rather public, in the sense that they can be applied to a number of things. Caution: in any relational theory of time, t must be a value of a function defined for pairs of events. In example 2 above, the function fs, s times tb is a state function for the individual system S. In example 3, the function fcu, c times t times u is a state function for C. In example 4, the function fqf, q times f times t times 3 is a state function for q relative to f. And in example 5, the function f, g times f times e3 times t times u is a state function for g relative to f. The preceding remarks suggest the following preliminary characterization. A function is a state function for a thing of a given kind only if it represents a property possessed by the thing. Whether this representation is faithful, true, is not essential to the function's qualifying as a state function. What is decisive is that the function should refer to the thing and be interpretable as representing or conceptualizing the intended property. The reason is that we must build theories before we can put them to the test to find out whether they are reasonably true. Nor is it necessary for a state function to occur in a theory. State functions are also useful in empirical inquiry, to display the current state of a system and follow its course. For example, a state function for a nation could be a rather long list of values of environmental, biological, economic, political, and cultural indicators, such as average rainfall, life expectancy, GDP, voter turnout. 288. And literacy rate. But, of course, it is best if such empirical values can be plugged into theoretical formulas such as law statements, for in this case one can hope to explain and predict the facts in question. Every scientific theory refers to concrete things of some kind or kinds. And every such theory, whether general such as Maxwell's electrodynamics or specific such as a model of a circular antenna, involves a finite number of state functions to describe its referents. Since some scientific theories, such as Einstein's theory of gravitation and quantum electrodynamics, are true to a remarkable degree, it is reasonable to assume that the things they concern do in fact possess only a finite number of general properties. Let us now consider the whole bunch of state functions for things of a given kind K. In principle they have little in common except for their common reference to things of the given kind. In particular, they need not even be defined on exactly the same domain. For example, one of them may be defined on K, another on K times T, and a third on K times T. However, a harmless trick will assign them all the same domain. Thus, if FL, AB, and F2, CD, where AC and BD, we may adopt the new state functions G1 equals A times CB, such that G1, AC, equals F1, A, G2 equals A times CD, such that G2, AC, equals F2, C, for all A in A and all C in C. But we seldom need to resort to this trick because, as a matter of fact, many state functions for things of a given kind are defined on a common domain. Think for instance of the collection of property representing functions, such as mass density, velocity, and field potential, concerning a continuous medium such as a fluid or a field. They may all be construed as sharing a single domain, namely, some four-manifold. Likewise, the set of dynamical variables, observables, of a quantum mechanical thing are operators in the Hilbert space of the thing in question. Still, whether or not this is in fact the case in a given instance, the above-mentioned procedure will do the trick of regimenting the domain of the state function for the given thing. Therefore we may adopt definition 1. Let phi, A6, with I in n, be a state function for things of a given kind. Then the function f equals, a v1 times v2 times vn, such that, a, equals, for a in a, is called a, total, state function for the things of the kind concerned. If all the 6 are vector spaces, is called a state vector. Notice the cautious indefinite article in the above phrase a state vector. The reason is that there is no such thing as the state function for things of a given kind. Indeed, there are as many state functions as representations, or models, of the thing can be conceived of, that is, any number of them. Analog. 289. There can be any number of portraits and photographs of one and the same person. For example, whereas Lagrangian theories employ generalized coordinates and velocities as the basic state variables, functions, Hamiltonian theories use generalized coordinates and momenta. Furthermore, one and the same representation is compatible with infinitely many choices of reference frame, every one of which will ensue in a different state function. More on this below. This is an instance of the principle of scientific realism, according to which any concrete thing may be represented in different ways. Hence, the anti-realist will be unable to make any sense of the formulas that relate different representations of one and the same fact, such as the Lorentz transformation formulas occurring in special relativity. How do we test for the suitability of a given state function? Ultimately by testing for the adequacy, factual truth, of the model or theory as a whole, in particular that of its key formulas. These are the formulas interrelating the various state functions, that is, the law statements of the theory, on which more below. Still, there may be alternative though basically equivalent formulations of one and the same theory. For example, most field theories can be formulated using either field strengths or field potentials, and the latter are mutually equivalent modulo certain arbitrary constants or functions. In the case of equivalent theories, there are no preference criteria other than those of computational convenience, ease of interpretation, heuristic power, or even sheer beauty or fashion. All of these criteria were tacitly adopted when wave mechanics was preferred over matrix mechanics. To put it negatively, the choice of state function is not uniquely determined by experimental data, but depends partly upon our total knowledge, as well as upon our abilities and goals, and even our inclinations. This consideration will play an important role in any talk of states and state spaces, on which more in the next section. Lest I have given the impression that the choice of state functions is utterly arbitrary, and therefore strictly a matter of taste, let me hasten to state that, whichever state function one chooses, it is expected to satisfy the law statements included in the theory, and this is far from being a matter of convention. Neither is the choice of law statements arbitrary, such statements are expected to be reasonably true to fact. Shorter, every scientific theory contains some conventions, but the choice of theory is not conventional. More on this in the next section. The concept of a state function may be used to elucidate the notion of a concrete system such as a political party, in contradistinction to an aggregate, such as a constituency. Indeed, an analysis of a state function for an entity can 290. Help us discover whether or not it constitutes a system, that is, whether or not it has parts that act upon one another and are thus held together. Indeed, the state function of an aggregate of non-interacting things is uniquely determined by the partial state functions. Typically, the state function of a whole of this kind equals either the sum or the product of the state functions of the parts. Not so in the case of a system proper. Here the state of every system component is determined, at least partly, by the states of the remaining components. Hence, the total state function is no longer separable either additively or multiplicatively. The contributions of the parts become inextricably entangled. This should suffice to wreck the program of methodological individualism in social science. A couple of examples should bring this point home. Think of a system composed of a population of foxes and a population of rabbits occupying the same territory. The rate of growth of each population depends on the numericities of both populations. Each of them varies sinusoidally, though out of phase, in the course of time. The two populations are so entangled that the state function of the whole cannot be decomposed into two partial state functions. A methodological individualist could not even pose this familiar ecological problem, because he does not admit the very concept of a system. If it were up to him, the foxes would die of hunger and the rabbits would multiply without bounds. Actually, the methodological individualist could not even approach the problem of modeling a system containing two electrons close enough to interact appreciably, as is the case of those in a helium atom. This system is described by a Schrödinger equation, classically, by two coupled equations of motion, jointly with the Pauli exclusion principle. The latter is not derivable from the former, and it only applies to entire systems of a certain kind. It selects those total state functions that are odd or antisymmetric in the coordinates of the electrons. That is, the additional law statement is, xy equals yx, where x and y are the electron coordinates. This principle expresses an emergent systemic property, that is, one that the individual components do not possess, whence it cannot be represented by the partial state functions. Therefore, the construction of a state function for the system must proceed from scratch rather than on the basis of the state functions of the individual electrons. The individualist strategy fails once again. More on individualism in Bunge 1996, 1998, and 2003a. 3. State space and event. We are now in a position to elucidate the notions of state and change of state. Let f, a v1 times v2 times vn be a state function for things of a certain kind. 291. Every value f, a, for a in a, represents a state of a thing of the kind in question. In particular, if a equals t equals the set of all instants of time, the value f, t, at t in t, will be said to represent the state of the thing in question at time t. Note, however, that the concept of time has not been presupposed. So far, t is just a dummy. Since f spans the lawful state space Sk for things of kind k, every state of such things is a point in Sk. Note also that there are no states in themselves, any more than there are properties in themselves, except of course in a Platonist ontology. This is no dogma, it is shown by the way state functions are constructed. In fact, every one of these functions represents, by hypothesis, the states of a concrete thing. This remark should suffice to dispose of the ontologies that take states, or states of affairs, as the building blocks of the universe. The life of abstract ideas, such as the concept of a set, is utterly uneventful. Only concrete things can change. Now, change can be instantaneous or nearly so, such as a quantum jump or a car collision, or it may take some time, such as changing places and learning. In the first case one speaks of events, and in the second of processes. Furthermore, as Aristotle taught us, a change may be merely quantitative, as in the case of motion, or qualitative as well, as in the case of the assembly or the breakdown of a system. A light flash, the dissociation of a molecule, a storm, the growth of a bud, the learning of a new trick, and a change of government are events. Actually, these particular events are processes, for, unlike the elastic collision of two atoms, they are complex, that is, they can be analyzed as strings of events or, better, as sequences of states. Being changes of state of things, events are representable as pairs of states, and processes as trajectories in a state space of the things where they occur. By contrast, the emergence of a new property is representable as the budding of a new axis in the state space, and the submergence of a property by the pruning of an axis. Because states are relative to the reference frame and the representation, in particular the choice of state functions, their changes, or rather their conceptualizations, are relative in the same sense. Hence, one may well construct a state space on which the representative point is stationary, and alternative state spaces in which the point is moving. Every conceptualization of change, then, is relative to frame and representation. Caution, every observer is a possible frame of reference, but the converse is not true. Hence, relativity to a frame is not the same as relativity to a subject, or subjectivity. Example 7. Suppose a thing that, in the respect of interest, can be in either of three states, for instance, on, off, and transient, as in the case of a switch. Calling these states A, B, and C, we have S equals A, B, C. Form now all the ordered pairs in S times S. 292. The thing stays in state A, that is, the identity event at A, the thing jumps from state A to state B, and so on. We have thus altogether 9 elementary, not composite, events in S times S, E1 equals UA, E4 equals, E7 equals E2 equals UB, E5 equals, E8 equals E3 equals UC, E6 equals, E9 equals that is, S times S equals UA, UB, UC, E4, E5, E6, E7, E8, E9, where the US are the identity events, which actually are non-events. Suppose now that all of these events are lawful, that is, really possible. In this very particular case, then, the event space is E equals S times S. In general, E is properly included in S2. A standard representation of finite event spaces like this one is a Moore graph, familiar from computer science. Certain events can compose to form more complex events, others cannot. For example, event E4 equals above can be followed by event E5 equals, but not by E9 equals. The composition of the events E4 and E5 amounts to the net event E6 equals. In other words, event E6 can be analyzed as the composition of events E4 and E5. To symbolize the composition of events we use the asterisk and write, E4 asterisk E5 equals E6, or, explicitly, asterisk equals. Intermediate states do not show up in the net change, they are absorbed. On the other hand, the complex event asterisk, which is the reverse of the former, cannot occur, and so it is left undefined. In other words, asterisk is a partial, not everywhere defined, operation in the event space E. More precisely, asterisk is an operation such that, for all A, B, C, D in S, IFFB equals C asterisk equals not defined IFFBC. If E and F are two events in E, then E asterisk F equals G is another event in E, consisting of event E followed by event F. In general, not all state transitions are possible. For example, the transition is impossible. Moreover, if a state transition is possible at all, it may occur in more than one way. That is, different trajectories in a state space may have the same endpoints. In other words, two different processes, one along a curve G and the other along a different curve G, may result in the same net change. The two functions must be lawful if we are to allow only lawful events and discard lawless ones, such as miracles. In other words, G and G must be compatible with the laws of the thing under study. They need not be law functions. In general they will be laws cum circumstances, for instance field laws together with specifications of the field sources and the boundary conditions. This suggests introducing definition 2. Let S be a state space for things of some kind, and let S and S. 293. Be 2 points in S. Then a lawful event, or process, with endpoints S and S will be representable by a triple, where G, SS is compatible with the laws in question. For a particular transformation G we may focus on the endpoints of the net change, that is, on the initial and final states of the process. The ordered pairs in SG times SG constitute the space of events of the things considered for the transformation G, or EG for short. In general, EG is a proper subset of SG times SG, because G may exclude certain conceivable but physically impossible changes. For process. A process may be defined as a string of events, for instance, equals E1 asterisk E2 asterisk E3 asterisk N. However, this definition only works for finite state systems such as digital computers, or rather the idealized models of computers that occur in mathematical computer science, as different from the models used by computer engineers. Indeed, even the simplest physical thing, such as an electron or a photon, can be in any of a non-denumerable set of states, and it can undergo continuous changes in addition to quantum jumps. This is one of the many reasons that the computer metaphor of the brain and its mental functions is so shallow and misleading. A more realistic definition of a process, applicable to all state spaces, is this: a process is a lawful sequence of states. More precisely, we adopt definition 3. Let f, AV be a state function for things of a certain kind, and SL the set of lawful states that those things can be in. Then the sequence equals of states is a really possible process occurring in the things in question if it proceeds along a trajectory G, SL compatible with the laws of the things of the kind in question. If A equals T equals time, then equals is a temporally ordered sequence of states. Upon reversing the sign of T we get equals, which is the time reversed image of it would be mistaken to interpret as representing a thing plunging into the past, or as involving the backwards flow of time. See Bunge 1959b for a critique of the literal interpretation of the Feynman diagrams, which involve such fictitious travel backwards in time. The exchange of t for t, and consequently the substitution of negative velocities for positive ones, and conversely, is only a paper and pencil operation that need not represent a real process. When reference to a real process is intended, what is meant by time reversal is not operating Wells's time machine, but just inverting the velocities, and spins if any, of the entities concerned. More on this and the following in Bunge 1968a. It is well known that Newton's equations of motion for point particles are t. 294. Invariant, that is, they do not alter under the substitution of t for t. By contrast, Fourier's equation for the flow of heat in a body is not t-invariant. The trajectories of ideal, perfectly elastic, billiard balls on an ideal, frictionless, pool table are t-invariant, as long as the balls do not fall into any of the pockets of the table. In other words, their time-reversed images are physically possible. By contrast, scrambled eggs do not unscramble, and alpha particles do not re-enter the nuclei that emitted them. There are, then, laws and processes that are t-invariant and others that aren't. A process or history is said to be t-invariant, or reversible, if its time-reversed image is really possible. Otherwise it is said to be irreversible. A law statement is t-invariant if it does not alter upon the substitution of t for t. The relation between t-invariant processes and t-invariant law statements is this: if a process is t-invariant, then its laws are t-invariant as well. The converse is false, whence the two kinds of t-invariance are not equivalent, contrary to popular belief. In other words, some irreversible processes, such as radioactive disintegration, can be described with the help of t-invariant law statements. There are two reasons for the inequivalence of t-invariant processes with t-invariant laws. The first is that a process, or history, is usually accounted for by some logical consequences of the basic law statements concerned, and the former may lack the symmetry properties of the latter. For example, Maxwell's equations are t-invariant but, whereas the electric field intensity does not change upon time reversal, the magnetic induction is inverted. A simpler example, a sinusoidal oscillation is not t-invariant even though it solves a t-invariant equation of motion. The second reason for the inequivalence in question is that processes are described by logical consequences of basic law statements together with constraints, boundary conditions, and constitutive equations, any of which is bound to further restrict the set of really possible trajectories. A simple example is that of a rain droplet falling onto the middle of a sliding roof. The reversed motion, resulting from the inversion of the velocity, would take the droplet past its point of impact, to the top of the roof and beyond. We exclude this conceptually possible trajectory by adding the condition of continuity of the velocity, not only the trajectory. A spatial analog is this. Maxwell's field equations have solutions representing incoming, convergent, electromagnetic waves as well as outgoing, divergent, waves. Since no convergent waves have been observed, one discards such solutions by imposing an additional condition on the asymptotic behavior of the solutions, Sommerfeld's Australingsbedingung. A moral of this story is that, to judge whether a conceptually possible event or process is really possible or else impossible, miraculous, we must check. 295. Whether it satisfies its laws together with all of the pertinent subsidiary conditions. Interestingly enough, the latter are often afterthoughts prompted by a negative result of the comparison of the theory with reality. An anti-realist would never hit on such subsidiary conditions and would insist on making contrary to fact predictions. Being averse to distinguishing theory from reality, he is bound to condone miracles. Realism, then, is a necessary condition for doing genuine science and avoiding bogus science. 5. Objective pattern and law statement. Realists distinguish objective patterns from the propositions, example equations, representing them. This allows them to explain a typical endeavor of scientists, that of attempting to uncover regularities. The same distinction helps explain a good portion of the history of science as the history of successive approximations to the truest possible representation of objective patterns. Objective patterns, be they natural, social, or mixed, are supposed to be regularities or constancies with broad scopes, namely, entire species of concrete things or even genera of such. Every such pattern can be conceptualized in a number of ways, in fact, in as many as there are choices of state functions. Such conceptualizations are called law statements. In short, we distinguish objective laws or patterns from their conceptual representations. And we assume that the objective patterns do not change when their conceptual representations alter. In particular, scientific revolutions may impact society, but they do not change the universe. In addition to objective laws, patterns, and law statements, there are higher-level principles concerning either patterns or law statements. Instances of these are the requirement of Lorentz covariance, and the philosophical principle that all facts satisfy some laws, Bunge 1959b. In sum, the word law denotes three different concepts, which we identify by a subscript each. L1 equals objective pattern. L2 equals law statement equals proposition representing an L1. L3 equals metanomological statement equals proposition about some L1 or L2. Let us focus on L2. A law statement may be regarded as a restriction on certain state functions for things of a certain kind. Such a restriction is neither stray nor arbitrary, it must belong to a system, theory, and it must have been confirmed to a reasonable degree with the help of observations, measurements, or experiments. The first condition disqualifies empirical generalizations, and the second untested or false formulas. Law statements may take a number of forms, depending not only on the things they refer to but also on the state of knowledge and even on the 296 mathematical ability and the goal of the scientist who proposes them. All of the following are conspicuous simple forms of law statements. Example 8. Rf equals V, where Rf is the codomain of state function f, and V some well-defined set. Thus, nothing can travel faster than light, and the prices and quantities of goods cannot be negative. Example 9. F/T0, where T is in T, and T is a subset of the real line occurring in the domain of f and representing time. Example 10. df/dt equals g, ft, with g a specific function of t(t2). Example 11. F, q dq/dtt, dt equals extremum, with t1 and t2 designated t1 elements of t. Example 12. F2, xy, equals do dv f1, u, x, v, y, with f1, f2, e3 times e3. Example 13. 2f1/ x2 equals f2, with f1, f2, e3. The preceding considerations suggest adopting the following definition for: let f be a state function for things of a given kind. A restriction on the possible values of the components of f, or a relation between two or more such components, is called a law statement if 1. It is included in a consistent factual theory, and 2. It has been satisfactorily confirmed, for the time being. If only condition 2 is met, the restriction is called an empirical regularity. Consider now the collection Lk of law statements for things of kind K, calling L an arbitrary member of that collection. L, x, may be regarded as the value that the predicate law function L takes at xk. This function has the form L, k Lk. Since at each stage in the history of science we only know a finite subset of Lk, this collection is variable, it is not a set proper. For example, in the elementary theory of electric networks, a battery resistor circuit with a single loop and at room temperature, an individual of class K, satisfies a single law, namely Ohm's. This law statement is not true for all conductors, and it is only a first approximation for conductors at very low temperatures. Further, the particular law for the ohmic resistance of conductors of a given kind is called a constitutive equation. Ohm's law can be written as follows: for every x in K, L, x, equals E, x, equals R, x, I, x, where E, R, and I represent the electromotive force, the resistance, and the current intensity respectively. Thus, in this case the law predicate L is the function L, K L K such that, for every x in K, L, x, equals Ohm's formula. This manner of writing shows clearly that laws interrelate properties, and are themselves properties of things. That is, they are possessed by things instead of hovering above them. That is, laws are universalia in re, recall chapter 9. If 297. A more explicit evidence for this claim is called for. One may write Ohm's law in even more detail: E, I, R, K, and L, K L K, such that the above condition, Ohm's, holds. This shows also what Ohm's law is about, namely, physical things of a certain kind K. Which suffices to refute the views that physical, or other, laws are subjective or else social constructions. Occasionally one reads about natural objects, such as brains, whole organisms, or even molecules, behaving in accordance with algorithms, such as evolutionary algorithms and algorithms for computing limb movement, perception, or even emotion. This idiom betrays ignorance of both science and algorithm. Indeed, algorithms are, by definition, rules for computing something, such as the squares or the square roots of numbers. By contrast, the natural laws are thoroughly natural, they emerged along with the things they inhere in. This is why the expression natural algorithm is an oxymoron. So much for laws or natural regularities. Let us now deal briefly with norms or artificial regularities, such as the moral and legal norms. We propose definition 5. A norm or rule is a man-made restriction on the possible values of the components of a state function, or a man-made relation between two or more such components, compatible with the law statement, S, satisfied by the state function. This definition incorporates the idea that, no matter how stupid, brutal, and powerful humans may be, they cannot violate the natural laws. In other words, every norm or rule involves in some way or other the pertinent natural laws. In particular, the efficient norms for assembling or operating a machine or a social organization must satisfy the laws possessed by the components of either system. 6. Lawful state space. The point of constructing mathematical models of things of a certain kind is to represent as accurately as possible the really possible, lawful, states of the things in question, and perhaps their really possible, lawful, changes of state as well. Hence, every such model is centered on a state space for the things referred to. A few typical examples should give us a feel for this matter. Example 14. In the elementary theory of the ideal gas, the state function is the triple consisting of the pressure, volume, and temperature functions. The domain and codomain of each of these functions are the set of ideal gas bodies and the positive real line respectively. Hence, the corresponding state space is a box contained in plus 3. Example 15. In the genetics of populations, three state functions are often 298 employed: the size n of a population, the frequency, or rather probability, p of occurrence of some particular gene, and the adaptive value v of the latter. Each of these is a real valued function. Hence, for a system composed of two interacting populations, A and B, the state space is the region of plus 6 spanned by the vector in the course of time. Example 16. In my theory of social structure, Bunge 1974d, the instantaneous state of a community may be construed as the distribution of its population among the various social groups in the community. Hence, the component phi of the total state function may be taken to be the column matrix Nij for a fixed I, the elements of which are the populations of the mutually disjoint social groups resulting from the partition of the total population, at the given time, by the ith equivalence relation with a social significance, such as equal occupation or similar educational level. Example 17. In chemical kinetics, the instantaneous state of a chemical system is described by the values of the partial concentrations of reactants and products. Therefore, the state space of the system is inside, plus, n, where n is the number of system components, reactants, catalysts, and reaction products. Example 18. In electrostatics, the state function is F equals where represents the electric density and the potential of the electric field. The domain and codomain of both functions are E3 and respectively. Hence, the local state of the given field is the value of F at x E3, and the entire state space is the set of ordered pairs 2xV, where V denotes the region of E3 occupied by the field. Example 19. In quantum mechanics, the state of a thing is represented by a ray in the Hilbert space associated with the thing in question. Since a thing of this kind typically is not attributed a point-like location, but is assumed instead to be spread over some spatial region V in 3 space, with a definite probability distribution, the state of the thing is the set of all the values its state vector takes in V. Before attempting to draw general maxims, let us emphasize a point of method made earlier. We may certainly assume that, whether we know it or not, every isolated thing is, at each instant, in a definite state relative to some reference frame. That the state may be a superposition of eigenstates is true, but beside the point. Yet our representation of such a state will depend upon the state function chosen to represent the thing, and this choice depends in turn upon the state of our knowledge as well as on our goals. What holds for every single state holds a fortiori for the entire state space for a thing. That is, far from being something out there, like stars and people, a state space for things of a certain kind stands with one leg on the things it refers to, a second on a reference frame, and a third on the theorist or modeler. 2. 299. Persuade oneself that this is so, suffice it to take another look at example 18 above, where a reference frame at rest relative to the field source was tacitly assumed. If now the same system of electrically charged bodies is considered relative to a moving reference frame, a 4-vector current density will have to replace the single charge density, and a 4-vector potential will take the place of the single scalar potential. Seen from a moving frame, a charge is a current surrounded by a magnetic field. Alternatively, and this is where the scientist's freedom comes in, the 4-vector potential can be replaced by an antisymmetric tensor representing the electric and magnetic components of the field relative to the new frame. Incidentally, the problem of finding an adequate vector potential is of the inverse kind. For instance, given A, H equals the curl of A, but there is no rule for finding A from H. Having emphasized the conventional ingredient of every representation of the states a thing can be in, let us now stress that every such representation has an objective basis as well, as long as the representation has a grain of truth. For one thing, a state function may not take values in its entire codomain, but may be restricted to a subset of the latter, and this by virtue of some law. Indeed, recall that law statements are restrictions on state functions, section 5. Therefore, for every component of a state function for things of some kind, the focus of our concern will be the range of the function rather than its entire codomain. If we now take all the components of a state function for things of a given kind, and form the Cartesian product of their respective codomains, in tune with definition 1, we obtain the conceivable state space for those things. This is precisely what we did in the examples that led off the present section. However, this restriction is insufficient to identify the really possible states of a thing, as should become apparent from the following examples. The total population of organisms of a given kind, in a given territory, is constrained not only by the carrying capacity of the latter but also by the birth and death rates, as well as by such additional factors as sunshine, rainfall, and plagues. Again, although the codomain of the speed function for a body is the entire interval 0c, the speed of an electron traveling in a transparent medium will not come close to the upper bound c, the speed of light in a vacuum, for such a body is subject to further laws, such as those concerning the radiation emitted by the electron traveling through a transparent medium. In general, only those values of the components of a state function that are compatible with the laws, constraints, and initial and boundary conditions will be really, not just conceptually, possible. In other words, because the law statements impose restrictions upon the state functions and their values, hence upon the state spaces, only the states in certain subsets of the latter are 300. Accessible to the things in question. We shall call the accessible region of a state space the lawful state space for the things in question, in the given representation and relative to a given reference frame. To say that a thing of a certain kind behaves lawfully amounts then to saying that the point representing its instantaneous state cannot wander beyond the bounds of the lawful state space chosen for the things of the kind in question. The preceding remarks can be summarized into definition 6. Let f equals a v1 times v2 times vn be a state function in a theoretical model for things of kind k, and call Lk the variable collection law statements of the Ks. Then the subset of the codomain v1 times v2 times vn of f restricted by the conditions, law statements, constraints, and initial and boundary conditions, in Lk is called the lawful state space of such things, or SL for short. Example 20. In example 18 above, the conceivable state space of an electrostatic field was S equals 2xv, where v is included in E3. Since the two components of the state function f equals are linked by the Poisson law statement 2 equals 4 and the boundary condition that the potential vanishes at infinity, the lawful space state for the thing, electrostatic field, is SL equals 2xv and 2, x, equals 4, x, and, equals 0, a set that is properly included in S. What holds for the state spaces of natural and social things holds also for the state spaces of technical systems such as machines, factories, and armies. Indeed, all artifacts satisfy not only laws but also norms or rules, which amount to new restrictions on the state functions for the things concerned. Recall definition 5 in section 5. However, artifacts, including formal social organizations, have emergent properties that their natural components lack, this being why we care to design, build, and use them. Hence, the work of technologists, managers, and planners does not boil down to shrinking state spaces for natural things. It involves setting up new state spaces not found in the natural sciences. 7. The category of facts is very broad. It includes a property having a given value, a thing being in a given state, a change of state, whether a point event, or instant transition from one state to another, or a protracted process, or sequence of states, and a fact fitting a given pattern. Things, by contrast, are not. 301. Facts, they are the supports or bearers of facts, as in this car started and that car passed by. Whatever involves a thing is a fact, and nothing that fails to involve concrete things is a fact. For example, it is a fact that this is a printed page, but it is not a fact that twice 2 equals 4. All facts are singular, there are no general facts. Some facts are composite, but there are neither negative nor disjunctive facts, negation and disjunction are de dicto, not de re. A pattern, regularity, or constancy can be of either of the following kinds. It can be objective like the law of gravity, or conceptual like the associative law. If objective, a pattern can be a law of nature or a norm, custom, or convention in force in some social group. A conceptual pattern can be either purely logical or mathematical, such as P or not P, or it may represent an objective pattern, in which case we call it a law statement. It is a tacit ontological principle of scientific research that all concrete things behave in accordance with laws. This, the principle of lawfulness, cannot be proved, but it animates all modern scientific research, which to a large extent is the search for or application of laws and norms. See, example Bunge 1967a. Lawfulness is often mistaken for uniformity. Actually, These are different though related concepts, and so are the corresponding principles. The lawfulness principle states that every state or change of state of an arbitrary thing satisfies some laws. By contrast, according to the principle of uniformity, the laws are the same across space and at all times. Put negatively, no laws would ever emerge or disappear anywhere. In a stronger version, this principle states that the same events recur everywhere and at all times, that there is never anything new under the sun. This strong uniformitarian is false. It was falsified in natural science in the mid-19th century, with the emergence of evolutionary geology and biology, but it is still going strong in social science. In particular, it is inherent in all of the rational choice models, for they assume the constancy of both human nature and personal preferences. Every law statement is about concrete things of some kind or other. It consists in a restriction on the possible values of the state functions of the things in question, or on the possible relations among components of such state functions. The same holds for norms or rules. Since the values of a state function represent possible states of the corresponding things, a law statement tells us which are the possible states a thing can be in, and which are the changes, events or processes, it can undergo. Since every concrete thing is in some state or other, is engaged in some process or other, and is assumed to satisfy some set or other of laws, or else norms, the concepts of thing, property, state, event, process, fact, law, and norm are intimately connected with one another. Yet they are usually treated, if at all, in separation from each. 302. Other. Worse, most of the definitions of these concepts proposed by philosophers are at variance with their meanings in science and technology, which is where they are used every day, if mostly in a tacit fashion, and in the most precise and consistent way. When in Rome, do as the Romans do. When in scientific territory, speak the language of science.